Statistics is one of the most used concepts for all the companies. When it comes to data science, or if you talk about machine learning, the basic things you need to know, that is statistics. But why? Let me tell you a few examples where we are actually using statistics. Suppose there is a weather forecasting. In that case, what do you think? What we use? We use statistics concepts to basically forecast our weather. Or if you are talking about credit card fraud analysis, so in that case, we try to understand a particular transaction is a fraud transaction or a genuine one. How we do that? Again, stats comes into the picture. The last but not the least, if we talk about the stock market prediction, in that case, if you want to say in the upcoming week, the stock market is going to crash or it's just going to be, in a good position, how you do that? So in order to do that, you have to use again stats. So keep that in our mind. We came up with a tutorial where we are going to talk about the basic statistics you need to know to start your career with data science. So let's start with what are the agenda we have for this particular video. Before complete the video, let me tell you, Great Learning has came up with the free initiative of Great Learning Academy, where you will get almost 80 plus free courses, and after completing your course you can claim your certificate as well, and you can use these certificates in your resume and also in your LinkedIn profile to show that you actually skilled up yourself. Do not forget to subscribe Great Learning, and also please do hit like this video if you feel like it's going to help you in your career. So let's have a look at the agenda. So first we are going to talk about what's the difference between statistics and machine learning. Then we will jump into the types of statistics like descriptive statistics, prospective statistics and predictive statistics, right? Then we will look into the types of data we have. Then we will jump into the correlation concepts, and then we will see what is the covariance concepts. Then we will jump into the introduction to probability, how probability comes into the picture. Then we will see the conditional probability with Bayes theorem. Then we will see what is Bell curve and sampling distribution. Then we will look into what is normal distribution. And then we will see what is discriminant analysis and also what is binomial distribution. Then we will have a look at what is Poisson distribution. And with that, we will start our journey with statistics for data science. So let's get started with the tutorial.
What you now need to do is you now need to be able to get the data to solve this problem. So therefore, the statistical way of thinking typically says you formulate a problem and then you get the data to solve that problem. The machine learning way of looking at things typically says, here is the data. Tell me what that data is telling you. Many of my colleagues and I myself have run into this problem when going for interviews, etc., etc. And so statisticians say that we're not getting jobs out there. And so I go to people who are hiring and saying that, why don't you hire statisticians? And I reach an interesting conclusion to this entire discussion, that sometimes around the way the interviewer who's interviewing the statisticians for a data scientist job asks the question, here is my data, what can you say? And the statistician answers with something like, what do you want to know? And the business guy says, but that's why I want to hire you. And the statistician says, but if you don't tell me what you want to know, how do I know what to tell you? And this goes round and round, right? No one's happy about this entire process. So there's a difference in the way these two communities approach things. My job is not to resolve that. Because in the world that you will face, you'll see a lot more of this kind of thinking than you'll see in this kind of thinking. Because in this world, the data is cheap and the question is expensive. And you're paid for asking the right question. In this world, the question is cheap and the data is expensive. You're paid for collecting the data. So sometimes you will be in a situation where this is going to be important. For example, let's suppose you're trying to understand who's going to buy my product. You're asking the question, let's say that my products aren't selling and you want to find out why. What will you do? Get what data? So let's say that you're selling, I don't know, what do you want to sell? You want to sell watches, say? So let's suppose people aren't buying watches anymore, which is a reality, correct? So you're a watch company. Who buys watches these days? The entire business model of a watch is disappearing. Do you have watches? Some of you have. He has. Actually, a surprising number of you have. Maybe they do different things these days, right? That seems like a very... That's a fitness device, it's not really a watch at all. So something like this was actually with my daughter at lunch today. So she got something like this. I'm not sure. My wife, who's an entrepreneur, runs her own company. She came back from Delhi. She came back with 2 of these. I don't know where she picked them up. So my daughter, the first thing she did, she took one of this and she took this thing out. Because she thought of the whole wristband as an unnecessary idea. I mean, that didn't occur to her. I mean, that's a separate thing. That's a nice little beautiful red wristband, etc. So a watch is a different thing. But let's say that you're a watch company, nobody's buying your watches. Or fewer people are buying your watches. Now, how are you going to solve this problem? Or how are you going to process this information? What do you want to do? What do you want to know?
Check the models testing.
Okay. But remember, I'm asking this question also from an analytical perspective. So when you say that to check the model and see what is not sold, that assumes the whole data question. So first order, you'll see sales. For whom and when and how? How do you structure your data? How will you arrange the problem?
Let's say what are your competitors selling?
Okay, that makes problems even harder because now you're going to look for data that isn't with you. No, he's right. Maybe people are not buying watches because they're buying something else. That's a reasonable thing. But let's keep this problem simple. Let's consider only data that is within you. We'll go outside, not to worry. But let's say that I'm looking at my data. What data do I want to see and what questions do I want to ask of it? So sales year by year, types, and then what comparisons do I want to do?
Year on year.
Year on year?
Region wise.
Region wise, age. With what purpose? What question am I asking the data?
What section of customers are buying my product or
what section of customers are buying my product compared to what?
What has changed in terms of the
what are my biggest set of customers?
So that's one thing. Who are my biggest customers? Okay. That's a very interesting question to ask, except that question implies that I needed to know who my biggest set of customers sort of could have been. But it's a good point. Where is the bulk of my sales coming from? Then someone else says something about time. Is it going down? So you can look at things like saying that for which group of customers are my sales going down the most? For example, you could ask that. I'm not saying that's the right question, but that's a possible question to ask. So let's suppose you follow that approach, that I'm trying to understand. I know that my sales are going down. That's an obvious thing. My CEO is telling me, my CFO is telling me, and if I don't stop this, we're all going to be out of a job. Correct? The HMT factories in Bangalore are not in good shape. One of them, I think, has become the income tax office. Right, somewhere in the Malleshwaram area. So that's going to happen to me if I don't do this well. So I know my sales are going down. But I don't know by how much and particularly for whom. So are there segments for which the sales are going down? Which segments are sales going down the most? In which segments are they going down a little bit? How fast are they going down? I can ask questions of that sort. Now, what conclusions at the end of this do I want to be able to do? How do I want to use this information? Now, for this, you usually follow something like a 3-step process, and you may have seen this, and this covers both these sides. And these words should be familiar to you to some extent. The first is called descriptive. The second is called predictive. And the third is called prescriptive. Have these words been introduced to you, at least in this you've read it, I'm sure. You all cruise the web and look at blogs and things like that. Nothing new in this, I'm sure. But I just want to set a context because it's going to talk a little bit about what we're descriptive. There's a C here. So descriptive, predictive and prescriptive. Now what is a descriptive problem? The descriptive problem is a problem that says that describe for me where I'm losing my sales and when I'm losing my sales. It just describes the problem for me. It tells me where the problem is. It locates it. It isolates it. The predictive problem says, look at this data and give me an idea as to what might happen or what would happen if I change this, that or the other. So let's suppose I do the following kind of idea. I say that, let me relate my sales to my prices. Let me try and understand that if I reduce my prices of my watches, will more people buy them? Conversely, if I make my watches luxury items, increase the price of a watch, remove a low-end brand and make a watch an aspirational thing, a decorative item, a luxury item, a brand item, so that people wear a watch not to see the time but also as a prestige statement, as a fashion statement. Whatever it is, if I do this, then what will happen? That's predictive. I'm trying to predict something based on it. I'm trying to say if something happens to, let's say, one part of my data, what will happen to the other part of my data? And then based on that, the doctor carries out a predictive analysis of you. Because I see this, I now think you have this issue. You have this thing going on. Let's say I'm diagnosing you as being pre-diabetic. You're not yet diabetic, but you're happily on the way to becoming a diabetic. Now, because of this, I now have to issue you a prescription. I now should tell you what to do. So there's the data that comes from you. That data in some way is modeled using the domain knowledge that the doctor has. And that model has translated into an action. That action is designed to do something. Typically, it's designed to do something actually fairly complicated. The first action that the doctor tries to do is, number one, let's say, do no harm, the Hippocratic Oath. First, let me make sure that I don't do any unnecessary harm to the patient. Then let me, shall I say, optimize his or her welfare by making sure that I control the blood sugar the best and that I postpone the onset of diabetes as best as I can. It's a complex optimization problem of some sort. In a business also, it's a complex optimization problem. Right? I need to be able to sell more watches. But I also need to be able to make money doing so. I can increase my sales, but if I increase my sales and my profits go down or my earnings go down based on the cost, then that's a problem. But at the same time, if I try to run a profitable business and nobody buys my product, that also is not a particularly good idea. Then there are other issues maybe in running the company. I've got employees that I want to keep on the boards. How do I run the company in such a way so that it needs that particular labor force? I have finances to take care of. I have loans to repay. How do I get the cash flow in order to repay the bank loans that I have? So the prescription has to meet lots and lots of requirements. If you are building an autonomous vehicle, you'll have situations saying the car has to do this. But it also has to follow certain other rules. For example, if it sees someone crossing the road, it should stop. But it shouldn't stop very suddenly. Because if it stops very suddenly, it's going to hurt the car, it's also probably going to hurt the driver. So it needs to stop, but it shouldn't stop too suddenly. It has to follow the rules of the road. Because otherwise the computer will simply say, oh, you want me to avoid the person crossing the road? I'm just going to go behind the person. And you're going to tell the car, please don't do that, because there's a house next to it. You can't just sort of do that, oh, you didn't tell me that. You just told me to avoid the person. You didn't tell me about the house. Okay, we'll put that as a constraint in our program and see how well it goes. So prescription is problematic. Another simple way of doing it might be to say that description is how many centuries has Virat Kohli scored. Look up Cricinfo and it will give you the answer. Prediction might be try to guess how many centuries Virat Kohli will score in the World Cup. Prescription might be how do we get Virat Kohli to score more centuries in the World Cup. And as you can figure out, you're going from a purely data-based version of the problem into something that's only notionally about the data. Data will help you, but there's a lot more than the data when it gets to that. What we'll do today, what we'll do now, once I've finished talking to you, is we'll take a look at what the descriptive part of analytics is. So the descriptive part of analytics is talking about simply describing the data without necessarily trying to build any prediction or any models into it. Simply telling you the way it is. This is hard. This is in itself not necessarily an easy thing to do, because you need to know very well how to do that and what are the ways in which one looks at data. This is skillful in itself. So, for example, let's suppose that you're a doctor. You go to the doctor, and the doctor is looking at your symptoms, and the doctor recommends a blood test. Now, how does a doctor know what blood test to recommend? Based on the symptoms. But remember that potentially there's an enormous amount of information in you. All of us as biological things carry an enormous amount of information in our blood, in our neurons, in our genes, or wherever. You know, if you're talking about big data, as I said, there's 2 meters inside every cell, and there are a few billion neurons in your head. You don't need to go far to see big data. You are big data. You are one walking example of big data. We all are. Right? Now, in that big data, what little data does the doctor know to see? That's the descriptive analytics problem. The doctor is not doing any inference on it. The doctor is not building a conclusion on it. The doctor is not building an AI system on it. But it's still a hard problem. Because given the vast amount of data that the doctor could potentially see, the doctor needs to know that this is interesting to me, and this is interesting to me, and this is interesting to me. And this is interesting to me in this particular way. For example, a blood test. Let's suppose that I draw blood from you for a particular purpose. Let's say for blood sugar. Correct? Leaving aside the biology of how much blood, etc., to draw. None of you, I guess, are a doctor. Any of you are doctors here? Any doctors in the room? No doctor, so I can say whatever I want to. You won't understand what I'm saying. No, but I'm old enough that this is a real problem for me. So you have a large amount of blood that's flowing through you. We all do. This blood carries nutrients. What that does is that every time there is a nutrient inflow, the blood looks a little different. So if you eat, your blood looks a little different. Because that's your blood's job. The blood's job is to carry nutrients. So if you want to run, you want to walk, if I'm walking around, my legs are getting energy from somewhere. The energy needed to my legs is being carried from the blood, and it is being generated through inputs that I get. Some of it because of the air that I breathe, from where it gets the oxygen to burn things. Some of it from the food that I've eaten, the nice lunch that I had, where it gets the calories to do that. So therefore, based on what my energy requirements are, and based on what I've eaten, my blood is not constant. My blood content is what is known as a random variable. What's random about it? Because it looks a little different all the time. Your blood at 12 o'clock is going to look a little different. 12 o'clock at midnight is going to look a little different from 12 o'clock at noon, because it's doing something a little different. The same phenomena is there everywhere. If I were to, for example, measure the temperature of the oil in your car or in your two-wheeler, what do you think that temperature will be? It depends. First of all, it depends on whether the car is running or not. It depends on whether it has run or not. It depends on how much oil there is. It depends on how you drive. It depends on the temperature of the car. The answer is it depends. And the same is true for your bodily fluids. So this becomes a slight problem. Because if it is random, then from a random quantity, how do I conclude what your blood sugar is? How does a doctor reach a conclusion of any sort? Average of what? Average of particular duration. So there are multiple averages that you can get. First of all, there is a question of saying that if I take blood from you, how is the blood usually collected? So the phlebotomist comes and usually takes an injection from one point. Let's say by some strange accident, this is thoroughly inadvised, but let's say by some strange accident, two different people are drawing blood from two hands at the same time. Do not try this at home. But let's suppose they do this. Will they get the same blood?
Depends. Ideally, yes.
Ideally, yes.
It depends.
What time?
Two different.
Same time. Right, at the same time, as I said, do not do this at home. But at the same time, you're getting two different samples. There's not just a question of time. Your blood is not going to look the same even within your body at one period of time. Even from the left hand, even from the right hand at exactly the same period of time, it's not going to look the same. There is a slight problem that's somehow a little obvious, that you know your heart is in the middle. Right? Your heart is actually in the middle, but it beats to the left. Why? Because the heart is what? The heart is both a pump and a suction device. The pump side is on the left, the suction side is on the right. So your blood pours out from your left side and it goes back in on the right side. So there's a slight asymmetry in your body between left and right. One side tends to go out, the other side tends to come in. It's slight, it mixes up all in the middle. So one sampling idea is that I'm taking a sample of blood from you, and it's just one example. The second question is, as you were saying, it's a question of time. So you can average over time. Now if you average over time, this is a little easier. You can say I'm going to do this maybe before eating, after eating, a little after eating. So for those of you who have blood pressure tests, for example, blood sugar tests, once they ask you to do it, fasting. And then they ask you to do it some 2 hours after eating. Do they tell you what to eat? Sometimes with glucose. Okay. Sometimes they don't. They sort of say that based on what you naturally eat, let me figure out what you are processing. They expect you to eat a typical meal and not go and eat, large amounts of KFC if that is not what you normally eat. Just eat what you normally eat. If you're vegetarian, eat normal vegetarian, eat normal food and then figure it out. Let's see how good your body is at trying it out. So it's saying, do a normal thing and I'll take another normal sample. Then one of you said something very interesting. They average things out. Now what does averaging do?
Neutralize.
That's an interesting word to use. Neutralizes things.
Provide a general idea.
Provide context. Context of what? Context, that's a good point. So what is the doctor trying to do? So let's simplify things a little bit and say that let's suppose that the doctor has a threshold. Let's give it a number. Let's say the doctor says that if your blood sugar is above 140, I'm going to do something. If your blood sugar is say less than 140, I'm not going to do anything. I don't know whether this is the right number or not, but just let's make it up. Now the doctor is going to see from you a number. It may be a single reading, it may be an average, it may be a number of things. How is the doctor going to translate what they see from you and compare it to the 140? How is that comparison going to be made?
Maximum number of people.
Normalizing the value.
Maximum.
So let's suppose I have just one reading. So let's suppose that I have one reading and that reading, is 135. I've just got one reading from you, 135. What does that tell me? No test required. One argument is, it's simple. Let's take a very machine learning computer science view to this. 135 is less than 140. So now he's saying, yeah, but you know what? Let's say that 135 and another guy who say 140, 120, there should be something that says that this 135 is a little bit more trouble than 120. Closer to the threshold, as he says. So maybe in other words, this threshold isn't quite as simple as I thought it was. So I can solve this problem in one of two ways. One way to do this is to make this 140 a little range. This is something called fuzzy logic. Right? In other words, the question you're asking becomes fuzzy, not as crisp. You're not fiddling with the data, you're fiddling with the boundary, you're fiddling with the standard. The other way to do that is to create a little uncertainty or create a little plus minus around the reading itself, around 135. Saying that if this is 135, and let's suppose that I go and get another reading, and the second reading that I get is say 130, and the third reading that I get on the day after that is say 132. And I'll say, okay, seems to be fine, I might say. But let's suppose after 135, the guy goes in, I do my usual thing, and I measure it again. And this time, it comes out as 157. And I do it again, and it comes out as 128. And I do it again, it comes out to be 152. So, in both cases 135 was probably a good number, but in one case 135 was varying very little, and in the other cases 135 was varying a lot. Which gives me different ideas as to how to process it. So what descriptive analytics talks about, essentially, is trying to understand certain things about data that helps me get to conclusions of this kind a little more rigorously. Now, to be able to quantify what these plus minuses are is going to take us a little bit of time, and we will not get there this residency. We'll get there next residency. To say that in order to say it's not 135 but 135 plus minus something, that question now needs to be answered. But to do that, I need to have two particular instruments at my disposal. One instrument that I need to have at my disposal is to be able to know what to measure. I need to say, what does an error mean? I need a statement that says that maybe I'm 95% confident that something is happening. I'm 95% sure that this is below 140. I need a way to express it, and that is the language of probability. So, what we will do tomorrow is we'll introduce a little bit of the language of probability. It will be sort of unrelated to what we're doing today, so there's going to be a little bit of a disconnect. But what we're going to do is we're going to create two sets of instruments. One instrument that is purely descriptive in nature, and one set of instruments which is purely mathematical in nature, so that I can put a mathematical statement on top of a description. And the reason I need to do that is because the pure description is not helping me solve the problem that I've set. So therefore, what will happen is, you will see in certain medical tests, you will not see points like this, you will see intervals. Your number should be between this and this. Your cholesterol number, your HDL, whatever, should be between this and this. You won't see a number, you will see a range that typifies a variation. And in certain cases, you will see thresholds, and maybe it's just a lower limit or an upper limit, but you'll also see a recommendation that says, please do this again. In other words, I'm going to compare, I can't compare one number to one number. One number to one number is typically a very bad place for any kind of analyst to be in, because you've got no idea of which is error prone and where the error is. So therefore, what happens is you try to improve one of those numbers. And so either by fiddling around with the range or by getting more measurements. And you'll do that, and you'll see that as we go along a little later. So this is a context for what we have. In terms of data, let's see. So this is a set of files that has been loaded. It's a very standard set of files. It's not mine, to be honest. I just want to make sure that I'm doing what I'm supposed to be doing. So for reasons that are more to do with security, my understanding, the notebook will not access your drives. So keep it on your desktop and not complicate life. So, and there is this notebook. It's called Cardio Goodness of Good. The word statistics refers to the idea that comes from the statistical way of thinking. which, as I said, opposed to the machine learning way of thinking, tends to be a little more problem first, data next, which means we worry about things like hypothesis and populations and sampling and questions like that. And the descriptive part refers to the fact that it is not doing any inference. It is not predicting anything. It's not prescribing anything. It is simply telling you what is there with respect to certain questions that you might possibly ask of it. Now, what is the context to the case? The market research team at a company is assigned the task to identify the profile of the typical customer for each treadmill product offered by the company. The market research team decides to investigate whether there are differences across product lines with respect to customer characteristics. Exactly what you guys were suggesting that I should do with respect to the watch. Understand who does what. Entirely logical. The team decides to collect data on individuals who purchase a treadmill at a particular store during the past 3 months. Like watches, they're now looking at data for treadmills. And that is in the file, in the CSV file. So what you should have is, you should have a CSV file in the same directory, and through the magic of Python you don't have to worry about things like path. Before we get there, remember, because we're looking at this statistically, before we get the data we should have a rough idea as to what we're trying to do. And so they say that here are the kinds of data that we are looking at. The kinds of products, the gender, the age in years, education years, relationship status, annual household income, average number of times a customer plans to use a treadmill each week, average number of a customer expects to run walk each week, on a self-rated fitness scale on 1 to 5, where 1 is in poor shape and 5 is in excellent shape. Some of this is data, some of this is opinion. Right? Some of this is opinion masquerading as data. Like for example, number of times a customer plans to use a treadmill. Right? Hopeful, wishful thinking. It's still data. You're asking someone, how many times will you use it? Her rows, daily, no problem, 7 times a week. Oh, we'll see. But it's still data. It's come from somewhere. So what has happened, the way to think about this is to say that I want to understand a certain something. And the certain something has to do with the characteristics of customer characteristics. And to do this, you can then use you can either take, let's say, a marketing point of view, who buys. You can also take a product engineering kind of view, what sells, in other words, what kind of product should I make, etc. In business, as you probably know, for those of you aren't, any of you entrepreneurs? One hand up. One hand up. They're closet entrepreneurs from what I could figure out. Right. Sometimes it's unclear what that word means. In other words, you think you are, or you're not confident enough to call yourself one, or you're doing that. In IT space, if you're an entrepreneur, for example, in physical product space or even in software space, one of the things you often think about is what's called the product market fit, which is you're making something. How do you match between what you can make and what people will buy? Because if you make something that people do not buy, that doesn't make any sense. On the other hand, if you identify what people buy and you can't make it, that also doesn't make too much sense. So the conclusions that we will draw on this, we will not draw on today. But the purpose is to be able to go towards the conclusions of that kind. Either isolate products, isolate customers, and try and figure out what they tell us. Pandas generally has a fair amount of statistics built into it. That's what it was originally built for. NumPy is something that was built more for mathematical problems than anything else. So some of the mathematical algorithms that are needed are there. There are other StatSci plots in Matplotlib or Seaborn and many other things that you've seen already. Python is still figuring out how to arrange these libraries well enough. Shall we say, the programming bias sometimes shows through in the libraries. So I, for one, do not remotely know this well enough to know what to import up front. But a good session, you know what to import up front and you do all this up front. So you don't get stuck with what you want to do. The naming is up to you. If you like the names as they are, then that's fine. If you want a standard set of names. So when you wrote the data set, if this is in the right path, just this will work. .csv. It's usually smart enough to convert Excel forms into CSV. In other words, if you have this as XLS and things like that, it's usually smart enough, but if it isn't, then just go in and save an XLS file as a CSV file and operate that way, in case it doesn't do it on its own. But more often than not, what you see is that when Jupyter sees it, it will see any XLS file as a CSV file, or go and make the change yourself. Or you can have other XLS, other restatements in it as well. You can change functions inside it and you can figure out how much to head. What this tells you is there's the head and the tail of the data. This is simply to give you a visualization of what the data is. This gives a sense of what variables are available to it, what kinds of variables they are. We'll see a little bit of a summary after this, etc. So for example, some of these are numbers. Income. What is income? Income is annual household income. That's a number. Some, for example, let's say gender, male, female, this is a categorical variable. This is not entered as a number. It's entered as a text field. If you are in Excel, for example, right at the top, if you go in and you see that, it will tell you how many distinct entries there are, how many distinct settings there are. So usually what happens right at the beginning, and a data frame like this, if it is created, this is a data frame. If a data frame is created, when it gets created, the software knows as to whether it is talking about a number or whether it is talking about categories. There are certain challenges to that. You can see one particular challenge to this. What does this 180 mean? Counts. Why do you think there are so many decimal places that comes here? 14 years of experience, 16 years of experience. Why is it going 0, 0, 0, 0, 0, 0?
No, that's because mean, median,
By default,
Yes, it does this because it sees other numbers where those decimal places are needed. So what it does is, what any software typically does is, when it sees data, it sort of says that at what granularity do I need to store the data. Sometimes this is driven by your computer, your 64-bit, your 32-bit and things like that. But what it does is, it means that the data is stored in the data frame to certain digits. Now, usually you don't see that, you'll see it in this way. But sometimes, for example, when you say include equal to or and you ask for a full description, the data comes out in this slightly irritating way. Because of something here, because of, let's say, the income field or any of that. Now, when it looks at the descriptions of this, what is the description that it is reporting and how does it choose to report out the description? So in this particular situation, so let's take a little bit of a closer look at this. One thing here, look at the way it's done here. So count, unique, top, frequency, and then there are certain things here, mean, standard deviation, minimum, 25%, 50%, 75% and max. When it sees a variable like gender, it reports out lots and lots of NANs. What does that tell you right off the bat? It can't do that, which means it's not a number. This is not a number. In other words, if you ask me to find the mean of something and you're giving me male and female as inputs, I don't know what to do. Which is an entirely reasonable stand to take for any reasonable algorithm, right? It requires another kind of description for it to work. But the problem with describe this syntax is that it's asking for the same description for all of them, whether it's in significant digits, whether it's in columns, etc., etc. So it's chosen this description and it says that that's all that I'm going to give you. But where it makes sense, let's say for example I look at age. Now for age I've got 180 observations and it is calculating certain descriptions for it. Correct? So what are the descriptions it is calculating? Let's look at these. It's calculating a description like, say, minimum. Minimum is what? 18. Maximum is 50. These are easy to understand. Then let's look at something a little interesting. Suppose I want to report one number, one representative age for this data set. This is like asking the question, how do I get a representative blood sugar number for you? I can give you a minimum and a maximum, but to do the minimum and the maximum, I need to draw blood many times from you. But let's suppose I want one representative age for you. Somebody asks you, what is your blood sugar? You want to give them one number. Similarly, somebody is looking at this data and asks the question, give me a representative age. How old is your typical user, or what age do you want to build it for? Or you're even asking, let's say, a product question. You're a product designer, and a product designer building a treadmill. Now, how do you design a product? Those of you who are engineers, based on the weight. Now, very good. What weight? Whose weight? Who's the user? What is the weight of the user? He's got a good point. As a design engineer, I need to know what weight will be on that treadmill. Now, what is the answer to that question? Max?
Users who visit the gym.
So there's a question of saying that if I want to measure a variable by one number, how should I even frame that question? What makes sense? What is a one average? No? Max? In this particular case, you might argue the max is the right number, because I want to be able to say, if I can support him, I can support anyone. But there's also a downside to that. I've now engineered that product. You could argue that I have, shall I say, over-engineered that product. Correct?
Factor of safety.
I'm sorry?
Factor of safety.
A factor of safety? Okay. Alright. So let's suppose that you are doing this for a mattress. You all sleep on mattresses. We're all relatively wealthy based on the fact that we're here. So we probably sleep on a mattress. Not everyone's fortunate enough to sleep on a mattress, but let's suppose you do sleep on a mattress. How much weight should that mattress be designed to bear? If you over-engineer it, what will happen is that number one, for a reasonable weight, let's say weight a lot below that, that mattress is not going to sink. Let's say that you design it for 100 kilos. Now if you're 50 kilos or 60 kilos, that mattress is not going to sink for you. Because it's going to feel comfortable for someone who is 100 kilos. And for someone who's 50 kilos, you're just going to bounce on it. You're not going to feel its soft silkiness or whatever it is you want to feel from the mattress. It won't work. So what to do? So that's a hard problem. It's a description, but it's a hard problem. Who do I engineer it for? And so therefore, people have different ranges of what I mean to represent it. So here's one version of it. This is what is called a 5-point summary. I report out the minimum, the 25% point, the 50% point, the 75% point, and the maximum. Variable by variable, I report 5 numbers. I report the lowest. What does 25% mean? 25% of my data set or the people are younger than 24. The youngest is 18. 25% or a quarter of them are between 18 and 24. A quarter are between 24 and 26. A quarter are between 26 and 33. And a quarter are between 33 and 50. This is what is known as a distribution. This is what is known as a distribution. The statisticians love distributions. They capture the variability in the data and they do all kinds of things with it. So I'm going to draw a typical shape of a distribution. We'll make more sense of it later on. This is a theoretical distribution. A distribution, for example, let's say has a minimum, has a maximum, has say a 25% point, has a 50% point, it has a 75% point. In terms of probabilities, there's 25% here, 25% here, 25% here, 25% here. If you want to think in terms of pure description, this is not a probability, it's just a proportion. If you want to think in terms of probabilities, what this means is that out of 180 people, if I draw one person at random, there's a 25% chance that that person's weight is going to be below 24. Sorry, age 24, correct. If you want to think in terms of probabilities, we'll do that tomorrow. But this is a description. So what this description does is it gives you an idea as to what value to use in which situation. So for example, you could say that I'm going to use 26 as my representative age. If I do that, what is the logic I'm using? This 25%, this 50% point, so to speak, this is called the median. This is called the median, and we'll see it. Median means the age of the average person. First sort, take the middle person and ask, how old are you? The age of the average person. I could also ask for the average age of the person. Which is what? Which is the mean. Which is 1 over n x1 plus xn. Now this is algebra. What you have to do is you have to put n equal to 180. This is the first age, the second age, the third age up to 180. 1 by 180, age 1 plus age 180. This is called the mean. This value is what? 28.79. The average age is about 28 years or 28 and a half years, 28.8 years. But the age of the average person is 26. Yes?
So could you please repeat the median and the mean?
The difference between the two?
You described what is the age of the person.
So I described the median as the age of the average person. And I described the mean as the average age of a person. Now he's looking at me like saying, you have to be kidding me, right? That's confusing. I admit to it. The easy way to understand it could be this. What is the mean? Add them all up, divide by how many there are. What is the median? Sort them from the smallest to the largest, pick off the middle. If they're an even number, what do? You take the average of the two middle ones. If they're the same, it'll be the same number. If they're not, it'll be a number between them. So sometimes the median may show up with a 0.5 or something like that for that reason. If there is an integer counts, but there are an even number of counts. Now, which do you think is better? You're giving the right answer. It depends. You'll figure out that I like that answer. They both make sense. They both make sense. It depends on what context you're going to use it for. In certain cases, yes.
You said that median is basically the mean of the.
It's the age of the average person. It's a reading from the average person.
So what is the parameter we are saying it is the average person? How we are getting that average?
Okay. So if you're talking in terms of parameters, so he used an interesting term. He's saying, what is the parameter I'm after? Parameter is an interesting word. Parameter refers to something what generally in a population, it's an unknown thing. that I'm trying to get after. For example, blood sugar is a parameter. It exists, but I don't know it. I'm trying to get my handle on it. Correct? So if I'm thinking in terms of parameters, then these are different parameters. So let's look at a distribution here. I'm not sure whether this will pick up things. I hope so. So the median is a parameter such that on this side I have 50% and on this side I have 50%. This is the median. The mean is what is called the first moment. What that means is, think of this as a plate of metal and I want to balance it on something. Where do I put my finger so that it balances? It is the CG of the data, the center of gravity of the data. You can understand the difference between these two now. If, for example, I push the data out to the right, what happens to the median? Nothing happens to the median because the 50-50 split remains the same. But if I push the data out to the right, the mean will change. It will move to the right. Your lever, the lever principle, right? If there's more weight on one side, I have to move my finger in order to counterbalance that weight. So these are two different parameters. If the distribution, for example, is what is called symmetric, symmetric means it looks the same on the left as on the right, then these two will equal. Because the idea of going half to the left and half to the right will be the same as the idea of where do I balance, because the left is equal to the right. So when the mean is not equal to the median, that's a signal that the left is not equal to the right. And when the mean is a little more than the median, it says that there is some data that has been pushed to the right. And that should be something that you can guess here, because the mean and the median to some extent are what? 24, 26, etc. The lowest is 18. That's about 6 years, 8 years less than that. But what is the maximum? 50. That's 25 years beyond. The data is pushed to the right a little bit. Instead of saying pushed to the right technical term is right skewed. There are, shall I say, people are more not average on the older side than on the younger side. There was a hand up somewhere. Yes.
I was just confused with the statement that median would not move, but then you explained it.
Yes. So therefore, one reason that the median often doesn't move is because it is not that sensitive to outliers. So let's suppose, for example, we look at us and we ask ourselves, what is our mean income or our median income? And we have that. Each of us make a certain amount of money, we can sort that up and put that in. Now let's suppose that Mr. Mukesh Ambani walks into the room. Now what is going to happen to these numbers? Mean is going to go up, right? He alone probably makes a very large multiple of all our incomes put together. Possibly. I don't know how much you make. I know how much I make. But what's going to happen to the median? It's going to stay almost the same. The typical person may move by at most half. Because what is the typical person going to be? The typical person is going to be an actual individual in the room, or maybe an average of 2 individuals in the room. And that person is not going to change. Yes. Yes. That's one conclusion we can draw on this. There are other plots below which will also show the same thing. You're not being able to draw that conclusion. Well, good logical reason. I haven't shown you the full data. We'll see the histogram and we'll do that. So hold on to that question. The conclusion was drawn is that there are two things to do. See here. One is, if I simply look at this without seeing any more graphics, where is the middle of the data from a median perspective? At 26? Correct? Now from 26, look at the difference between 26 and the smallest. 18. Between 18 and 26, that's 8 years. This 8 years contains 90 observations because there's 180 total. Now, what is on the opposite side of this? 26 to 50. That's how many years?
24
years. This 24 years now contains how many observations? Same 90. So there are 90 observations that are between 18 and 26. And there are 90 observations between 26 and 50. So if I were to draw a picture, what would that picture look like? Yes, exactly as you're drawing it, right?
It means what we can say is skewed on the left hand side or right?
This usually by definition is called right skewed. This is a problem that BABI has. Does this mean it's left skewed or right skewed? As a word, right, it's called right skewed. More data to the right. Sorry, more data is a dangerous word. No, it's the same number of observations. I'll say the data is pushed to the right.
More variation on the right side.
More variation on the right side is probably a safer way of putting it, yes. So skewness is often measured in various things. One measure of skewness is typically, for example, mean minus median. Mean minus median, if it is positive, it usually corresponds to right skewness. Mean minus median negative usually corresponds to left skewness. This is a statistical rule, but sometimes it is used as a definition for skewness. There are many definitions for skewness. Skewed data sometimes causes difficulties in analysis because what happens is the idea of variation changes. Being variation on one side means something a little different than variation from the other side. By the way, what's happening to you with respect to things like books? Are you getting books? Are you not getting books? I have no idea what the books are. You got one book, which is what? Which is the statistics book? Okay, I'll take a look at that book later. So, this book, right? Okay, show me the book. Okay. Comment 1, very nice book. Comment 2, not a Python book. Right? That doesn't make it a bad book. So, if you're looking for help on how to code things up, this is not the right book. Get a book like Think Stats or something like that. But, if you want to understand the statistics side to it, it's an excellent book. So everything that I'm talking about is going to be here. I might talk about which chapters and things like that at some point. And I might talk about how to use this in the book. So for example, at the back of this book, there are tables. There are tables at the back of this book, which we'll learn how to use. And then I'll try to convince you that you shouldn't use them. But remember, many of these methods are done in ways in which either you don't have access to computers, or if you do have access to computers, you don't have them, shall we say, at runtime. In other words, when I want to run the application on it, I can build a model using a computer, but I can't run it within one. The runtime environment for statistics is often done when there are no computers around. The build environment can include computers, but the runtime environment cannot. A lot of statistics is done under that kind of situation.
Even probability is also covered here?
Yes, very much so. Very much so. Okay, so definitions of skewness and things like that. Do it in the way you usually use a book, which means you go to the index and see if the word is there. And then you go back and figure it out, and it will give you some ideas as to how that works. It's a nice book. It's one of the best books that you have in business statistics, but it's not necessarily a book that will tell you how to code things up. That is not a deficiency of the book. Not every book can do things of that sort. There are other books around that will tell you how to code things up, but will not explain what you are doing. It's important to know what you are doing. It's also important to know why you're doing it. But books can't be written with often everything in mind. Yes?
Can you suggest some book which tell us how we can think that way?
The thinking is here. I think this is good for thinking. I would absolutely recommend this book on the thinking side.
Because the problem lies that in which situation what we need to apply.
Yes. And that answer I think is very, very good here. Where you won't get is it will say do this, and it won't give you the Python syntax to do it. That will not be here. So if you can solve that problem through some other means. I used to have a colleague in corporate life who had a very big sticker on his board. It said, Google search is not research. Right? Now nobody agrees with him anymore. So I suppose that when in doubt, you do what normal Homo sapiens do today, which is you Google for an answer. So one possibility is that you understand something from a book such as this, and if you want to understand the syntax, just Google for the term. Say Python, that term, whatever, it will probably give you the code. Things are very well organized these days. There's also the question, and I should give you a very slight warning here, not to discourage you from anything. But in the next 9 months or thereabouts, the duration of your program, there's going to be a fair amount of material that will be thrown at you. Correct? The look and feel will sometimes be like what we would often call at MIT as drinking from a fire hose. You can if you want to, but you will get very wet. So therefore, pick your battle. If you want to understand the statistics side of it, please go into the depth of it. But if you try to get into equal depth on every topic that you want to learn, that will take up a lot of your professional time. Now the reason we do the statistics part first, one, it's a little easier from a computational perspective, although harder from a conceptual perspective. So we begin it this way. But hold on to that idea, and then as you keep going, see if this is something that you want to learn more on. And if you can, you're welcome. Just write to us or let us know, or let anyone know. Oida's just come in, let her know, and we'll get the references to you. But if you want to, say for the first 2 residencies, please read the book and see what happens. If there are doubts, yes, but it's a well-written book. Its instructor is one of our colleagues here. If you want, we can also help explain things. So this is the summary. What did the summary tell you? This summary gave you what's called the 5 numbers that help you describe the data. Minimum, 25, 50, 75, max. We'll see another graphical description of this. It also described for you a mean. There is also another number here, and this number is indicated by the letters STD. STD refers to standard deviation. STD refers to standard deviation. And what is the formula for a standard deviation? STD is equal to the square root of little bit of a mess, but 2 steps. Step 1, calculate the average. Step 2, take the distance from the average for every observation. Ask the question, how far is every data point from the middle? If it is very far from the middle, say that the deviation is more. If it is not far from the middle, say that the deviation is less. Deviation being used as a synonym for variation. I'm talking about variation. Variation can be more or variation can be less. More than the average, less than the average. If someone is much older than average, there's variation. If someone is much younger than average, there is variation. So therefore, both of these are variation. So what I do is, when I take the difference from the average, I square it. So more than x bar becomes positive, less than x bar also becomes positive. Then I add it up and I average it. There's a small question as to why it is n minus 1, and that is because I'm taking a difference from an observation that is already taken from the data. Now I have squared. When I have squared, my original unit was in age. When I have squared, this has become age squared. So I take the square root in order to get my measure back into the scale of years. So the standard deviation is a measure of how spread a typical observation is from the average. It is a standard deviation, where a deviation is how far from the average you are. And because of this squaring, you need to work with a square root. In sort of modern machine learning, people sometimes use something called a mean absolute deviation, MAD, very optimistically called. So what MAD is you don't take a square, you take an absolute value. And then you do not have a square root outside it. And that is sometimes used as a measure of how much variability there is.
So why it is squared then?
Why is it?
Why we do it just
We square it because we want to look at both positive and negative deviations. If I didn't square it, what would happen is it would cancel out. What was the word that one of you used? Neutralize, right? I love that term. Your positive deviations would neutralize your negative deviations.
So I went to this x minus x bar is there.
Yes.
So it should be like x square minus x square. And if you are seeing the positive and the negative.
This number is going to be positive if say x1. So let's look at the first number here. So if I look at the head command here, when I did the head command here, what did the head command give me? The first few observations. So now this is an 18-year-old. This is probably sorted by age. This is an 18-year-old, correct? Now I'm trying to explain the variability of this data with respect to this 18-year-old. Why is there variation? This 18 number is not the same as 28. And 18 is less than 28. So what I want to do is I want to go 18 minus 28.7. What I'm interested in is this 10. This 10-year difference between the two. Now the oldest person in this data set is how old? 50. When I get to that row, this 50 will also differ from this 28 by 22 years. So I'm interested in that 10 and I'm interested in the 22. I'm not interested in a minus 10 or a minus 22. I can do that. I can do that. In other words, what I can do is I can represent 18 minus 28 as 10 and I can represent 28 minus 50 as 22. And that is this. As I said, 1 over n minus 1 absolute x1 minus x bar plus absolute xn minus x bar. That is this with n minus 1. And this is done, as I'm saying. This is what is called mean absolute deviation. And many machine learning algorithms use this. You are correct. In today's world, this is simpler. Now, when standard deviations came up first, this was actually a little harder. But people did argue about this. I think, well, 150, maybe more about, I forget my history that much. There were two famous mathematicians, one named Gauss and one named Laplace, who argued as to whether to use this or whether to use this. Laplace said you should use this, and Gauss said you should use. Now the reason Gauss won was simply because Gauss found it easier to do calculations. Why is this easier to calculate with? Because Newton had come up with calculus a century or so before that. And so, for example, let's suppose that you want to minimize variability, which is something that we often need to do in analytics. Which means you need to minimize things with standard deviation, which means you need to differentiate. This function, the square function is differentiable, you can minimize it using calculus. This is not. So therefore what happened was, Gauss could do calculations, but Laplace could not, and Laplace lost. And Gauss won the definition of the standard deviation.
We haven't much used 25% or 75, so
okay. Why do we not do that? So, today, this entire argument makes no sense. Because today, how do we minimize anything? Our computer program. You don't use any calculus. You run fmin or something of that sort, you basically run a program to do it. So therefore this argument you can both do calculations equally well with this as in that. So today what is happening is that Laplace's way of thinking is being used more and more. This one is a lot less sensitive to outliers. This one, what it does is, if it is far away, the 22 squares to 484 or something like that, which is a large number. So the standard deviation is often driven by very large deviances. Larger the deviance, the more it blows up. And so therefore this is often very criticized. If you read, for example, the finance literature, there's a guy called Taleb, Nassim Taleb, he writes this book called The Black Swan and Fooled by Randomness, where he left and right criticized the standard deviation as a measure of anything. So Today, this argument doesn't make a great deal of sense, and when in practice something like this makes sense, it's often used. So, a lot of this is done historically. It looks this way because of a certain historical definition, and then it's hard to change. So today, in centuries after Gauss, sad people like me are trying to explain it and having trouble doing it because there's a logic to it, right? I mean, and that logic doesn't hold at all anymore now. Yes.
Standard deviation in simple terms is that 18. How far generally is that from the median?
How far on the average is an observation from the average? Confusing statement again. He's again going to go unhappy. But how far on the average is an observation from the average? If that answer is 0, that means everything is at the average. But you're asking the question, how far from the average is an observation on the average? If I take your blood pressure, how far from your average blood pressure is this reading? If this is exactly equal, then I don't need to worry about variability. Every time I measure blood pressure, I'll see the same thing. What is your average bank balance? Don't tell me that, but you know what I mean, right? You have an average bank balance. Your bank account manager or your bank actually tracks this, what your average bank balance is. But you're not actually, your balance is almost never or very, very rarely equal to your actual average bank balance. It's more and it's less. How much more, how much less is something that the bank is also interested in order to try and figure out, how much of your money, so to speak, to get out there. Because the bank is going to make money by lending it out, correct? But when it lends it out, it can't give it to you. So it makes an assessment as to how much money, I don't want to get into finance now, but you get the drift. So therefore, it is a measure of that. It is not the only measure of that. So for example, here's another measure. So you remember this 25 number and the 75 number that you're asking about? Let's say that I calculate a number that looks like this. Let's say 33 minus, let's say 33 is a 75% point, minus 24. So 33 minus 24, let's say this is my 24 and this is my 33. Between this, how much data lies? 50%. Why? Because this is 25% and this is 25%. This now contains 50%. This is sometimes called the interquartile range. Interquartile range. Big word. Right? Now, why is it called an interquartile range? The reason is because sometimes this is called Q3 and this is called Q1. Q3 stands for upper quartile. You can understand quartile, quarter. So upper quarter, and this is the lower quartile. And the difference between the upper quartile and the lower quartile is sometimes called the interquartile. Why is it called the range? Because what is the actual range of the data? The range of the data in this particular case is 50 minus 18. And 50 minus 18, which is your max minus your min, this is sometimes simply called the range. Range is maximum minus minimum. Interquartile range is upper quartile minus lower quartile. And these measures are used. They do see certain uses based on certain applications. You can see certain advantages to this. For example, let's suppose that I calculate my 5-point summary. With my 5-point summary, I can now give you a measure of location, which is my median, and I can give you 2 measures of dispersion, which is my interquartile range and my range. So those 5 numbers have now been twisted to give me a summary number, which is the median, and a range number. Interestingly, I can also draw mental conclusions from that. For example, I can draw conclusions from these 5 numbers in the following way. 24 and 33 half my customers are between 22 and 24 and 33. So if I want to deal with half my customers, I need to be able to deal with a range of about 9 years. Within this 9 years is all that I'm interested to get this right. So if I'm building my machine, I'm going to make sure, let's say, that the 33-year-old is okay with this and the 24-year-old is okay with this. Will the 50-year-old be okay with this? Yeah, may not be. But if I want to make the 50-year-old okay with this, I'll have trouble with the 18-year-old. So I can do a lot with even these 5 numbers. We'll see more descriptive statistics as we go along. By the way, this is only for age. I can do this for usage, I can do this for fitness, I can do this for income, I can do this for miles. Income is interesting. Here's the median income, $50,000, and the mean income about $53,000. If you see income, in almost all real cases, the mean income is going to be more than the median income. The per capita income of India is more than the income of the typical Indian. Say, what does this command do? If I say mydata.info, what this is doing is, my data first of all is a data frame that I created. Just to review, I read the PDF file this way. Now this is a describe, and this here is info. Now describe and info in the English language are similar things, description and information. This is interpreted in the software as two completely different things. Information is like your variable setting. It's like your integer field, your real field is setting like that. It's giving you information on the data as data. The word data means different things to different people. To a statistician, data means what? To a statistician, data means a number. To an IT professional, what does data mean? Bytes, information. I've lost my data. I don't particularly care what the data is. I've lost my data. So this is that information. It tells you about the data. It's an object. This is description. It's a 64-bit stored integer. It's an object. So it tells you about numeric, categorical. It tells you about the kind of data that's available. Non-null fields. In other words, there are objects in the field, etc. There are so many integer types which are stored at 64 because this computer is probably capable at 64. And there are 3 categorical variables. This is, shall we say, a data object summary of what is there in that data frame, not a statistical summary. Useful in its own way, particularly if you are processing it and storing it. For those of you who are going to go into data sort of curation-like careers, this kind of a database is a nightmare. Because typically what happens is, when you store real data, in addition to data, you often store what's called a data dictionary. Sometimes that's referred to as metadata, data about the data. Because simply storing a bunch of numbers is not enough. You have to say what the numbers are about. This adds a layer of complexity to the metadata. You now have to store not only what the variable is about, but what kind of a variable it is. So many professional organizations say is that archival data should never be a mixture of both numerical and categorical objects. And they pay a price for that. Numerical things should become categorical or categorical things become numerical. But what happens is, if you are storing large volumes of it and archiving it and making it available for people who have not seen it before, it sometimes gets convenient. So therefore, fields like this are often useful to see how big a problem you have. Right? Now I want to plot a few things. To plot, you can plot anything. Seaborn, I think, is coming a little later. But this plot, this is from Matplot library, and it is plotting through a command called hist. Hist means histogram, which you've already seen. You've covered histograms, right? I think you've seen histograms. So this is a histogram. Now histogram as a syntax has bin sizes and figure sizes. So what you can do is you can play around with these and see the differences in what this histogram does. But there's a certain default that shows up, and that default is quite good. And here is a histogram distribution of the age. This is not a set of numbers, this is a picture. This is a picture. What does this picture have? This picture has a set of bins and it has a set of counts within each bins. Between these two numbers, between say 10 and whatever this is, let's say 22 or thereabouts, I have a count of, let's say 17. So it gives a count, and it does this by getting a sense of how many bins there are and plotting this shape. It's a little bit of an art to write a histogram program. There's a Python book out there, I think ThinkStat one of it, in which sort of the first 1/3 of the book is basically how to write a histogram code. It's a wonderful book, but because it treats this example, it got terrible reviews. Reviewers said, why do I want to learn how to code a histogram? And the book's author is, I'm teaching you how to write a code. A histogram is an example of how to do that. And I tend to agree. If you want to test yourself of your understanding of data and your understanding of any programming language and any visualization language, code a histogram in it. And have fun. So it's a nice challenge from many perspectives. The data challenge, the language challenge, the visualization challenge, all of that. Yes?
So you said archival data should not be numerical plus category.
Many companies do that. That they want archival data to be of only one data form, only one format. Why is that so? Because, as I said, when you store data, how do you store it? Let's say that you've generated an analysis. The analysis is done, correct? And you've decided not to destroy the data. You're going to keep the data in your company's databases or in your own database. How will you keep it? You can take a technology. Let's pick an example. Let's say pick an example. SQL, Excel, whatever. Let's say Excel. Let's say I keep it in Excel. Now, if I keep it in Excel, what will I now do? So let's say I have an Excel spreadsheet. Let's say my cardio data set. Let's say this data set. Now, in addition to the data, what do I need to store with it?
Metadata.
Yes, metadata. How do I store that metadata? Yes, so one possibility is I can have a text file like that, like I had at the top of this, describing all of this, which is typically what happens in Excel storage. It describes this and it describes, there's one file called .dat and another file called .disc or something of that sort, which basically describes the variables, and the idea is that they have the same name, and one extension gives you the data, the other extension gives you the description of the variables that are in this data. Correct? Now this is good. Now what's going to happen? On that data, certain code has been run. That code is going to assume certain things about the data. What do you want that code to assume about that data? Whatever you want that code to assume about that data should be available in the data dictionary. Now, if that code is stable enough to realize that whatever fields you give me, I will run on, that's cool. But if that code requires you to know what kind of data is being used, let's say discrete data, let's say continuous data, in the future you'll be doing things like linear regression, logistic regression. Linear regression will make sense if the variable is a number. Logistic regression will make sense if the variable is a 0 or a 1. If you have that problem, now in the metadata you need to be able to tell not only what business information this variable contains, but also what kind of a computational object it is, so the code can run. So therefore what people often say is that I'm going to make it very simple and I'm going to assume that my entire data frame consists of only one kind of variable, so that when I run any algorithm on it, I know exactly what kind of data input that algorithm is going to get. But I'm saying it's a practical answer that many companies often have. And I've worked in a couple of companies, at least one company where this was very seriously done. So we had to, when we put data back in, we had to convert it. And in the situation that I was in, it wanted everything in categories. So what we would do is we'd take continuous data and we would do what's called fine classing, which means that we would divide not into 4 pieces but into 10 pieces. Decile 1, decile 2, decile 3, decile 4 up to decile 1. And every variable was stored now not in its original numbers but as 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So let's suppose that I tell his income is 9. What that means is I know he's in the 9th decile. 10% of the people or more have income more than him 80% have less than him. He's in that bracket. And all variables were stored that way. Now what happens is every algorithm knows that every variable is going to be stored that way. And you can keep writing algorithms that way. Otherwise, what would have to happen is every algorithm would need to be differently. And let's say you're doing credit scoring. Let's say you're doing CRM models. You're doing something of this sort. And you've built a very sophisticated CRM model that tracks your customers. And it works. Now suddenly you've got a new variable coming in, the Twitter feed. And suddenly nothing works. What to do? Go back and rebuild that entire model. That's going to set you back 3-4 months. That's going to set you back a few $1,000s. So you say, no, any variable that has to go in in this form. And if it goes into this form, my algorithm can deal with it.
So, well, in such case, it might not affect the efficiency of the model that we generate?
Yes, yes. And in practice, I'm going far away from topic now. In practice, a professional analyst has to struggle between doing the right thing badly and the wrong thing well. You want to do the right thing well. But the right thing well is going to cost you time, money, data, and everything. So you struggle between saying that I'm going to get a flawed model quickly built on a new data set, or I'm going to get an inefficient answer on a model that's already been built. And let's see how far it goes. And so these are more cultural issues with how an analytical solution is often deployed in companies. They vary very much from industry to industry. They vary very much from company to company, from the culture of a company to a culture of a company. They depend on regulatory environments. In certain environments, an auditor-like entity comes in and insists on seeing your data. Show me your data. Let's say in finance, this is sometimes happening. Regulatory agency, let's say Reserve Bank of India, goes into a bank and says, show me your data. All this NPAs, etc. Show me your order book, show me your loan book. Correct? And now that has to be done, and the decisions you made have to be done in a way that is patently clear why you have done this. So very often people say, I don't want to make the best risk decision. I want to make the most obvious risk decision. Which may not be the same thing at all. But I'm being audited. So that's a practical question, and I don't have a clean answer to that, but I do know what happens. Is it right? No, it's not. But we live in a world that has that kind of imperfection. One of my teachers, his name was Jerry Friedman. You'll see some of his work later on. He came up with algorithms like projection pursuit, CART, Mars, gradient boosting. He created many of the algorithms that you will be studying. One of my teachers at Stanford. When he ran our consulting classes, he would say this: solve the problem assuming you had an infinitely smart client and an infinitely fast computer. After you've done that, solve the real problem, where you do not have an infinitely smart client and you do not have an infinitely fast computer. This was in the early 1990s, where computer speeds were a lot slower. And we didn't have powerful machines like this around. So a lot of this is done in that kind of situation, where you are struggling for continuity, when you're figuring it out. Imagine yourself as an analytics manager, and I hope many of you will be. And you have an analytics team sitting in front of you. Correct? You're looking at them and you're looking at them in the eye, and you know how much you're paying them. And you know that half of them are going to leave at the end of the year. What are you going to do with regard to the modeling and things like that? Your first order of business is going to be to ensure continuity in some form. Keep it simple, right? Keep it simple. Keep it obvious for the next bunch of people who are going to come in. And for that, you'd be willing to trade a little bit of make it right. So now the new person coming in will now not want to solve a very complicated kind of situation. This is not where you want to be, and I do not want to depress you on day one. But it's also the fun part of the profession, right? It's also what makes it interesting and exciting. Right? It's not all bad. Okay, so the histogram command summaries of what these histograms are, and each gives you a sense of what the distribution is. And as you can see from most of these pictures, most of these variables, when they do have a skew, tend to have a right skew. Maybe education has a little bit of a left skew. Maybe education has a little bit of a left skew, that a few people are educated and most people are here, but even so. Right? Now here's an interesting plot. Matplotlib has this as well, but Seaborn has a better version of it. This is what's called a box plot. You've seen a box plot? This is a box plot. People are unsure as to where this box came from, because there's a statistician called Box who's used this before, but this box came from, it used to be called a box and whisker plot. These are the whiskers. This whisker will go, this is the median, this is the upper quartile, the top edge of the box, the bottom edge of the box is the lower quartile, the end of the whisker is 1.5 times the interquartile range above the box. Right? If you want a formula, sort of the whisker, the length of the whisker is 1.5 times IQR. Should I have a break now? A little bit maybe, huh? So we'll, okay, 3:45 or whatever, we'll go up to there. Yeah, I haven't stopped, I just got distracted. So 1.5 times the, so it goes up to that. If a point lies outside it, the point is shown outside it. If the data ends before it, the whisker also ends. Correct? What is the whisker? Okay, what is the whisker? Alright, let me explain another way. The whisker is the maximum, the top of the whisker is the maximum, the bottom of the whisker is the minimum. Okay? Not okay. Okay. Some of the points are outside. So, this point here, now what is this plot here? Age for males. So what this means is, this is the minimum, 18 or whatever it is, and this is the maximum, 48 or whatever it is. Minimum and the maximum. So if you see nothing else on the box plot, no other points other than just the box and the whisker, then your 5-point summary is sitting there. That's it. Right. Now, what happens if you see points like this? Outliers. What is an outlier? An outlier is a point that lies more than 1.5 times the interquartile range above the box. So this whisker will not extend indefinitely. It will go up to 1.5 times this box, and then it will stop. And if any points are still left outside it, it will show them as dots. You can treat this as a definition for what an outlier is. Same thing. Same thing in the other direction. The logic is symmetric.
1.5 times from the
No. That means this it hasn't. The data is ended here. The data is ended here.
Was there any other number tried instead of 1.5?
I suppose so, and you can change it. You can. I won't try it now, but you can go to the box plot syntax and change that. So you can go to box plot syntax and you can change that 1.5. It's not hard coded into the algorithm. I think 95% sure. As a statistician, I'm never sure about anything. But it's a parameter in the you should be able to pass the parameter in the box plot function. Default is 1.5. You should be able to change it.
And what's the color part? That's the median, is it?
Which one?
The color.
Color? Oh no, these two colors? These two colors are because I've asked for two things. I've asked for male and female. If I had 3 of them,
That's okay, but how the range of color? The box.
Oh, this one here. Oh, this is Q3. The lower is Q3 and the upper is lower is Q1 and the upper is Q3.
So this is the quartile range.
Quartile range. So for males, between the bottom whisker to the end of the box is a quarter of your data. The box is half your data, and the top of the box to the end of the whisker is quarter of your data.
So the middle line is
the middle line is the median. The middle line is the median. There is also a function in box plot you can play with where it will give you a dot, and that dot is the mean. I mean, you can ask box plot to do that, but a mean is not a general standard component in the 5-point summary. It's a different calculation, not a sort. But if you want to, you can make box plot to give a dot on the mean as well, by definition. Yes. So mean median. So half the data is between 24 and 34 or whatever that is. Half of all the men in my sample are between those two numbers. I think box plot doesn't allow you to change the shape of the box. I think that is set. That's sort of central to the idea of a box plot. It does allow you to fiddle with the size of the whisker, but I don't think it allows you to fiddle with the size of a box. In other words, if you change that to something else, let's say the 20% point to the 80% point, 80-20 rule, that's no longer a box plot. It's another interesting plot. The significance of it is exactly this, as we had seen before. The significance of it is that the data looks like this. It's right skewed. Think of the picture. So if this is your Q1 and this is your Q3, this is your Q2 or the median, then the median is going to be closer to Q1 than it is to Q3. In the same way that the minimum will be closer to the median than the maximum, same idea. This is a summarization for numbers. If you want to summarize for categorical data, what's called a cross tab or a cross tabulation, this is simply how many products are there. Product category 195, 498 and 798. They've got three kinds of treadmills and they're trying to understand who was using what kind of treadmill. Our business problem is to understand who was using what products. This is a cross tab. What is this? This is something that will be used for categorical variables. No box plot will make sense here. There are no numbers. So now you can ask interesting questions here if you want to, and you can think about how to answer it. Is that, for example, you can ask a question, is there a difference between the preferences of men and women? Possibly. Is there a difference in the products that irrespective of gender, is there a product that they prefer? You can ask all kinds of interesting questions and you can find ways to answer it, which we will do, not in this residency, but next time around.
For those we can categorize it also?
Categorize?
For those preferences?
So this is simply, once again, this is descriptive. All this has done is it has simply told you the data as it is. What I'm saying is that if you want to do a little more analysis on it, you now have to reach a conclusion based on it. So for example, one conclusion to ask is that do men and women have the same preferences when it comes to the fitness product they use? Now that's a question. To answer that question, it's enough to look at the data. But just looking at it will not give me the answer. I need to be able to find a statistic to figure that out. A statistic that does what? That in some way measures that difference. Let's say measures the difference between men and women, or what we will do is not measure that. What we'll do is we'll measure that if there was no difference between men and women, what should this table have looked like? And then we'll compare the difference between these counts and that table. But that's the interesting part of a statistical statistic, which we'll do. That's called a chi-square test. It's coming up in the next residency. But that's the prediction part or the inference part of this description. This is just the description. You can do a similar thing here. This, for example, is for marital status and product. What product you use. Are you not very dependent on whether you're partnered or single? What is marital product versus product? Maybe it has to do with age, or maybe they're correlated. Should you use one as opposed to the other? Okay. You can use counts as well. If you say instead of doing it this way, instead of seeing it as a table, if you want to see it as a plot, you can ask for counts. So there are things like count plots and bar plots, which allow you to do counts. In the lab, you'll do probably a few more of these. This is simply another visualization of the same thing. For those of you who like things like pivot tables in Excel, Microsoft has made, wonders of us all. In corporate life, I was told that you can have a master's in bachelor's and master's in anything. Engineering is good, etc. And it's nice if you have PhDs in a few areas. But what you really need is a PhD in PowerPoint engineering. I mean, that's a necessary qualification for success. So certain tools have been used. So therefore, those tools have been implemented in many of these softwares as well. This is the pivot table version of the same data set. This is the last, not last, but still this is a plot. Let me show you this plot and then we'll end, or we'll take a break. This is a plot that is a very popular plot because it is a very lazy plot. This plot requires extremely little thinking. Pair plot of a data frame. Right? You don't care what the variables are. You're telling it nothing about the plots. You're simply saying, figure out a way to plot them pair by pair. And it does that. So for example, how would you read this plot? On this side, so it creates a matrix. The rows are a variable and the columns are variables. What is this? This is age versus age. Age versus age makes no sense. So what it plots there is a histogram of age. Doesn't like the gap. Nature abhors a vacuum. I suppose Python does as well. So it'll now plot what it should have plotted is age versus age. You're right, it should have been a 45-degree line. But a 45-degree line is a useless graphic, particularly if the same 45-degree line shows up in all the diagonals. So to make a more interesting graphic, it plots the histogram there. This analysis, this kind of analysis sometimes has a name associated with it. The name is univariate. Univariate means I'm looking at it variable by variable, one variable at a time. When I'm looking at age, I'm only looking at age. It's called univariate analysis. It's just a word. Uni as in uniform, same form, unicycle, cycle with one wheel, things like that. Univariate. Unit.
But for the other set of data also, will it replicate the same kind of pattern? If I'm going to give the other set of data.
Another set of data, it will replicate the same nature of the data. There will be histogram here again.
Age and education versus education, this visualization.
So yes, so what it will do is, remember that this graph, the nature of the graph, so let's see this. Right? So where is gender here? Where is gender here? Is it there? Is gender in my data? It is there? So when I did pairs plot my data, What did it do with gender?
It is only 2 variants, so it is only
Yes. Remember in info, when we did info here, remember how it had stored the data? No, not NAN, here. So it had product, gender and marital status, it had identified as objects in the data frame when it had formed the data frame. So now what does it tell you about the command, the pair plot command? Yes, it will ignore those objects. So in answer to your question, if the data frame has been stored, has been captured with integer 64, basically integers or numerics in it, it will plot. If it's only objects, it will probably give a null plot. Yeah.
So how come age is not
Say again, age is not.
line? Why it is not a linear line? Age versus age.
Why like that? This is the histogram. This is the same plot. This plot is the same as which plot? This one. It's the same as this one here. No, this is not age versus age. This is just age. Age versus age would have been a 45-degree line, but it's not plotting that. It's not plotting that. In the diagonal, it is not plotting age versus age. In the diagonal, it is simply plotting age's own distribution.
With count. Age with count.
Yes, with the count. So what it is doing is, it is essentially running hist on age, on each observation, and putting it on the diagonal. Yes.
What can we infer from the histogram of like 20 to 25 bins?
20, say again?
There is a bin, right?
There is a bin.
So what can we infer from that? From each bin?
From each bin, it's a count.
Count of people in that age.
It's a count of the number of people who are in that age group. Here, this is age. No, this is miles. This is age. This is age. So let's say between here, between let's say 40.5 and 43.5, or whatever these numbers are, there are 3 people. Remember, the histogram is a visual thing. You can data mine a histogram if you want to, which means you can find out what those are, and you can see it inside histogram. Just ask for a summary of that, it will give you what the features are of that histogram. But the histogram is not meant to be used that way. It's meant to be used as an optical device, to see the shape, to see the count. It's an art to do a histogram. If you change the bins a little bit, the histogram will look a little different. So I would suggest that unless you've got a lot of experience in this, or you really enjoy the programming, do not fiddle with the histogram. Its shape will change. I'll show you a little later after the break. Not change the histogram, but what shape is. No, not in default. You can go in and change it on size. But the bin width, etc., the bin width of histogram takes a little more to change. Right? So there is stuff out here. You can find other things in which you can play this. So there are ways to do it. Okay? So quickly ending, we're losing our food. So these different plots, and we'll continue after the break. The rest of it is simply an X versus Y. So for example, this is age versus education. This is age versus education.
So the second graph from the first one is just rotated.
Yes, he's right. If this is education on the y-axis and age on the x-axis, or vice versa, then these two plots, 1 and 2 and 2 and 1, are just mirror images of each other.
It's not a mirror image, it's just rotated.
You're right. Depends on where you look, where you put the mirror, but yes. Mirrors. So I remember when I was a kid, mirrors would confuse me. So I would ask the question like this: that when I see a mirror, left and right get switched. but top and bottom don't. I never understood why. You know, due to gravity? You can think, I mean, left and right gets switched, but top and bottom don't. I thought it was something to do with the mirror, and then I thought it was something to do with my eyes, you know, maybe because they left hand. So I looked at it this way, and that didn't help. So yes, it's an important point. When you do symmetry, it's a good catch. It's a good catch to realize that there aren't so many plots. There are actually only half as many plots, because the plot on this side of the histograms and the plot on the opposite side of the histograms are the same. There was another question that one of you asked, is that many of these seem to look like rows and columns. In the sense that, what are these rows? Now, what does this row look, what does this mean? It means that this variable fitness actually has very few numbers in it. It has a number 1, 2, 3, 4 and 5. Now, why is that? Because remember how I defined fitness is my perception of whether I was fit or not in my original definition of the variables. Here you go. Self-rated and fitness on 1 to 5 scale, where 1 is in poor shape and 5 is in excellent shape. This was the created data. So in this data set, I now have this variable in it. These kinds of variables sometimes cause difficulty in the sense that there's a word for it. These are sometimes called ordinal variables. So sometimes data is looked at sort of, you know, numerical and categorical. And categorical is sometimes called nominal and ordinal. Nominal means it's a name of a person, north, south, east and west, gender, male, female, place, etc. It's a variable. Essentially, it's a name. Ordinal is, it's also categorical, but there is a sense of order. There is a sense of order. Dissatisfied, very dissatisfied. So there's an order. Order, therefore ordinal. This variable, the fitness variable, can, if you wish, be treated as an ordinal categorical variable. So for example, the Likert scale is that, so the 7-point scale. Not satisfied, very dissatisfied, dissatisfied, moderately dissatisfied, neutral, moderately satisfied, satisfied, very satisfied. Mark 1. This generates a data from a scale of say 1 to 7 or 0 to 6. So it will show up in your database as a number. Like for example, here you can say instead of 1 to 5, very unfit, moderately unfit, okay, relatively fit, very fit. Instead of giving 1 to 5, give it that way. And you code it up this way, your choice. So sometimes when you have data that looks like this, the Python or any database will recognize it as a number because you've entered it as a number, but you analyze it as if it is a category. So the opposite problem also sometimes exists in that sometimes you get to see a categorical variable show up as a number, but you know it's a categorical variable. A zip code is an example. A zip code shows up as a number, but it's obviously not. You can't add up zip codes, right? You take two places in Bangalore and you want to find a place between them, that's not the average of the zip codes. It might be close, but you can't do arithmetic with zip codes. The other difficulty with zip codes is that there can be many of them, which means that as your data set grows, the number of zip codes also grows. So the number of values that a variable can take grows with the data. And this sometimes causes a difficulty. Because what happens is that in the statement of the definition of the variable, you now cannot state how many categories there will be present. So you know that there will be more zip codes coming, you just don't know how many more zip codes will be coming. But you also know it's a categorical variable, so you can't treat it like a number. And so there are some special types of, problems like zip codes that require special types of solutions. So the plot itself is a very computational plot. If it recognizes it as a number, it plots it. If you don't want to make it plot as a number, change it to a character. Most softwares, including Python, will allow you to do that. Now, this is in some way a graphical representation of it. For the end of this session, we can talk a little bit about the numbers associated with it. So here, for example, my data age, you can also go, dot age if you want to and things like that. This is the mean. 27.7888 is the mean. So you can extract it. There are functionalities of the mean that can be recovered, like trimming, etc., that if you want to. You can calculate the standard deviation. You remember the standard deviation formula? That strange formula that I wrote on the board? This is the standard deviation formula if you want to calculate the standard deviation. You can do this for other variables as well. This is an interesting plot. So I don't want to go too far into this plot, but it's an interesting plot. Right. In Seaborn, there's a warning on the code. This is called, or what they're referring to, is a distribution plot. So this is a plot that tries to look at not what the data is, but what the distribution is. So remember, I was drawing these odd pictures like this, and drawing lines on it. Those were distributions. So what it's trying to do is it's trying to go after the distribution of the data. Now, what does this mean? It means that it says that there is an underlying distribution of the age variable. This distribution is a distribution you do not know. However, you have a sample from that distribution. How big a sample? About 180 observations. From that sample of 180, can you guess at what that distribution is? In other words, can you give me a curve? It's an answer to that problem. And it gives a curve. Why is the raw data not enough? So the raw data is not enough, then this goes to the heart of what the statistical problem is because I am interested not in the age of this particular group of people. I am interested in the corresponding age of another very similar group of people. Why? What is the problem I'm trying to solve? I'm trying to solve the problem of who is buying my cardiac equipment. Now, when are these people going to buy my cardiac equipment? At some point in time? Okay. Now, what is my data? But for whom is this data? Who have I got the data for?
People have already
Right. People have already bought. So I have a problem. My problem is, I want to reach a conclusion about my future customers based on my old customers. How to do this? What mathematical logic allows me to say something about the future based on the past? Yes. In short, the way to do this is to assume that there is what is called a population. We'll talk more later. At this stage, to assume a distribution. To assume that there is a distribution. From this distribution, I have seen a sample today. From this distribution, I'll see a sample tomorrow. The people are not the same. Because the people who are going to use my cardiac equipment yesterday are not what are going to use it next year. If it was the same, I'd never have a growing business. There's no point analyzing data of customers unless I want them to buy more things or I have new customers coming in. So what is common between my observed set of data and the data for my new customers? That commonality is what you can think of as a distribution. So he says that from this, can you give me a sense of what this distribution is? And from this distribution, I can think of other people coming. So what we'll do tomorrow is we'll talk about a few distributions. certain few specific distributions and how to do calculations in the distributions. For now, what this graphic does is it simply calculates that distribution for you. I'll explain very, very briefly how it does that. Won't go into too many details. What it does is, it takes the averages of points. Yes?
So you mean that for a sample, distribution cannot be done?
I'm saying that for a sample, why is not the sample the distribution itself? Why am I not saying, it's a good question, why am I not saying, ignore the curve, why am I not saying that the original histogram, which I've seen 3 or 4 times before, why is that itself not the distribution? That's similar to the following question. Let's suppose that you have done a blood pressure test and you've gotten a few measurements. You've been tested twice today, let's say pre-prandial, before breakfast, after breakfast. Next week also you have done this. Let's say you have done this for whatever be a reason. You have done this, say, once a week for a month. So now you got 4 readings. No 4 readings, 8 readings. Now these 8 readings, is that the distribution?
No.
You need to have a range.
Yes, so there's something that says, yes, if I want to understand what my blood sugar is and what it will be going forward if I do not get treated, then certainly there's a relationship between this and what will happen in the future. For example, if I behave exactly the same way, if I eat exactly the same way, or I exercise and not exercise exactly the same way, if I smoke, if my lifestyle is exactly the same as it is, I would expect my readings to be the same. But what about it is going to be the same and what about it is different, I don't quite know. Yes, it is true that those 8 numbers are a representation of the distribution, but they're not the distribution itself. If they were the distribution itself, I would be forced to say that in the next month, I would have exactly these 8 readings. But I know that's not true. But I also know that from these 8 readings, I can say something about what will happen next month. It's not that there's useless information there. So if my readings this month, for example, are, let's say 110, 120, 115, 125, let's say in good health, 130, etc. I know these are my 8 readings. I know with some idea perhaps that if things remain the same, next month they will not start becoming 220, 210, 215, 230. They will not become that. How do I know that? Because I have this readings this month. So the idea of a distribution is to be able to abstract away from the data the random part and the systematic part. And the systematic part is what remains as the distribution. Around it there's going to be a random variation. And that random variation is going to exist from data set to data set, like this month and next month, like this bunch of customers and another set of customers who buy cardio equipment, maybe from another branch of my store. If I am, for example, running, let's say, a chain of stores, let's say that I'm, I don't know, not to pick names, but let's say, I don't know, Reliance Fresh or something of that sort. And I want to understand how my stores are doing. Let's say I take 5 or 6 stores and I study them extensively. How do I know that those results are going to apply to the remainder of my 500, 600 stores? What is common between these 5 and the remainder? How are they representative of it? What part of it applies to the rest and what part of it does not? How do I extend it? How do I extend your blood pressure readings to the next blood pressure readings? How do I figure this out? That is the heart of statistics. That's called statistical inference. To abstract away from the data certain things that remain the same and certain things that do not. So a distribution is an estimate of that underlying true distribution of age. And so it's not as rough. It's smoother. How smooth is something that the plot changes, that the plot figures out on its own, like histogram. But you are free to change it. You are free to change it. There are functions within it, functions within this plot, and it's a fairly sophisticated function, which you can do many things with. I mean, it's a fairly sophisticated thing. There are many functions available within it. So, for example, this bin of histogram, this allows you to say where should the boundaries of those the histogram part of it be. whether you want to plot it or not. Whether you want to plot that what I was calling a distribution, the Gaussian kernel density estimate, it's a sophisticated way of saying the same thing. And there are functions available to put into that. So you can change this. It's one of the most sophisticated plotting functionals that you'll be able to see. I wouldn't suggest doing it now. Get a little more experience in doing this, but yes.
Slightly different if you use Gaussian.
Gaussian will not make too much of a difference. What will happen is if there is no smoothing out here, it'll look like a normal distribution. These little wiggles will go away.
I mean, it's better, gives you a smoother curve.
We will discuss that a little later as to when, maybe tomorrow, as to when it's a good idea to do that and when it is not. Just hold on to that question a little bit. We haven't talked about the Gaussian distribution yet. I'll deal with that when the Gaussian distribution comes. For now, what this is it gives you a visual representation, simply a descriptive representation of the underlying distribution. Hence a distribution plot.
So the distribution you always want to compare with it's the samples, 8 samples if you're taking an example.
Yes.
You've distributed them, then you're taking a current sample.
So if my distribution is correct, let's suppose in an ideal world, if my distribution thinking is correct, then here's what would happen. If I take my old 8 data and I do a histogram, I do a dist. In the new data, I do a dist again. These two should be very similar. The histograms may be different, but the distributions should be similar, if I've done my analysis correctly.
Does that mean the variance is?
I wouldn't use the word variance, I'd say variability. It means that there is a sum, this is called sampling variability. In other words, there's a variability that is due to the fact that you've taken a sample. There is an underlying truth, but you're not seeing that truth because you're taking a sample. There is an underlying level of your blood sugar, but you're not seeing that because you've taken only a very small sample of your blood, a few milliliters, where there are liters flowing around, and at only at a few seconds in time. There are many hours in the day. There are so many other things that your reading could have been. But if it is a good sample, then what would happen is that I'll be able to cover this variability. So if I want to get a sense of what your blood sample actually is, and I want to sample this well, what I will do is I'll take samples in different kinds of situations. One thing they cover, for example, before eating and after eating, that they cover. Maybe I want to cover other things as well. For example, in certain kinds of diseases, they're very conscious as to where to take the blood from. Because the metabolism in the blood changes based on what? Certain diseases, and I won't make what. For example, you draw the blood near the liver. The liver is the body's filtration system. So essentially you want to figure out the nature of the blood when it flows into the liver, and then after it flows out of the liver, in order to understand whether the liver is filtering your blood correctly or not. Now to do that, you need to draw the blood in very specific places. So in order to do that, therefore your experimentation should cover all of that. What does that mean, for example, in business terms? Let's say that you're looking at sales data and you want to understand your sales distribution. Well, don't focus on certain salespeople. Look at your bad salespeople, look at your good salespeople. Look at your high selling products, look at your low selling products. Cover the range of possibilities. If you do not cover the range of possibilities, you will not see the distribution. And if you do not see the distribution, you will not know where the future data will come from. And if you don't know that, you will not be able to do any prediction or prescription for that. The histogram is just a summary. This is also just a summary. But the histogram summary applies to just this data set. This distribution is pretending to apply to a little bit more.
What is the definition of it?
Definition of?
Distribution.
The definition of a distribution doesn't apply to the data. So a distribution function, so to speak, is just this. So for example, it's sometimes defined this way. F of x is equal to the probability that x is less than or equal to x. This is sometimes called a distribution function. F of x is equal to the chance that age is less than or equal to, say, 15. Age is less than or equal to 16. Age is less than or equal to 17. And now let me confuse you even more. F of x, this is the derivative of x, the differential of x, is the density function, which is the area under the curve. This is called the density function, which is what this plot is plotting. This is sometimes called the density function. The density function, so the distribution function is the integral of the density function, and the density function is the derivative of the distribution function, if you're very mathy in all of this. So what they're plotting is they're plotting the density function. I showed the code. So this is actually called the density function. The reason I'm calling it a distribution function is because it says distribution here. I was hoping not to confuse you. Clearly I failed. Go ahead. Yes. That's the idea. Yes. Now you've hit the problem of statistics bang on the head. How do I get an idea of a distribution that applies to everyone based on only one sample sitting in front of me?
Lake, frozen lake. And then
That is the $1 million question, and that is why people like me exist. Right? That is the whole point of the subject. And it is a hard problem. It is a hard problem because you are trying to draw a conclusion outside your data. Nobody is interested in your data. Nobody is interested in your data. Right? Everybody is interested in their data or in their problem. Aapka मामला आपका ही है. Nobody is interested in your data. Now, but you still have to analyze the data that is in front of you and reach a conclusion that makes sense to them. The bank has to look at its portfolio and figure out what its risk strategy should be. The clothing store needs to look at its sales and figure out what clothes it should make. Great Learning has to figure out its course reviews and figure out which faculty members to keep. You have to look at your expenditures and figure out how much salary to negotiate for. How will you do all of this? How do you do all of this, by the way? Based on some sense of distribution, right? So when you go and you negotiate for a salary, now you're not going to negotiate for 100 crores. You might, but you'll say no one's going to give me that anyway. So maybe you're good enough, I don't know. But what you do is you essentially say, you do roughly something like the following. You figure out how much money you need and how much money you're expecting. And that to some extent is based on your expenditure and what you want to do. Your expenditure is also based on that. You have a certain income and you're spending based on this. You're doing all of this on a regular basis. You're standing on the road. Correct? You're standing on the road and you're trying to decide whether to cross it. How do you decide? Experience. You got past data and that data is telling you, please cross the road. How? That data has not seen that car. K533619 with his driver has not been seen by your data set. How are you crossing? Because you're making the assumption that while I have not seen him, I've seen many others like him. So there's this story, right? So a taxi driver is going at night on the road, etc., and he's just running left, right, etc. So red light, cross, no issues, etc. It just keeps going. The passenger is getting very scared. Stop karo ye. The driver, he says in Hindi, apologize for the language. Hum raaste ka sher hai. And I'm the lion of the road. Who will stop me? He goes through all the red lights. And then there's a green light. And then he stops. And then he says, why have you stopped? Now the guy says, raaste mein bahut sher hai. So the guy on the other side. So he's logical, right? So his data is saying that there are people who cross the red light. So therefore, if I'm standing at a green light, there's red light on the other side, cars are going to cross that red light, right? Very logical. So therefore, and we do this all the time. So while we are not trained as statisticians, at least normal people are not, they behave like one based on the experience. Now your objective and the objective of an analytics professional is to translate this logic into an algorithm, into a procedure that the company and the computer understands. And that is not easy. For starters, let's say that you are here and you say that this is an average, right? This is the mean age. This is 28.7888. And you could say that this is an estimate of the mean of the distribution. This is the mean of the data. But you are not interested in the mean of the data. Why are you not interested in the mean of the data? Because you're not interested in this particular set of 180 people. But you are interested in the average age of my customers. So now the question becomes, what does the age of my new customers have to do with the number 28? Are they related? Yes. You would say that they're like a copy of what I have. Now that's interesting. So if they're like a copy of what I have, then will I see 28.78 again? And I will say probably not. They're a copy, but not that much of a copy. Most likely, now we're talking. So now, how likely is most likely? And what about it is going to be the same, and what about it is going to be different?
The y-axis of the distribution.
So the y-axis of the distribution you will say is the same. So for example, you could say that this 78.8 is an estimate of the population distribution, which means that yes, it comes from the histogram. It comes from the same data histogram comes from, but it also comes from this distribution. But there's also this nagging feeling that I do not know for sure. I do not know. I don't know what this new data is going to be. So what will happen is we will not give the answer 28. We'll not give the answer 28.7. We'll give an answer that is like 28.7 plus minus something. We'll say, I do not know what the population mean is, but I'm going to guess it's around 28. I know it is not going to be exactly 28, but 28 isn't useless for me either. It's going to be around around 28. How much around 28? Now certain criteria come in. What will this depend on? It will depend on the variation of the data. If the data is standard deviation, if the data is very variable, this plus minus will be large.
And the nature of the data, right?
Same, yes, the nature of the, it will depend upon how many things I'm averaging over. If this was 180, I'm so sure. If this was 18,000, I'll be even more sure. If this was 18, I'll be less sure. So it depends on how much data is being averaged over. The more data I have, the surer I am about the repeatability of it. The surer I am that I will see something similar again. It depends upon how sure I want to be. If I want to be 95% sure, if I want to be 99% sure, if I want to be 99 the more sure I want to be, the bigger the tolerance I must have on my interval. And those are things we'll get to. So those are also descriptions, but those descriptions are heading towards being able to predict. So now if I give you this 28.78, I've given you a description of the data, but I've not given you a prediction. If I've now given you 28.78 plus minus something, I've now begun to give you a prediction. Today is about descriptive analytics. We're not predicting anything. We'll get there. But this plot is in some way a first measure of looking at this idea of a population and of a distribution associated with the population. Okay? This is, yeah.
Deviation is less. That means this curve will be almost flat. Instead of
If the variation less, this curve will be sharp. Flat means variation is more. If the curve goes this way, it means that there is a lot of variation. I'm unsure about the middle.
In that case, we can't give the proper prediction.
It's harder. You need more data.
No, if data is more, definitely the variation will be more.
Not necessarily. The variation of the average would go less. So let's suppose that you have no control over your diet. I'm not accusing you of anything. It happens to humans. But let's suppose that you are doing a job in which your lifestyle is very varied. You travel from place to place, you eat in different hotels, sometimes you don't eat at all, sometimes you stress out a lot, sometimes you're naturally going after trains, and sometimes you're sleeping for 12 hours in a row. Your life is highly variable. Now let's suppose, and there's nothing wrong with that, many people have very varied lives. But let's suppose I'm now trying to measure the blood sugar of such a person. What must I do? Now, try to other variables, or at the very least what I need to do is, if I simply want to get a good blood pressure measurement, is I have to measure it under many different circumstances. Or I could argue, I don't control your circumstances. I can control your circumstances. So I can say, for example, that go and measure it at this time, or go and measure it. Take a glucometer, and before going to bed, do this. Or after you've just had a very hard day, do this. I can give certain instructions to cover all the corners. Or I can simply say, I don't know, but what you need to do is you need to measure your blood pressure, or sorry, your blood sugar, say every 6 hours. And then tell me what happens. But you need to do this often, because I expect your blood sugar to be highly variable. Simply because your body is being put through an enormous amount of variation. In a business situation, let's suppose that you've introduced a new product. You do not know if this new product is going to sell or not. What will you do? I mean, how will you measure it? You've just introduced it. Based on past data, you'll do that, but you've just released it. You can measure current data. No. Different situation. I've just released the product. All that is over. All that is over. I now have just released this watch in the market. What typically happens is people track the market very, very closely. Number of hits to the ads, the number of sales made, everything. The reason is because they're not sure how much this will sell. See, the question is what changed? What changed was your product release. Now the competitor could be reacting immediately. My point is not that there are many things to look at, which you should. My point is that when there is a change in the distribution, when there is an unknown distribution coming in front of you, whose variation you do not know, you tend to get more data. You sample more frequently, or you get more data. You figure this out. We do this all the time. For example, let's suppose for those of you who have kids, let's suppose your kid is going to a new school. What will you do? You'll ask more questions to them. You'll get more data. You'll find out what is happening in school. What are the teachers like, etc. Because there's too much variability standing in front of you. Now with those answers, and then you do a few trips to the school, you're now a little more, you know. You may like it, you may not like it. But you're at least more informed. The distribution is now known to you. So you get more and more data. That's why you get the experience. That's why you start getting that experience. If you have that experience already, in other words, if you know the distribution very, very well and you're comfortable with it, it'll take time to get there. And that's why this big data world is becoming so interesting, that by the time you have understood a problem, the problem is not important anymore. There's a new problem. Now this is good, right? That's why you guys have jobs. But it also means that the answer to that it also means that when you have new data, you solve a different problem. You don't solve the older problem better. Which is what a statistician to some extent is trained to do. That as you get more and more data, get the distribution better. Get a better idea of the unknown. Make a better product. But the alternative view is make another product. Solve a different problem. If you have more data, so the CEO is now saying, I have more data, give me more. More of what? Solve another problem for me. Give me new customers that I can go after and things like that. So therefore, that problem is a problem that statisticians, big data people often, and it's not an easy problem to go after. That as you have more and more data coming in, how do you utilize it? How do you make efficient use of this information? Do you get tighter estimates of what you're going after? You're doing sentiment analysis of text. Many of you will do text analysis. You'll write, Twitter code in Excel, and you'll do latent semantic analysis. You'll look at positive net sentiment scores and things of that sort. And now the question will be that you know that this is going to change. People's opinions are going to change. Correct? So, over what granularity do you expect people's opinions to stay the same? Do they change every day? If they change every day, there is no point looking at a person over an average of days, because that average is nothing. Every day is a different opinion. On the other hand, if their opinions change, let's say on a monthly basis, then you can look at daily averages and average them. You'll get a better estimate of that monthly rating. So you have to make a guess as to whether I'm estimating a changing thing or whether I'm estimating a solid thing better. That's not an easy thing to do. I know it's happened to me. I don't know whether it's happened to you or not. But there are times in my life where I have simply not had haircuts. What that means is, I've gone 6 months, 8 months. A haircut has been like a weight loss program. Right? I've not cared what I look like. I'm not sure I do now. But, when things become very unhygienic, I go and get a haircut. There have also been times in my life when I've been a lot more conscious of what others think about me. You can imagine what points in my life. So now I groom, I'm very careful, I get my hair done and, I'm all correct and I'm getting my hair cut much more regularly. Now, what am I doing? So in the second case, what I'm doing is I'm trying to make sure that I'm reaching a certain distributional standard. There's a certain target distribution that I have and I'm interested in getting there. I'm intolerant of variability. I'm saying that I'm going to estimate this distribution and I'm going to stay close to it. In the first case, I was not. I was perfectly okay with the variability. And in certain cases, you will be okay with the variability and you will not want to estimate a distribution of this type. And in certain cases, you will. You will want to estimate it very, very well. You'll want your hair to be done very correctly. You'll want your product to be targeted to a very specific age group. You'll want to know that when I am targeting to this particular age group, what advertisements do I want to show? You'll want to advertise it on television. And you'll want to know who is watching the program on which you're advertising this. Are they college people? Are they professionals? Are they old people sitting at home? Who will use this? And therefore, where will I advertise my cardio product? There are times when you'll want to know this very, very precisely. Or as precisely as you can. So therefore, this number, this mean number, and this number from a description perspective, is perfectly okay. It is just the average. But from an inferential perspective, it's just the beginning of the journey. It's just one number. And we're going to have to put a little more bells and whistles around this. Statisticians need to make assumptions about their data. One of the assumptions is what he's talking about. It assumes a certain distribution. It says that I'm going to assume that the data has a normal distribution. It's an assumption. Now, why do statisticians make assumptions like that? One reason they make assumptions like that is because they make it, the calculation becomes easier. Now, just because the calculation becomes easier doesn't mean the calculation is correct. Because if the assumption is wrong, the calculation is also going to be wrong. But because of the assumption, you can do many of these calculations. And if you don't make those assumptions, these calculations now become difficult or even impossible given the data at hand. So a lot of the tests and a lot of the procedures that we'll be talking about are going to make certain assumptions. We'll see one in about an hour or so. And if that assumption is correct, I will have a strong model. But if that assumption is wrong, I will still have a model that is indicative. So there was an economic, I think Paul Samuelson, I'm not entirely sure who, but someone who said, George Box, I think, the box. He said that all models are wrong, but some models are useful. So the question is, it may still be useful. If, in many cases, the distribution is expressly allowed to be not normal. The domain tells you that. Let's say that you are in an engineering domain, you know the data has a certain shape. And the engineering domain tells you that it's a shape, and the shape is sometimes called a Weibull distribution. What that means is that if you are reporting out, let's say, the failures of something, you're reporting out the failures of gas turbine blades. I've spent a number of years doing that. We had to report out a Weibull distribution. We didn't report out a normal distribution, we had to report out a Weibull distribution. In the finance industry, you report out a log-normal distribution, means and variances of it. Every industry has its own favorite distribution, because every industry has its own generic data form. Now, even within the industry, a particular data set could violate that rule. And then it becomes interesting that as a statistician, do you now use a higher power tool set, a more powerful tool set to solve that? This leads to certain complexities. The first complexity that often runs into is which one, and do I do it differently from someone else? It's literally like a doctor who looks at a patient and says that, you know what? The textbook says that I should do it this way. But I like this guy. He looks different. I've never seen anyone like him before. So let me ignore the textbook and treat him this way. I think he'll get better. Now, could I be right? I could. But I'm taking a risk. So every time you're making an assumption on your own and following through on it, you're taking a very similar risk. You could be right for that particular case, but the precedence, you have far fewer precedences to go on. And as a result of which, later on when you extend it beyond to someone else, you're going to find it hard to do so. So therefore, people often make assumptions on distributions in a sort of historical sense, that they've known that this has worked moderately well over a period of time. And they're very hesitant to change it for particular cases. Sometimes they're not allowed to. In regulatory terms, they're not allowed to. Any accountants here? Accountants, right? So accountants, so you know this. So if you're an accountant, you have to do your books in a certain way. Right? Let's say that you're measuring cash flow. There is a certain way in which you will measure cash flow. Right? Now, you may say that in this particular month, your business was done a little differently, so I'm going to show better cash flow this way. If you can, you know you're running into trouble. Now, you may be right. You may be right in the sense that that may actually be a better way of doing it. But as soon as you go out of CFA, as soon as you go out of a very standard way of doing things will be a problem. And the same kind of logic applies to often statistical analysis as well. So as a result of which, like an accountant, you are doing the right thing approximately most of the time. In machine learning, there's a term that you might see, there's a term that's often called, like supervised, unsupervised, etc. It's called pack learning. Pack learning. It's a deeply technical field, and PAC stands for probably, approximately, correct. Probably, approximately correct. I'm not telling you anything. If I'm wrong, don't blame me. But I'm probably approximately correct. And the probabilistic part comes from statistical thinking, the approximately part comes from machine learning thinking. And it's a deep field, it's a serious field. But it puts a probabilistic statement on an approximation. So therefore, at the end of the day, whatever method you use, there has to be a sense of how generalizable it is. You will do that. You'll do that fairly soon. In a couple of months, you'll do your first hackathon. In your first hackathon, all your hackathons will have a certain feel to them. A common feel for a hackathon is, I'm going to give you a data set. You build your model on the data set, and I am going to have a data set that I'm not going to show you, and I'm going to tell you how well your model has done on my data set. And you have a day or 6 hours or whatever to fiddle around with your data set and show improvement on my data set. This is what you'll do. You'll do it twice, I think, in your schedule. What does that mean? It means that by being very good on your data set doesn't necessarily mean you are successful. You have to be good on my data set, but I'm not going to give you my data set. This is not as impossible as it sounds. This is a very standard problem, and this is a typical problem. You will not find this hard. You will find this very easy by the time you get there. No, not a problem. You all will. Your predecessors will. You will. You'll get 90, 96, 99, whatever % accuracy. Not to worry. Technically, this is not hard. How? Right. So there are two answers to that. One is, if the mean is different from the median, then you ask no. Mean being equal to the median from a distribution sense means that these are the two numbers. Okay. If the distribution looks like this, and I have a parameter mu, we're going to do this later. When statisticians use a Greek letter, they're referring to something that they do not know. Right? It's all Greek to them. So mu is a population parameter. It exists, but it is unknown. It exists, but it is unknown. Now, if the distribution is nice and symmetric like this, then this unknown thing in the middle can be estimated using a mean, or it can be estimated using a median. Now, the question becomes, which is better? And the answer to that, roughly speaking, is this, that if there are many outliers, if this distribution tends to sort of spread out to the tails, then use a median. Because of the reason that I said, the median becomes stable to outliers. If this distribution has a more bell-shaped curve of this particular kind, the mean is more efficient at this. A better answer is, what if the nature of the distribution is not that, but it is like this, then the median may be here and the mean may be here. Now you're asking different question. Now it's not a statistics question, it's a common sense or a science-like question. Which one are you interested in? Are you interested in per capita income, or are you interested in the income of the typical Indian? Correct? For example, let me ask you this. How much time, or give me one number, one representation of the amount of time that you spend on a website? I'm asking for one number. Don't tell me the number, but think in your head as to how you would answer this. How much time do you spend on a website? By a website, what I mean is this. Yes, but what does average mean? So how would I do this? So here's what I'm asking. You're cruising the web every day, let's say. So what I'm asking for is a number like this, and the amount of time that you spend on a website, you go to different websites, and you spend a variable amount of time on each of these websites for whatever be your purpose. Sometimes you're just passing through, sometimes you're seeing a video, sometimes you're sending an email, blah, 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 whatever. And every session I'm thinking of as a different website. And if you go to Google twice, then I'm thinking of that as two websites. So session wise, so to speak. Now I'm asking for a representative number. So how would you come up with that number? What's a fair answer to that? A mean? So if I do the mean, here is how I would do it. On a given day, so the first website I've gone to, I'll find out how much time I spend there. Second, how much time I spend there. Third, how much time I spend there. Fourth, how much time I spend there. And I add this up and I divide. That's the mean. Right? What would be the median? The median would be, I'd look at all those times and I sort it and I'd put this in. Which is going to be larger? It depends, is correct. But in this particular case, so think of your typical browsing habits. Now everyone's browsing habit is different. But just think of it, and people who deal with network traffic deal with this problem on a regular basis. So here is what usually happens. Most of your sessions are actually quite short. For example, a query. You go to a website and you post a query. Or you go to your Gmail and you check whether there's been a new email. Or you go to a favorite website, news site, and see whether something new is there or not. Most of the actual pages you visit, you don't spend a lot of time on. But sometimes you go to a website and you spend a lot of time on it. Let's say you write an email. Let's say you see a video. So what does your data look like? Many small numbers and a few big numbers. This is what is called a heavy tail distribution. The distribution, the histogram sometimes looks like this. Heavy tailed. This is the right tail. This is called a tail of a distribution. A tail to a statistician is not an animal thing. A tail usually refers to the end of a distribution. Some called a heavy tail distribution. And network traffic is an example of a typical example of heavy tail. So now here is what happens. People in this particular case, the mean and the median are carrying very different kinds of information. The median is essentially saying that for a typical website that you go to, how much time do you spend on a typical website? Now, if that number is low, that is an indication that most of the time you are, shall we say, cruising or browsing. On the other hand, if you're looking at the mean and that number is high, then you know that you're spending a lot of time on certain very specific websites. And this points to two very different kinds of people. So the mean and the median are carrying different kinds of information with them, both useful. So in answer to your question, it depends on what you're going after. And in certain things you will see one of them being naturally used as opposed to the other. There's also a third one called the mode, which is actually harder. When we were statistics students, we would study mean, median, mode. And the mode is the peak of the distribution, what is most likely. And the reason the mode isn't talked about much is because the mode actually algorithmically is very hard to get at. The mean is a very simple algorithm. The median is a very simple algorithm. The mode is a harder algorithm. You can think about how to write a program for the mode if you want to. It's a much harder algorithm. So the mode essentially, what is the mode of this distribution, for example? So let's take a look at one of them. This is what? This is income for men. What is the modal income? The modal income is here. It's somewhere around 55,000, where this maximum is. Correct? For women, it's here, maybe around just less than 50,000. So you understand what the mode is. It is the highest frequency or the most common value. But in practice, that's actually a little difficult to do. If I give you a set of numbers, how will you calculate the mode? But will you see a spike? What is a spike? So I'll give you all your ages. How will you calculate the mode? So one possibility is you will look at the age and ask which age is the commonest.
Where the count of the age is.
Where the count of the age is more. But that almost means that your data is not numerical. You're almost thinking of the data as being categorical because you're counting how many observations there are at a value. The idea of a numeric is that it is sort of continuous. It's not chunked that way. So for data that is chunked up or categorical, you can easily calculate the mode. For something that is not. And so the mode therefore has become less fashionable because it's not a very easy thing to go after. When we were in college, the mode was something actually quite easy to calculate. Here's the way we would calculate the mode. Here is the histogram. And the way we would calculate the mode is this. We draw a line from here to here. We draw a line from here to here. Left to left. Take the highest class. Draw this cross line, and here is the mode. This is the way we would do the mode in the pre-computer era. Right? I went to college where we didn't have any laptops and things like that. Running a program meant running to the computer center with pieces of paper. So many of these things were done by hand, and this is something very easy to do by manually. This is not that easy to do on a computer. The logic is twisted. You have to figure out what the bin width is. Therefore, you have to therefore his estimation of mode and his estimation of mode will be different from the same data set. That is not going to be true for the mean or for the median. And as soon as two different people find the same answer to the same, different answers to the same question, you know there's a problem with the statistic. So therefore, this is, so the mode isn't done as much these days. These are the histograms, sort of my data histogram. This is a way of separating out the histograms. In other words, looking at the histograms by different column equal to income essentially means that which variable, the by says which gender, so and they go side by side because they essentially tell you as to what the difference in the distributions is. So what does this tell you? I could have plotted a disk plot here as well, or the code could have, but this says that there is a little bit of a difference between the male and the female distributions in shape as well as in the actual values, so to speak. And so from a descriptive perspective, you can keep doing analysis of this kind to see whether there is a difference, not just in gender variable, but in other variables as well. Do people travel the same amount of miles on different devices? A plot like this will tell you. To compare these two, what we can do in next residency, or you can do as an assignment after that, is you can say, is there a statistical difference between the miles of products that are traveled or that are used for between the different products. In other words, is there a difference between these three products in terms of how much usage they see? And you can compare three distributions, and we will compare three distributions in time. Okay. Now the last idea I want to talk about today is we've talked mostly about univariate, which is one variable. We saw a little bit of a plot, but I want to talk about, shall we say, bivariate. Bivariate means two variables at a time. If you want to talk about many variables at a time, that's called multivariate. But before we get to many, let's get to two. So we've looked at one notion, or we've looked at two notions. We've looked at the notion of location. Location means that if there is a distribution, what is its middle? And that can be mean or median. We've looked at variation, like standard deviation range and interquartile range. But when I look at distributions of two variables, there's a little bit more to it. There is a relationship between the two variables that I want to be able to capture. A sense of relation or a sense of correlation. That how do I measure whether one variable is related to the other variable or not? Remember, I'm still describing. I'm still trying to find a number. Like a mean, like a standard deviation, I'm trying to simply describe a number. If that number is this, correlation is high. If that number is this, correlation is low. What should that number be? There are many, many ways of defining such a number. Here is one, and is there in the book. Let's suppose, so I'm going to do this slightly abstractly. So I've got numbers that look like this. x1, these are my points. So for example, if I look at, say, a plot here, let's take one of these. This is, say, miles and income. The amount of exercise done and income. Each of these points has an x coordinate and a y coordinate. These coordinates I'm calling x1, y1, x2, y2, x3, y3, x4, y4, x180, y180. You understand? They're pairs of observations. This is, say, x1, y1. This is, say, x2, y2. This is, say, x3, y3. They're pairs of observations this way. Right? Now, x bar is what? 1 over n, x1 plus xn. And I'm going to write this simply because I'm going to have to write something a little more complicated now. Summation I is equal to 1 to n xi. If you don't like the sigma notation, that's fine. You can write it with dots. Why add a little complexity here? Y bar, which is the average, is similarly summation I is equal to 1 to n yi. Okay. Now I'm going to write something here. I'm going to write summation xi minus x bar yi minus y bar. I'm going to write that down. I'll tell you why I'm writing that down. But look at that. What is xi minus x bar? It's sort of like a variation or a spread of xi from its average. Similarly, yi minus y bar. Okay. Now, when is this term xi minus x bar, yi minus y bar, when is it positive? When both of these are positive or both of them are negative? Right? Now, both of them are positive means what? Both of them are positive means xi is above average and yi is above average. Right? Both negative means xi is below average or yi is below average. So, imagine a data set that looks like this. Where is X bar and Y bar? Somewhere in the middle here. Here is one line, or here is a line, and here is another line. For all the points here, Xi is above its average and Yi is above its average. For all the points here, Xi is below its average and Yi is below its average. Which means all these terms, or most of these terms, are going to be positive. I may still have a point, for example, say this point, where it is negative. But when my data looks like this number will be positive. What happens when my data looks like this? When my data looks like this, then Xi is above its average, Yi is above its average and Xi is below its average. That means one of these is positive and one of these is negative. That means this guy is negative. So when the data looks like this becomes negative. What happens if the data looks like this? The positives and the negatives will, this number being negative means when one is high, the other is low. For example, let's say height and weight. Height and weight means what? The taller you are, the heavier you are, the relationship between the two. My doctor says that I'm about 4 or 5 kilos overweight. I say, no doctor, I'm about 2 inches too short. I don't have a weight problem, I have a height problem. Your interpretation. So therefore, if you want to therefore get a statistic that captures whether your data, whether your variables are moving together or in opposite directions. Opposite directions, for example, might be something like, say, weight of a car and mileage of a car. Bigger cars have lesser mileage. Which means that if you have an above average weight car, that probably has a lower than average mileage. So this particular measure this is an addition. When I divide it by 1 over n minus 1 to take an average effect, this thing is called the covariance of x and y. This is called the covariance of x and y. Covariance are very heavily used in certain areas. They're heavily used, for example, in dimension reduction, in principal components. You see that in time. They're used in finance, for portfolio management and things of that sort. This is called the covariance of x and y. What is the covariance of x and x? The covariance of x and x, which means instead of y, I'll just put x. This becomes 1 over n minus 1 summation I is equal to 1 to n xi minus x bar into xi minus x bar, which means xi minus x bar squared, which is the square of the standard deviation. This is sometimes called the variance of x, which is the same as the standard deviation of x squared. So that thing that before I took the square root, that's called the variance. With the square root is called the standard deviation. Without the square root is called the variance. By the way, it's all there in the book. So in case you didn't get it, you can see the video or you can read the book, or these are very standard definitions. So the covariance is a measure of the nature of the relationship between x and y. If the covariance is positive, they are moving in the same direction. If the covariance is negative, they are moving in opposite directions. If the covariance is 0, then many things can happen. Either the data looks like this, there's no relation, or maybe the data looks like this. Not a normal distribution. This is not a distribution. This is, say, price and profit. For example, what is the relationship between price and profit, by the way?
Sales down.
So this is the theoretical relationship between price and profit. On this side, as price goes up, your profit increases because you're getting more money per product. And on this side, with even higher price, fewer people buy your product. So your profit goes down. Now for such a thing, the average is somewhere here. So the correlation also becomes 0. Another way to think of it is positive on this side and negative on this side. So if this is 0, it doesn't mean that there is no relationship. It could mean that there is a complicated relationship. Something that is positive on one side and negative on the other side, and not that simple. I once remember doing an analysis in which we were trying to find out, it was about attrition, why people leave companies. And inside it there was a model where we were trying to, for some reason, trying to find out the relationship between, or trying to understand where people stay. Do they stay close to the office or do they stay far away from office? And now what do you think is the relationship between, say, experience and distance to home?
Higher the experience, closer the distance.
Higher the experience,
further
further is the home. No, because if I have home very far.
Tenure or experience? Okay. We had normalized for that. In other words, think of it as just experience, but we were looking at populations in which experience loosely translates to age. But you're right. There could be people who join the company very old. I agree with that. But let's simplify life and say that you have a data set in which you experience. And here's what we found. That early on in their careers, people live close by. In the middle, they moved away. And towards the end, they again became closer. Now, this was an observation. There's no science to this. This was just simply seen. In that particular company, this particular thing would happen. But remember, the point is not to describe. The point is also to predict, to understand and things like that. So we had to build a story around this when we went to the CMD and said that, here's what we had done. So you can make up a story around this. And the story we made up, correctly or incorrectly, I don't know, is that in the beginning, to some extent, people have low dependencies. You typically coming, you're unmarried, bachelor, etc. You're also ready to work a lot harder. So staying close by is convenient. You get a PG or you get an apartment, you stay close to work. Because staying further away from work gets you no particular benefit. It's just inconvenient. But as you reach in some way middle age, so to speak, things become very complicated. There is a spouse here, she may have a job, there are kids, there are schools, there's kinds of houses that you can afford. And so this solves a more complicated optimization problem, and you may not be able to find a solution to that problem close to work. But people who survive even longer in the company earn enough to solve this problem through other means. And then what happens is they move back to work again. Buy a villa close to, etc. And now there are multiple cars to take people elsewhere. Kids are often grown up. So the number of dependencies are a lot less. You may agree with the story, you may disagree with the story. But the point is that there's a complicated relationship you're trying to explain based on what the data is. Now the use of it, I won't talk about much. So this number is a number whose sign, positive or negative, tells you about the nature of the relationship. But only the sign tells you. The value is much harder to interpret. The reason is because I can measure these things in whatever units I want. Suppose I'm measuring, so height, say height and weight. And I measure height in centimeters and weight in kilograms. That's one answer. But I can measure height in feet and weight in pounds and get a different answer. I can even make this number much higher by measuring height in millimeters and weight in milligrams. I don't know why I do that, but I get. So this as a value is entirely dependent upon the units of measurement, which makes it a problem. So what statisticians do when they reach this situation is that they normalize things. They make the unit go away. So the way the unit goes away is you divide this by the standard deviation of x, and you divide this by the standard deviation of y. Now I can do this on the board without writing anything again, but I would suggest you write the whole formula again. When I divide this by the standard deviation of x and the standard deviation of y, now the units cancel out. Now this value becoming 1 means xi is 1 standard deviation above average in whatever be its units. And yi is say 2 standard deviations above average in whatever its units. The unit has gone away. This number is called the correlation between x and y. And the correlation between x and y is a number between is a number between -1 and 1. The correlation is between -1 and 1. If the data looks like this, then it is 1. If the data looks like this, then it is -1. This is the correlation. It is a measure of the relationship between two variables, measured in this very peculiar way. It is not just a measure of the relationship, it is a measure of what I would say the linear relationship between x and y. A non-linear relationship or a strange relationship could cancel out positive and negative and end up with 0 or a low number. So if the correlation is close to +1, there is a strong positive relationship between the two. Strong positive relation means what? If one of the variables is above average, then the other is also very likely to be above average. And vice versa. So what I can do is, this is the, when I do my data and I do .cor as a function, this gives what is called the correlation matrix. Again, it will calculate it only for the things with numbers. If it doesn't, in other words, if you give it a data frame and this doesn't happen, then just make sure that you only take the subset of it which has only the numbers. Do not calculate correlations for things that aren't numbers. If they're not numbers, there are other ways to calculate association. We'll see that later as well. Now based on this, what do you see? First of all, the correlation between age and age is 1. Why? Well, it's the 45-degree line, right? By definition, it is 1. That this is a number that comes from one data set with one kind of relationship. What does that say? Anything about the practical world, so to speak? It's another way of saying what I've been saying all along. How does your data have anything to say about these relationships outside the data? The problem is a little clearer here maybe, but the problem exists for anything. So for example, there is a correlation of 0.28 between education and age. 0.28 means that there is a positive relationship, but not a very strong one. Where is that graph? This is age. Education was the second one, right? So this one, right? Or this one, whichever way. This shows that there is a weak positive relationship between them. When one goes up, the other does have a slight tendency of going up. Now I should warn you that there is no sense of causation here. There is no sense that if x goes up, then y goes up. Because correlation of x and y is the same as the correlation of y and x. Definition? This is a symmetric concept. It makes no attempt at causation. That's a different thing altogether. So this is a positive, this is a positive relationship. It's a weakly positive relationship. This is about usage and education is about 40.4. income and education is about 0.62, miles and usage is about 0.48, miles and fitness is about 0.78. Let's see miles and fitness. This is miles and fitness. Nothing in this data set has a negative correlation, but you might have seen it if one was negatively correlated to the other, negatively related to the other. Close to zero. So you're looking for low correlations, right? So age and usage, for example, is a very low number. Age and miles. In other words, age doesn't seem to have much to do with things, shall we say, other than income. But age and income doesn't really have much to do with your product per se. It will be useful in when you do clustering later on. Variables like that are useful to try and segment. Rich old people. Always an interesting segment. Yes.
So, correlation is zero. What is the meaning?
Correlation means zero, that there is no relationship between the variables. It could mean, for example, that a plot that looks like this. Let's pick a variable. So closest to zero is what? Age and usage. So age and usage is where? Usage and this one? No, this is age and miles. That also is something low probably. This one? No, there's no relationship between them in the sense that there probably is a relationship in the variability. In other words, there's more variability here than here. But if I want to draw a line through this, the line doesn't have a positive slope or a negative slope. There's no idea that says that if one of them is above average, the other is also likely to be above average. So low correlation means that there is no sense that one being above average related to the other being above average. No increasing, no decreasing. Correlations are notoriously hard numbers to interpret, but they're also very useful summaries, particularly for large data. The question that he asked is does this make any sense in the real world has two components to it. Component one, is your relationship between the two related to a linear concept? So for example, I was talking about height and weight. What should be the relationship between height and weight? Linear. So if I plot height versus weight, I should see a straight line. Okay? Now she's going to say, not necessarily. Okay. Removing outliers. We're all outliers, aren't we? Okay. Have any of you heard of a concept called the BMI? Body mass index. In this day and age, you have all heard of body mass index. क्या होता है? What is body mass index? Height by? No, there is no age in it. Height by weight squared. Height by weight squared. Now, so BMI is height by weight squared. Now, if BMI is height by weight squared, what does that tell you about the human body? Height by weight squared is what is called BMI. And this number, let's say, should be around 25 if you are healthy. What does that tell you? If you are taller, what will happen? How should your weight increase? No, there's a square here. Half the rate. So roughly this should mean, let's say that this is correct. Let's say roughly that this is correct. If this is correct, what does that mean? It means that height is approximately 25 into weight squared if you're healthy. That means if I see a bunch of very healthy people and I plot their height versus the weight, I should see a curve like that. Not a straight line. She's figuring this. She's saying, now why? If I'm twice as tall, I should be twice as heavy. Yes, if you want to give it a fancy name, correct. No, you're right. That is a parabola. Undoubtedly true. Now you could argue as to why is it height by weight squared? That's a slightly different question. Why isn't it, say, weight by height? So let's suppose that so weight by height means what? So let's suppose that these two, they're not the same. Well, let's suppose that so these two, so this is a certain height, this is a certain height. If I put this on top of this, what happens to the weight? If these two are exactly the same, this is going to double. Or if I take two of these, I don't see two of them, I apologize, but anyway, okay. So here's one more. So these two, so if I put this on top of this doubles. So therefore, if I look at objects such as this, then by doubling the weight, I'm doubling the height. So height by weight remains a constant, correct? So if I'm looking at BMI for bottles this way, it should be weight by height. So if you were a bottle, your BMI would be weight by height. Okay. Now imagine that you are a football. Now if you're a football and your height doubled, how much bigger would you be? You understand the problem? Is a football, it is now twice as high. How much heavier is it? By a factor of what? So the height has doubled, volume has gone up by what? No. Pi r what? No. 4 by 3 pi r cube. It has gone up by a cubic factor. So now, for a ball, the BMI should be weight by height cubed. So you're not growing like a cylinder and you're not growing like a football. You're growing like something between a cylinder and a football. We all are, not you personally. So, which is why it looks like that. Right? Babies grow like cylinders. We don't. We don't grow like cylinders, because if we grew like cylinders, we'd be a lot thinner. Think of yourself, imagine yourself when you are, 5 or 6, and now double your height. You'd be a lot thinner. Right? Similarly, you don't grow like you don't grow like a football as well. Imagine yourself at 5 or 6, and now imagine you grew in every dimension in the same way. You'd be a lot fatter than you are now. So therefore, this relationship depends on the empirical relationship between height and weight for the data that is available, which is of humans growing. And so empirically people have discovered that this is the object that should be invariant. This is an example of what's called dimension reduction. Two variables are being combined into one, which is carrying information for you. But it relies on a nonlinear relationship between the two that is not going to be only picked up by the correlation. So the correlation goes so far and no further. It is not one of the more analytically useful things. Very often we do test a hypothesis. Is the correlation 0 versus is the correlation not 0? To ask whether the correlation is real or what is often called spurious. And in a later class, I think about 2 or 3 residencies from now, you'll spend some time on things like spurious correlations. In other words, I'm finding a relationship between X and Y, but is it real or is it due to something else? Yes, it could start as a basis for a causation. It gives you some summary of the data. It is at best a descriptive measure of association. Sometimes people want to see it in another form. This is what's called a heat map. It is exactly the same thing as a correlation, except that in a heat map, it gives you nice colors. It gives you nice colors. And you can change those colors, so to speak. Here's the index of what the color is. -1 is pale blue, positive, etc. And positive was in the same direction. So it gives you a sense of what the color is. So sometimes when you have lots and lots of variables, this is too few a set of variables for a heat map to be useful. So for example, let's suppose that you're looking at a product catalog, a few thousand products. And you're trying to find the correlation between sales of those products across time and across geographies. And you give a display of, where, and so you do a heat map and you find those regions where the products are sort of clustering up. We often do it in medicine through what is called microarrays, where essentially we look at data from genes, and let's say there are thousands of genes, and you look at the expression levels of each of these genes, and you say these are the genes that have been expressed, and these are the genes that haven't been. So if you are doing correlations of thousands of variables or hundreds of variables, often a nicely arranged set of variables with a heat map gives you a good picture of the data. So heat map in this form is exactly the same as a correlation, except that it adds colors to the numbers. So that you're not looking at the numbers, you get a visual picture of it. So the traditional choice of it is hot is related. So red is related and white is not. But there are many ways in which you can change the coding of the heat map's colors. Okay, now comes to some extent a tool that is descriptive. However, it is the first predictive tool that you will see. I will not want to use it like a predictive tool, but I'll still show it. So let me show you what the end product is. The end product is, I want to summarize the relationship between, say, miles, usage and fitness, variables like these. Right? Now in relationships of variables such as this kind, here's an equation. Miles is equal to minus 5.75 plus 20 into usage plus 27 into fitness. This is, shall we say, a targeted equation. What is this equation? As far as I'm concerned today, this is a description of the data. But the description of the data will be used in order to predict how many miles my instrument will run. So, think of what the instrument is. The instrument is an engineer designed instrument, and I'm trying to figure out how much it will be used, how many miles it will be used. To do that, I will figure out whether people consider themselves fit or not and how frequently they use it. And using that, I want to get an equation for the number of miles this will run. Is there a descriptive way of getting at that equation? So, what this does, this kind of an equation, it's what's called a linear regression model. This is your first model. This is going from descriptive to predictive. I haven't done it yet. I'm just saying what I'm trying to do. Self-rated fitness on a 1 to 5 scale. I'll get there. Okay, so maybe I shouldn't have shown you the output. Always dangerous to show good people output. Never show output, moral of the story. So what I want to do is keep it deliciously vague. So y is equal to beta naught plus beta 1 x1 plus beta 2 x2. I want to fit an equation of that type. Why do we have multiple variables? I can't do it with one variable. Maybe life is simpler with one variable. You have given me itna sa data diya, ek hi variable ye kya hai yaar? So you can. In the code, as you'll see, you can have one variable, you can have two variables, you can have three variables, you can have any number of variables. I think they've chosen two to say that, I once had we were going from bivariate distribution to multivariate distribution. So he did all of bivariate distribution, and then at the end he said, now put 2 equal to n. And we were telling him, sir, it doesn't work that way. If you do it for n, I can put n equal to 2. But if you want me to put 2 equal to n, in which 2 do I put which n? So he's saying, I'll show you it for 2, but if I show it for 2, you can do it for 1, and then you can do it for 3, you can do it for any. But we can try it for 1 also if you want to. So let's look at that, and what am I trying to put here? I'm trying to put miles here, and I'm trying to put usage here, and I'm trying to put fitness here. I forget which was where, but anyway, these two variables. How am I using it to describe? So you might want to think of it this way. If I give you 3 variables, how do I describe the relationship between them? If I give you 3 variables, how do I describe the relationship between them? There are 3 variables. In the form of something like that is one way of doing it. Now, does that mean that in reality, as he might say, that there is a relationship between these three things? No. Correctly so, being precise. Maybe, I don't know, not necessarily. Correct. Not necessarily. So, when you do linear regression in the future, any regression for that matter, there will be three uses of it. Use one, it is simply descriptive. It will simply describe the nature of the relationship to you. It will make no causal inference, no sense that this causes this. It will give you no predictive model. It simply describes, and we'll discuss how it describes. Two, it predicts. Predicts means when I put in another value of x and another value of x1 and another value of x2, I will get a different value of y, which means that I've looked at data from all of you and a new person comes into the room with a new x1 and x2, and I'll put then her number in and I will predict her y. That is the predictive use of a model. Third, prescriptive. In order to get a different targeted y, what changes should I make in my x1 and x2? To get different usage of the equipment, what behavioral changes do I need to make in people to get them to use more? An even more complicated use of the same thing. So the same model, the same principle can be used for different uses. I am using it simply as a description. Simply as a way to summarize not univariate, not bivariate, but trivariate or multivariate. I can do that with a 3x3 correlation matrix. But if I choose to do it this way, now what number am I looking for? Fitness is here. Average number of miles a customer expects to walk or run. Average number of times the customer plans to use. So I'm going to give it this variable and this variable and try and get an outcome for the middle one. Getting it, the way to do it is something that I won't talk about too much. So there's sklearn, which is one of the learning modules that they learn in the sense of supervised learning. Import linear model, regression linear model as a function, and the slightly irritating big function here called linear model, which is inherited from linear model. You're giving it a y. What is the y? The thing on the left hand side of the equation. What is the x? The thing on the right hand side of the equation. What is reg fit? Reg fit means regression fit. And this fits my x and y. And this outputs something. It doesn't output anything at this point in time. Now I have my regression coefficients. And my regression coefficients are 20 and 27. My regression intercept is minus 56. And my miles predicted is minus 56.54 plus 20 usage plus 27 fitness. How is this interpreted from a purely descriptive perspective? It means that, for example, if usage remains the same and my fitness goes up by 1 unit, then my miles goes up by 27 units. If my fitness remains the same and my usage goes up by say 1 hour or 1 unit, then my miles goes up by 20. What does minus 56 means? If you don't use it at all and you have 0 fitness, you have run minus 56 miles. Makes no sense, but neither does 0 fitness. So the model is not necessarily written in a way in which this intercept makes sense, which is why in the software the intercept is not treated as a coefficient. The intercept is a part of the equation, but is not one of the coefficients that you interpret. This is pure description. What does it do, in case you are asking, and I hope you don't? What it does is this. What it does is, it looks at the data And what is my data? My data is, say, y1, x1, x2. And it says this, it looks at yi minus beta naught minus beta 1 x1i minus beta 2 x2i whole squared. This is my prediction or the equation, beta naught plus beta 1 x1 plus beta 2 x2. This is my actual. What prediction is the closest to my actual? In what sense? Find the difference between the prediction and the actual, square it, and then minimize it with respect to beta 1, beta naught, beta 1 and beta 2. So what are beta naught, beta 1 and beta 2? They're variables or they're parameters that are estimated in such a way that if I estimate it this way, this plane is the closest to the data. In what sense? In the sense that the difference between the predicted and the actual is the smallest. Don't worry, you will do this again. You will do this again. This is a very important thing in supervised learning. In prediction mode. In description mode, all that is necessary for this to happen is that it describes the nature of the relationship between miles, usage and fitness. Describes in what way? In addition to the interpretation of the numbers, there's also something else interesting here, the positive sign. What does the positive sign mean? It means that as fitness goes up, miles goes up. As usage goes up, miles goes. I've summarized the relationship between three variables, treating one of them as a output. This is a descriptive use of linear regression as a way to describe data. Is the description real? To be decided, to be confirmed, to be analyzed, to be understood. Right? You do not know. It is empirical. It is based on data. Why is it necessarily true? Is there a logical reason why this is to be the case? Yes. You can do it with one. You can remove it. So if I remove it, what happens? So what would you do? You guys can do it if it's there. You'd move it here. Instead of usage and fitness, just have one of them there. I have not given you any idea as to whether the description is good. I have not told you whether this model is a good model or a good equation. In the same way that I did not tell you whether the correlation was good or whether the mean was good. I have not given any quality assessment to anything. These are ways to describe the quality of the model. How accurate is my mean? How good is my prediction? These are things that are going to be inference and prediction and will come. We can't answer those questions before we get to probability. In the middle here, sense of language on it. Yes.
If you put the fitness and usage as one, the answer is still negative.
Fitness and usage as?
1 hour and probably 1 as fitness. Taking it 1. The answer gets negative.
That's true. So you're saying that it doesn't make sense for certain values, which is true, which may well be. As I said, I am not saying that this is a good predictive model. What will happen is you will study a model like this and you will ask certain questions. What questions might you ask? For example, here's a question that you would ask. You would ask the question that if I fit a model like that, is this coefficient that is in front of this variable actually equal to 0? Because if it is actually equal to 0, then there is no relationship between the output and that variable. So what we do is we ask for a statement of this kind. If say yi is equal to beta naught plus beta 1 x1 plus beta 2 x2, I ask for the statement, is beta 1 equal to 0? And these are called hypotheses. Because if beta 1 is 0, then this number should not be in the model, and therefore this variable has no predictive power over this variable, which is where the analytics part becomes interesting. But to answer that question, I need to have a sense of how do I know whether this is 0 or not. And to answer that question, I need to have a sense of what the error around that number is. So this number is not 20. It is 20 plus minus something. In the same way that my mean of 28, age of 28 was not 28, it was 28 plus minus something. This is also similarly not 20, it is 20 plus minus something. And if that plus minus something includes 0, then I can't say that this is not 0. If on the other hand that plus minus does not include 0, I can say it's a predictive model. That's coming. But for now, this is simply a way to describe data. And like for means, like for correlations, like for standard deviations, and for linear regression, all of these, all will now see an inferential phase to them. The mean must see a plus minus. The regression coefficient must now see a test. Is it equal to 0 or is it not equal to 0? All these models, all these estimates will now be put into an inferential test, into a predictive test. How useful is it for new data? Because just describing current data is not going to be good enough for me. I'm writing an equation like this. I want to write this equation. I want to write miles is equal to beta naught plus beta 1 into usage plus beta 2 into fitness. I want to write this. The code now tells me what these numbers are. This number is minus 56, this number is plus 20, and the third number is plus 27. That's it. You can call it intercept based on whatever your term is. Yes. Yes, yes. In X, just put in another variable, do comma another variable. It can be any number. Try it out. I mean, you can do it now. If I don't want to fiddle around with this, I won't plot it. My purpose is to, if I could plot it, I would. But remember, there are 3 variables. Remember, there are 3 variables. Why am I doing this? Because in 2 variables, I can plot it. I can also look at many variables at a time and see a correlation. But if I have 3 variables, plotting things becomes difficult. If I have 4 variables, plotting things becomes even more difficult. But you still do it. I think you have Tableau or in your curriculum, maybe, I'm not sure. But visualization techniques can still help you. But if you've got 10 variables, then plotting is not a way to do it. So how do I express the relationship between 10 variables? By arbitrary equations like this. What does it mean? This intercept is, if this is 0 and this is 0, what is this? But as we have said, this 0 doesn't make sense and this 0 doesn't make sense. But this is simply a line that goes through the data. If I have data that looks like this, for example, all it does is it fits this straight line. What is the intercept? Where it cuts this axis. Does it make any sense? Maybe, maybe not. This is the place where the data makes sense. But the equation is written so that it cuts the line here. Correct? If I find a relationship between height and weight, and I write the equation as y is equal to beta, or say weight, is equal to beta naught plus beta 1 into height. What is beta 1? Beta 1 is the weight of someone who has height 0. Makes no sense, right? But giving me the freedom to have a beta 1 here allows me to get a much better line, because I can move this line up and down in order to get the best fit. It allows me an extra flexibility. Don't worry. In fitting good models, you will have enough experience in doing this. My purpose is just to show you it as a way to describe 3 variables in one shot. I'm not building a model. So if I do it for 2 of them, just miles and usage, just 2 of them, this is an equation just of this kind. With 1 variable, you wouldn't do this, because there's nothing to model, right? There's no equation between 1 variable. Criteria for doing this, remember, my purpose is not to use this to select which variables to model. When I'm calculating means and standard deviations and correlations, I'm not using them to select anything. I'm not saying that I will measure your mean because you're important, or I'll measure your standard deviation because you're low. I'm using this as a tool to summarize 3 or 4 variables. Which variables to use when in predictive mode? You can do. You can look at for high correlations, and there are many other techniques that you learn in order to figure it out. So just like a mean is a way to do analytics, correlation is a way to do analytics, standard deviation is similarly. So what we had done yesterday is we had spoken essentially about descriptive statistics, and descriptive statistics is the taking of data and to simply describe it with the later purpose of either visualizing it or writing a report or using it for inference and prediction in later courses or later applications. It is compared with predictive statistics or predictive analytics, and then prescriptive. Describing is simply a task of summarizing a given set of numbers. You'll do sessions in visualization in due course. Prediction is a task that is often in machine learning or data mining professionals' requirement to say that if something changes, then what happens. I should have made a comment that there are 2 English language words that mean more or less the same thing. One is forecasting and one is prediction. In the machine learning world, these words are used a little differently. Forecasting is usually in the context of time. So something has happened in the past, what will happen in the future? I'm giving you this week, what will happen next week? Forecasting in the future. Prediction is usually used without any sense of time. Prediction is like I'm giving you an X, you give me a Y. So I'm giving you one variable, you give me another variable. So predictive analytics doesn't necessarily forecast anything, despite the fact prediction itself is about forecasting. So the words mean slightly different things. It's a little like, price and worth mean more or less the same thing, but priceless and worthless mean different things. So the words are used in a slightly different context. So in descriptive statistics, we had looked at certain ways of doing things. For example, we had looked at what is called univariate data. Univariate means one variable. For the univariate distributions, we had seen certain kinds of descriptive statistics. Some of them were about, shall we say, location. Location meant where is the distribution, and we had seen, for example, things like means and medians, which talked about where is the distribution located. We talked about things on variation, where we had talked about standard deviation. We'll talk more about things like this today. Standard deviation, range, interquartile range. Here also we had terms, for example, like the quartiles, the upper quartile, the lower quartile. These are parameters that are used in order to convey a message to someone saying that what is the data about. So for example, a 5-point summary talks about the minimum, the 25% point, the 50% point, the 75% point, and the maximum. Irrespective of the number of data points, you could have 10 of them, you could have 100 of them, you could have 1,000,000 of them, you could have 1,000,000,000 of them, it doesn't matter, it's still 5 numbers. Sometimes those 5 numbers tell a lot. They tell about location, they tell about spread, they talk about skewness. Is the distribution sort of tilted towards one side? Is there more data on this side than on the other in terms of the data spreading out towards the tails? So there are plots associated with this as well. We talk a little bit about the plots later. Then we went towards the end, towards the idea of, let's say, bivariate data. Bivariate means that there are 2 variables in which we just didn't spend a lot of time. We talked about covariance and correlation. Covariance is a sense of variability of two variables together. Its univariate version is a variance, which is the square of the standard deviation. A scaled version of covariance is the correlation. If the correlation is close to +1, then it means that there is a strong positive relationship between the variables. Positive means if one goes up, the other also goes up. If one goes down, the other also goes down. Negative means the opposite. As one goes up, the other goes down. Correlation is not to be confused with causation. There is nothing in the descriptive world that says that this causes this. There is no science to this. This is simple description. The science to it and the logic to it and the use of it for inference, for business logic and things like that will come a little later. For now, we are simply describing. Then we have taken an even brief and perhaps even more confusing look at multivariate, or first multivariate summary, where we looked at the idea of a linear regression. A linear regression is an equation of the form y is equal to, say, beta naught plus beta 1 x1 plus beta p xp, where one variable is written as an equation of the others. This is merely done to describe the nature of the relationship between the variables. Correct? It can be used for prediction, it can be used for prescription if you wanted to, but that is not our purpose here. Our purpose is simply to describe a relationship. Why is this useful? Because let's say that you've got 3 variables, 4 variables, 10 variables, you need a mechanism to say how these variables are connected. How do you describe 10 things at a time? There are graphics out there, there are famous graphics in history where you have many variables being represented on one plot or one visualization. So visualizing things itself, so for example, we looked at a certain kinds of plots. We looked at, for example, histograms. We looked at box plots, sort of pairs, which were essentially what are called scatter plots. So these are for the human eye. These are things for the human eye to see data. And they have the limitations because we can only see data in a certain way. We can't see very high dimensional data. Visually, we can see up to 3 dimensions maybe. For those of you who are interested about such things, or any of you who are in the graphics world, etc., you spend a lot of time saying, how can I make people see things? So how many dimensions can you actually plot in? I mean, Python itself is good at it, but there are other devices. So for example, let's say that you're plotting, you can have, of course, one variable as x, one variable as y. Another dimension can be maybe the size of the plot. You know, if this is bigger, then another variable z becomes larger. It can be a color, like a heat map. A 4th variable, if it is low, can be blue, and if it is high, can be red. Another may be the shape of it. Lower values are circles, higher values are more pointy. So there are many ways in which you can get summarization to be done. So when you do visualization, if you do, you'll see other ways of summarizing it. But if you want to do it as a number, then something like an equation that looks like this is often a good representation. How one gets at these beta 1s and beta p's, I explained very briefly. What happens is you form this equation and you take those values of beta naught, beta 1 and beta p that are closest in some sense to the data. So if I draw a picture of, say, 2 of them, y on x, and I say give me a line, which line should I take? Take the distance from the line to the points and make this distance the smallest. Get a line that goes through the data with the smallest distance to the points. How is small measured? Small is measured by the square of these distances, because distance on the above the line and distance and below the line are equivalent. So if this is my beta naught plus beta 1 x and this is my y, what I do is I look at y minus or yi minus beta naught minus beta 1 xi. I is equal to 1 to n, my n point, square it. This is the squared of the distances from the line, and then I minimize this with respect to beta naught and beta 1. That is how I get the numbers. But if you're simply interested in what Python or R does, then the program will simply give you what the number is.
So what those will give? This minimizing of beta 0, beta 1.
What? Sorry?
What I will get it from those?
You will get the value of beta naught and beta 1. Find the value of beta naught and beta 1 such that this is the smallest. For different values of beta naught and beta 1, this distance will be different. For different lines, this distance from the line will be different. Which line will I take? The line such that this is the smallest. How to get the beta? So, form this yi minus beta naught minus beta 1 xi squared.
On a plot, actually, that points are where the point exists.
The point is here. The points are here.
So these line is basically which.
The line is the line I'm trying to find. Here is a point. 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 Right? Let's say I have 5 points. I want to describe the relationship between these 5 points. Therefore, what I need to do is, I need to find a line that goes through these points. I want to write an equation of the type y is equal to, say, I'll remove the b and x, y is equal to a plus bx. I want a line like a plus bx going through those points. There are many lines. This is one line, this is one line, this is one line, this is one line, they're all lines. Which line will I use to represent the relationship between y and x? I need a criteria. So what I do is, I try to say, let me find a line, let's say that this is the line, and find out how good it is at describing the data. Now, when is it good at describing the data? When it passes close to the points. Because that is its purpose, to describe the data. Because I want to say that this line, without any data points, is a description of the data.
But how to get that line position?
That's what I'm talking about. So I need the value of A and B. Correct? So how do I find the value of A and B? For every such line, A and B, I find the distance of the points to the line. So if there are, how many points do I have here? I've got 5 points. So I've got 5 distances. What are the points? This is the point x1, y1. This is the point, say, x2, y2, x3, y3, x4, y4, and x5, y5. These are my 5 points. How far is the point x1, y1 from the line? This distance. And what is this distance? This distance is how much? This distance is, this point is y1 minus what is this point? A, so A plus B x1. That's the point on the line. Correct? Okay. I can stop here, but if I stop here, what will happen is that if this is the distance, then this will become a negative distance and this will become a positive distance. And they will cancel or neutralize, as you say.
Sir, A is which point? Which is from that point to the line, actually that is the A distance.
No, A is this equation. A is the equation of the line. You want to know what the term A is? A is this point. B is this slope, and I want to find A and B. So this equation is A plus BX. So this point is Y, and this length of this line is Y minus A plus BX1 squared. Plus, for the second one, what is it for the second one? Y2 minus A minus BX2 whole squared. Do this 5 times. Correct? For every line, you will get this number. If you want to, you can take a square root. For every line, you will get this number. This number is the sum of squared distances of the line from the data. It tells you how far the line is from the data. The larger this number is, the further the line is from the data. The smaller this number is, the closer it is to the data. If the data is on the line, what is the value of this? 0. So if every point is on the line, or if the data is itself a straight line, then this will be 0. So I have formed this. Now I find the value of A and B such that that is the smallest. For every A and B, I will get the value like this. If I take another line, I will get another value of this. For every choice of A and B, I will get a different distance from the data. Which A and B will I pick? That A and B such that this distance becomes the smallest.
So can we have an issue where the algorithm means computationally we don't find the value of which can kind of minimize means the kind of
okay, so let me finish this. So choose A and B to minimize this. And that is the A and B that the software gives you. This is called a linear regression. Right? Answer 2, does it have a least square? This is why Gauss was so successful and Laplace was not. You will get a unique solution. This is what's called a convex problem. And this is a convex optimization because of the squaring. If you have modulus values here, there is a possibility that you will not get a single answer. But because of this, and because of the square and because of the nice bowl-shaped curve that the square function gives you, you will find a unique solution to this.
So how many times the system tries? The number of data points?
No, the system doesn't do it that way. The way the system does it is, the system differentiates this with respect to A and B, differentiates with respect to A, sets equal to 0, differentiates with respect to B, sets equal to 0 and solves those two equations. It doesn't minimize. It doesn't minimize. When this becomes very high dimensional, this minimization, this differentiation of solving it becomes a very interesting problem in mathematics and numerical analysis. To do that, you need typically to do linear algebra, and in courses such as this and in machine learning books, you will see at the beginning of the book, you will often find chapters on optimization and linear algebra because of this or something similar to this. That to represent a problem, you often need a matrix representation, and to get a good learned solution, you need an optimization. So most machine learning algorithms are built that way. Because for example, as I was saying yesterday, that you're going to tell someone to do something. You're going to tell a car to behave itself on the road. Yesterday, while going back, today morning, I heard that, or I read that BMW and Daimler are setting up a, €1 billion R&D operation somewhere in Europe for self-driving cars, etc., etc. Two different industries are trying to go towards making cars that don't need people. The automobile industry is, as well as the ride-hailing industry. People like Uber and Lyft and Ola and these companies. So now you're going to figure out, the car is now going to have to be told when to go and when to stop. But how does the car know that it has a good rule? How does it know that it has learned? And what is good learning as opposed to bad learning? What is enough learning as opposed to not enough learning? A computer is stupid. All a computer can do is store a lot of data and do calculations quickly. Computers aren't intelligent. To make the computer intelligent, you have to give it an intelligent function. You have to say, okay, run your algorithm such that this thing becomes the highest it can be, or this thing becomes the lowest it can be, which is an optimization problem. So what machine learning algorithms almost invariably do is they say that here is an input and here is an output. Give me an algorithm such that based on the input, you can come closest to the output. For example, object recognition. If I'm teaching computer vision, or if I'm teaching text recognition, or any of these, let's say text recognition. So I'm trying to understand what the word is. So the computer is reading something, let's say in handwriting, and it's trying to identify that as an English language or a Kannada or a Hindi phrase. So it's going to write something down. You write this, and in my horrible handwriting, I'll write something, and that camera has to recognize what I wrote and transcribe it into something that you can read. Now, how does it know it's done a good job? What it needs to know is that this is what I think the word is, and this is what the correct word is. Now tell me whether I'm close. And if I'm close, I'm good. If I'm not close, I'm not good. But this has to work not just for one word, this has to work for thousands of words. So I must be close to thousands of words at the same time. Therefore, I need to measure the distance from my prediction and my actuality over many, many data points. So all these algorithms, what they do is they take your prediction and they compare with the actuality. And they find a distance between them. And they minimize the totality of the distance between the prediction and the actual. And an algorithm that minimizes that distance is a good algorithm. It has learned well. So they all do something like this. Where this is the prediction and this is the actual. And A and B are the parameters in the prediction. In other words, find a prediction such that it is closest to the actual. So this algorithm has become very popular. It's probably the single most popular fitting algorithm out there. This is called least squares. Least squares. This is called least squares. Squares. Here's a square. Least because you are minimizing. This is called least squares. And the least squares algorithm is a very standard way of doing things. This has nothing to do with the algorithm itself. The algorithm can be anything. This itself can be a neural network. It can be a support vector machine. It can be a random forest. It can be association rule. It can be any of your logics. But the question is, if you give me the program, how do I know whether the program is good? So I give it what's called training data. Training data means I tell it what the right answer is.
So sir,
yes.
This we can infer that this is the starting point of basically what the prediction and what actuality is that we are comparing, and
yes.
we are getting the result of that.
Yes. So this is the prediction. This line is the prediction if you want to think of it. The data points are the actuality. The problem is this. These data points are also not the actuality. The actuality is going to come in the future. It is a training set for the data. It is the data that has been given to the algorithm to train it. But it is not the algorithm, it is not the data that the data will actually run on. The car will run on the road. The car will see its data points, its people and other cars and the cows and whatever for the first time. It will not have seen that data before, but it will need to know what to do.
You're starting off learning basically.
Yes, so what do you do? So what you do is you train the algorithm. What does training the algorithm mean? Training the algorithm means you give it data for which the car is told what to do. In other words, you give it what they call ground truth. So you give it the why and you say, here is the data or here is the situation. Please do the right thing. So please do it such as this. So here's a person who's crossing the road. Please stop. Here is another person crossing the road, but he's very far away. Calculate the distance, compare with your speed, and decide what to do. He may be far enough for you to be able to see, but you may not stop. If you are driving a car, it's quite possible that you are seeing someone crossing the road, but maybe about close to 100 meters ahead, and you're not slowing down. Because you're doing the calculation that I have a speed, the person crossing the road also has a speed, and by the time I get there, this person would have gone. Do not do this when doing a level crossing. But we all do this all the time. We do this when crossing the road. So I'm happily doing that. There is a car coming, but I'm still crossing the road. Why? Because I know that I'll be able to cross the road before I get there. So the car needs to be taught how to do these things. So this data, it's given data like this and says, for the training data, get as close as you possibly can to the training data. And then it's given what's called test data. And now the algorithm is told, oh, now I'm going to give you new data. And now you're going to tell me how well you did on new data. So suppose you were given a problem like this. I'm not supposed to talk about this. Your ML instructors are supposed to talk about this. But suppose you're given a problem like this. In other words, I've given you a data set and I'm going to tell you that your performance will be judged not by this data set, but on another data set that I am not giving you. What will you do? How will you make your program ready? Yes, so how will you make your program generalizable? So the usual way it's done is something interesting. You say that, okay, you want me to predict data that I have not seen. I will see if I can do that. So what you do is all the data that is available, you take a certain part of it and you keep it aside. You have it, but you don't use it. And now the remaining part of the data you build your algorithm on. And now you test it on the kind of data that you yourself have but have kept aside. This is called validation data. And now if your algorithm works on your own held out data, that data that your algorithm has not seen, you are more hopeful that it will work on somebody else's new data. This is called validation. And this entire cycle is often called test, validate, train, etc. Or train, validate, test, etc. And you will do this in your hackathons. But to do this, the algorithm needs to know as to how good it is. And it needs measures like this. There are other measures. So for example, if you're classifying an algorithm, good or bad, positive sentiment on tweet or negative sentiment on tweet, no numbers, then you do not need this. What you need is simply, are you correct or are you incorrect? If it is correct, let's say you give yourself 0 distance. If it is incorrect, let's say you give yourself 1 distance. In other words, you made 1 error. And you just count how many mistakes you made. But what is a mistake when it comes to estimating a number? Like say miles and things like that. There's no mistake. You're either close or you are far. So you need a measure of how close. That's a measure of how close. So this descriptive method is used as a criteria for building predictive models. This itself can be a predictive model, but very rarely is it good enough. Too few things in the world are this simple. Are there things in the world this simple? Yes. But as we said, as we discussed yesterday, even things like height and weight are not that simple. There are complexities to that. So for example, you can have theories which say, for example, you could say, let's say a savings rate. What's a savings rate? A savings rate is the proportion of money that you save. Now, if there is a savings rate, what that would mean is that if I take your income data and I take your consumption data, that should form a straight line. Because you're saving up the same proportion every month. But it's not. If you go home and month by month you figured out what your income was fairly precisely from your salary or from other sources, etc., etc., and you also plot again fairly precisely as you can how much your household spent that month, it will have an increasing effect probably, but it's very, very unlikely to be a straight line. In certain things you may be going after a law of physics, but the law of physics may hold for gravity, may not hold for anything else. I remember trying to apply this, so one day cricket sort of became popular when I was in school or thereabouts, and one calculation was done as to how to figure out whether a team is doing well or how well is a chase going. So one possibility is to simply track the score. The other possibility is to say that if you know how many runs you're going to get, you tend to begin slow, protect your wickets and you accelerate. So what you do is you build models for that. You build models for saying that let me assume that the team is going to accelerate constantly, which means that every over that comes later, it's going to get better. Its run rate is going to keep increasing steadily. Now, if its run rate keeps increasing steadily, then when will it reach the halfway point? That is the same thing as asking the question that if I take a ball and I drop it, how long will it take to get to the halfway point? And there's a square root term there, and the answer is about 50 divided by the square root of 2, about the 37th over or something of that sort. So effectively the logic was, if you've reached halfway point below, let's say, the 37th over or so, you are on track. If not, you need to accelerate a little faster. That's using a physical law to try and predict something that is not a physical law. I mean, the laws of physics do not apply to cricket, at least not in this way that I am describing. So therefore, these laws will get you somewhere, like a straight line, etc., but they are approximations. And so what you will do is you will build better versions of this when you use it for an actual prediction. But the same argument holds for things like mean, standard deviations, and many such things. If there's a specific problem you need to solve, you may or may get a better estimate for doing it. Yes, someone was asking a question.
The question is that we calculated y minus a plus
yes.
x1. That is basically the distance.
Yes.
Right? What we are talking
yes.
about from the line.
Yes.
Then what the b is actually that is what we talked about.
So there are many ways to do that. One is you just put it in, you find for different values of a and b, you find what that number is, and then you solve it. If you want to do it the hard way, you can still do it the hard way, and the hard way will end up being something like this. I'm minimizing, and I should not be talking about this. Say yi minus beta naught minus beta 1 xi whole square. I was using a and b, right? So say a and b whole square. I'm going to minimize this with respect to a and b. So essentially what I'm going to do is I'm going to call this, let's say, L of a and b. And I will say DDA of LA is equal to 0. DDB of LB is equal to 0. And I will solve these, and this will give me two interesting equations. And my answers will be this. I'll tell you what the answer is. Your B hat, your estimate of B will be this. Summation xi minus x bar yi minus y bar divided by summation xi minus x bar whole square. And your A will be this, y bar minus b hat x bar. So if you want formulas, these are your formulas.
So how to compute that these derivatives will come to 0?
Because I'm minimizing something. To minimize something is the same thing as setting as derivative 0. Now that is also the same as maximizing something, but this is where convex optimization comes in. That this will have a minimum, but won't have a maximum. So by setting it equal to 0, I'm going to arrive at the minimum.
So,
yes.
The minimum will come with respect to A, right? Not with respect to X and Y.
Yes, X and Y are fixed. The data is fixed. The parameter is varying.
The range is fixed.
X and Y are fixed for my data, correct? So my B is written in terms of A and. So this is a formula. If you want to close it, this can also be written as the covariance of X and Y divided by the variance of X. So if you want to calculate it for two variables, what you need to do is you need to calculate the covariance and divide by the variance. And here y bar minus bx bar, this means that the line passes through x bar y bar, the line passes through the middle of the data.
So with the derivative, the minimum will be, we are minimizing A, right?
We are minimizing with respect to A. A is a variable.
So how come this equal to 0 will minimize the distance?
How it will do this? So for different values of A and B, the distance will look like this. There's a particular value of A and B in which the distance will be this. There's another value of A and B in which the distance will be this. There's a particular value of A and B in which the distance will be this.
That is corresponding to the x.
This is my summation yi minus a minus b xi whole squared. This value. For different values of a and b, I will get this. So when I minimize this, now to do this, you don't need to do it. All you need to do, if you want to do it, is this. If you want to do it, do this. Do you have yesterday's code? Open it. You can do it. Then right now, that's it. You stop. It's like saying I get the mean, then what? One use of it is to predict. Another use of it is to prescribe. There are many uses of it. A third use is to do nothing, but simply to use it to visualize or to summarize the relationship between two variables. Correct? And we do this all the time. So for example, how do you measure how price sensitive your product is? Do you understand the question? You're trying to change the price of your product. Why would you want to change the price of your product? Profitability. Maybe you want to increase it so that you get more money. So people in marketing often want to understand how sensitive my sales are to price. Now to do that, they come up with various kinds of measures. One particular measure is what is called the elasticity of demand. Elasticity of demand means this: if my price changes by 1%, by what percentage does my sales change? Well, if my price goes down, I would expect my demand to go up. But by how much? Now there are certain assumptions to this. For example, it's assumed that the same number works if it increase price as well as you decrease price. So this is called the elasticity of demand. So therefore, to get the elasticity of demand, but what is the elasticity of demand? The elasticity of demand is essentially a slope. A slope that relates something like this, that if I have demand on this side, let's say sales on this side and price on this side, I have this negative slope. The slope of this is what the elasticity is. So very often you do equations like these in order to simply get at a number that has a certain meaning for you. So the slope of a linear regression between log sales and log price is the elasticity of demand for that product. I mentioned log sales and log price because the elasticity is done in terms of percentages. A percentage increase in price and a percentage decrease in sales. If I don't do it as a percentage, there's a problem. Now my measure depends on my units. Is it 1000 units per rupee or what? It depends on what I'm selling in one currency, and that's not a good measure. So I measure it as percentages, but when I measure it as percentages, I have to measure on the log scale. So there are many models like this where the equation itself is used to simply describe a parameter, something that tells you a little bit about the market, like an elasticity of demand. You're not using it to predict anything. You're simply using it as a descriptor. So you say that this is an inelastic product. If this is an inelastic product, what does that mean? It means that if you change its price, there won't be too much of a change in its demand. Classic examples of that, for example, are salt. If you change the price of salt a little bit, at least certainly domestic salt, there won't be too much of a change in demand. There might be a little bit, but there are certain things that are highly inelastic. You change it a little bit and the demand will change a lot. And marketing people are very sensitive to this idea, saying that is my demand elastic or is it inelastic? If I want my prices to go up, then I want the demand to be inelastic, because I don't want my demand to go down. If I want my prices to go down, or if I'm pulling my prices down, then I want the demand to be elastic, because I want people to say that your prices are going down, therefore I will buy more. So marketing analytics is very concerned with things like this. So therefore, sometimes an equation of this kind is built just to describe something. Right? So what I'm going to do is, let's go down. And since we are going to do this just on 2, let's pick it just on 2. So let's change this to maybe miles, and let me remove this. So what I'm going to do is, I'm just going to do it on one of them. I suspect one parenthesis might then work. I suspect this might work.
2 parameters.
X has to be in 2 simply because of the way it's entered. Because I have not done anything on this data set now. This one is a comment. So what do I have on the coefficient here? 36 and 22. So what is my equation based on this? Miles is equal to minus 22 plus 36.29 whatever into usage. Okay? Alright. Now let's try to do this manually if you want to. If I want to do this manually, so I need to get at each of these things. So now I need to find, for example, I need to find, let's say, the covariance between miles and usage. How do I do that? Tell me. No, not a sample. The data is present in me. So now I have things like, for example, my data, miles. Correct? So I can calculate things on this. So for example, I can do this. This is the mean. I can do calculations on this. Okay. So now if I do say what is the standard deviation syntax? ST, not DV. Okay. This is the standard deviation. Okay. Let's try one more. This is the variance. What is the variance? The square of the standard deviation. Okay. Now I want to find the covariance of these. How will I find the covariance? Not necessary. Remember, I have the correlation function. How did I find the correlation function here? I found the correlation function from here. So I've got a number of ways to potentially do this. One is I can do it with the correlation function or the covariance function. In other words, so for example, I can try doing this. How do I write it here? My data dot this thing here was the correlation. This gives the covariance matrix. This gives the covariance matrix. Okay. Now, what is the value? What is the value of B according to my formula? So, covariance of which variables now? Which are my two variables? Miles and usage. Where is that covariance? Is it this number? 42.71, right? Okay. Divided by what? Variance of what? Variance of usage. Y. Not Y as in Y, but Y as in question mark Y. So my data dot usage dot var. Is this also here in the data? It is, because what is the what is the diagonal element of this? What is this number? Usage dot, this is usage 1.17, this number here. This number here is the variance. Okay, what is the equation? Usage. This is my x. This is my y, this is my x. So covariance of xy divided by the variance of x. So based on this, what is my answer? My answer is going to be for the answer for my coefficient is going to be, where is the covariance? Here, 42 point, I can do it manually, almost 42.71 divided by, where is the variance? 1.17, say 6 or something of that sort. 36.318. Where is my value of B? Here. This is my slope, right? How do I get my intercept? Mean of y. So my data, this is the mean of all of them. So what do I want? Which mean do I want? Mean of, what is my y here? Miles. Where is my mean miles? Let's say 103, say point, I don't know, say 19, minus, what is my slope? Say 36.32 or something of that sort, star, what is my x? Usage, which is 3.45, so 3.45, 3.3.45 or something like that, right? Will star work that way? Minus 22. What is my coefficient? Minus 22. So if you want to, you can do this from first principles by using that formula. I am not asking you to. You can do it just by running linear regression. But what it is this. You can also check the units. What is the unit of B? The unit of B is the unit of miles divided by the unit of usage. What is unit of the covariance? Miles into usage. Divided by variance, which is miles into miles. So the ratio of this is usage by miles. What is the unit of A? Miles. This is in miles. This is in miles per usage, and this is in usage. So the units all make sense. Which one? Units. What is the unit of the covariance? The unit of x into the unit of y. Why is that? Remember the definition of covariance is the product of an x and a y. So this is in the unit of the product of x and y. This is in the unit of the square of x. So the product of x and y divided by the square of x and y cancel out, this becomes in the units of y by x, which is what B should be. B should be in miles per usage. 36 means what? It is 36 miles per usage unit. That's what B is. B is in some units. Because B is in some units, we will run into some difficulty when you use this in predictive models. Because let's suppose I want to figure out, is this number equal to 0 or not? Because if this number is equal to 0, statistically speaking, then miles doesn't depend on usage. But because this is not a dimensionless number, I can make it anything I want to by simply changing the unit. So that makes the statistics a little hard. So I cannot simply look at this number and say whether it's high or low. I can make your height anything I want to by simply changing the scale. I can make your height 1,000,000 by simply using a small enough unit. So simply taking a raw measurement tells you no idea of the value of its magnitude.
That will equally have effect on noise usage as well.
Yes. That same argument will work for any of those parameters. So therefore, when we do testing, when we do hypothesis testing, we need to normalize all these numbers by something, and that something is typically standard deviation. So we'll do that. Okay. So let's end this. The purpose of this was just to tell you what that regression line is. And then there are similar formulas. But as the dimensions increases, it's hard to do this manually. A joint is a marginal multiplied by a conditional. So the Bayes theorem's idea is the following. What it does is, it switches which event is being conditioned on. It switches between A given B and B given A. Now, when would you need to do this? Here's an example. You want to find out whether the email that you're receiving is spam. Do you use Gmail? Gmail often identifies things as spam and moves them somewhere. How does it do that? Partly it looks at the mails and headers and it uses a very, very complicated algorithm. But let's suppose you are building an application of this sort and you want to do it based just on the content of the email. So you want a following kind of program. You want a program that says that if I know the words of the email, I can tell you whether it is spam or not. Which means I want the following thing. I want the probability of spam given words. If I tell you the words, can you tell me whether this is spam or not? This is what I want to do. Correct? But how will I solve the problem? I'll solve the problem by finding the opposite conditional. What is the opposite conditional? The opposite conditional is, what is the probability of words given spam? Now, why am I interested in this? Because this one is easier for me to do in the following sense. What I can do is, let's say in my research lab, I can collect lots and lots of documents and I can identify them as spam or not spam. In other words, I can manually go in and I can tag them. So let's suppose that I've looked at 1,000 of these and I've targeted, let's say 800 of them as spam and 200 of them as non-spam. Or maybe I go after things that are spam and find 5,000 of them, and go after things that I know are not spam and find 5,000 of them. Now I can solve the opposite problem, which means that if I know that it is spam, I know the distribution of words. And if I know that it is not spam, I know the distribution of words. I can do this inside my analytics environment. So now I know that if it is spam, this is what the distribution of words looks like. If it is not spam, this is what the distribution of words look like. Using that, I will now twist the problem and say, now if you give me the words, I will tell you whether it is spam or not. Now, how do I do that? I do that doing this. Now, this is a very easy formula to understand. Why? Because this formula essentially says this, that why is this equality true? This equality is true because, let me rewrite it slightly. Let me say, what is the probability of, let's say, spam and words? What is the chance of spam and words? In other words, there is an and there. Now I'm going to write this like A and B. But here's the interesting thing. When I can write A and B in two ways. I can write it as B multiplied by A given B, but I can also write it as A multiplied by B given I have a choice as to which is first and which is second. So therefore, I can write this in two ways. I can write this as spam given words multiplied by words, but I can also write it as words given spam multiplied by spam. Do you understand the trick? But what does that mean? That means these two things are equal?
No.
If these two things are equal, that expression now follows. Now I know that probability of spam given words is equal to the probability of words given spam multiplied by probability of spam divided by probability of words. So to execute on this, what do I need? Words given spam, which I told you what to do, probability of spam, which is an estimate of the proportion of emails that are spam or not spam, and probability of words that has no conditioning in it. This is what's usually called a lexicon or a dictionary. So if you give me a dictionary of the language, I can give you this denominator. If you give me, shall we say, an IT estimate or a sociological estimate as to the proportion of words or proportion of emails that end up being spam, I can give you the probability of spam. And if you give me things tagged as spam, I can find its dictionary distributions. If you give me things that are tagged as not spam, I can find it. So therefore, I know the right hand side. Therefore, I know the left hand side. And now if you give me the words, I can tell you the probability that it is spam. So it's either thought of in the way I just described it, which is sort of flipping these two probabilities. Sometimes it is described the following way. Spam given words is an update of just probability of spam. This probability of spam part is sometimes in Bayesian language called a prior. And spam given words is called a posterior. Which means that if I know the words, I have a greater idea as to whether it is spam or not. If I know his income, if I know he's an IT professional, I have a better idea whether he'll buy the product or not. If I know the income is more than 10 lakhs, I have a better idea whether he'll buy a car or not. If I know the words, I have a better idea whether it is spam or not. And to do that, I flip it this way. And because of applications like this, Bayes' theorem has become very, very central to machine learning. Because, for example, think of the autonomous car. What is the autonomous car's decision problem? Something is crossing the road. Should I stop? In other words, given cow, should I stop? Now think of the problem that has to be solved to do that. I can flip it. Now to flip it means what? To flip it means essentially flip it by saying cow then stop. Essentially I now have to tell the program, so I say stop given cow. So now I have to solve it by Bayes' theorem, cow given stop. So I need to say these are the situations in which a car has stopped and these are the situations in which a car has not stopped. So in a stopped situation, look at what that car saw, and in a not stopped situation, look at what the car saw. Like spam and not spam. And now I can flip this and say, therefore, if this is what I saw, I now know whether to stop or not. It's a neat little logic. So this is what Bayes' theorem essentially does.
So it will be a foundation to supervised learning, right?
It is one way of doing supervised learning. It is one style of doing supervised learning. And there are supervised learning algorithms that are explicitly this. For example, Bayesian belief networks or BBNs. There are some supervised learning algorithms that are this but aren't explicitly so. For example, linear discriminant analysis, where what you do is you find the posterior distribution of being in this class given the data. And so this class given the data is written as, class given data. So, and vice versa. So there are at least two of these algorithms that you will study later. Distributed analysis is one, and I think DBNs, I don't know which curriculum, but in general, you will find it to be a very useful trick. I'll come back and I'll show you the theory behind it if you're interested, but this is actually all that needs to be remembered for its application. So the question is in autonomous cars. His question is, why don't I do the simple thing of saying that if you see something, stop? Now, for a computer, following that logic, the computer now has to know what should I do when I see something. Not if I see something and stop. So he could say if I see something on the road, then stop. It will then ask what happens if I don't see something. I should keep going. So this becomes a very simple rule that says that if I see something, stop. If I sort of don't see anything, stop. Now what will this do to the car?
It won't stop in a signal.
Correct. So this is a translation of a rule. The difficulty will be the following, and you can try doing it. The difficulty will be that what precisely will the car see? And it will follow that logic explicitly. So if it sees a car that is coming quite far ahead, it will stop. Now you could say, I'm going to draw a threshold. If it is further away from this in front, the car in front, then don't stop. Because you're expected to see a car in front. And so if you're seeing a car in front, please don't stop because something is in front. But you now have to encode that. And so that way of doing things is entirely feasible. So for example, there's a whole branch of learning called case-based reasoning. Case-based reasoning, and case-based reasoning essentially lies on that. Give me all the cases and give me the reasonings for all those cases. But case-based reasoning sometimes becomes difficult if it becomes very, very difficult to enumerate all the possible cases. For example, in the spam problem, I have to solve this problem for every conceivable word that the email might see. Because the email is going to decide based on the words. And if you do a full case-based approach, if the email sees a word that it has not seen before, the email will say, what do you want me to do? So typically when Bayesian methods are used, when it sees that word, it will do precisely nothing. In other words, it will say, if certain words are there, I will update my decision. If those words are not there, I won't. It's irrelevant to it. There is no evidence that it has. So the other is a probabilistic way of thinking that Bayes' theorem or any of these relate, and this is probabilistic learning. That when you do when an autonomous system or any machine learning system decides, then what does it decide on? So you'll often find in data sets the following situation. I should have had an example, I'll pull it up. All the x's are the same, but the y's are different. All the x's are the same, but the y's are different. Two people have exactly the same characteristics, but one has bought the product and one has not bought the product. Two people applying for a loan have given you the same information. They come from the same village, they have the same income, they have the same, family circumstances, they grow the same crops. One farmer has repaid the loan, the other farmer has not. Car being tested out, there's someone crossing the road, identical scene. One test driver decided to stop, the other test driver decided not to stop. Same x, different y. What should the computer do? Now think of this from a computer's perspective. What is the computer's problem? The computer's problem is, if you give me an x, I will give you a y. Now what do you want the computer to do in this particular situation? Because in your real data, the same x is leading to different y's. Now what's an ideal solution here? What would you do? How would you think through this problem? One possibility is to give it a probability. That's one approach to the problem. What that means is this, that in your data set, let's say half your people who have seen this x have given a y of 0, and half your people who have seen this data set have given it a y of 1. The computer literally tosses a coin and decides which one to predict. That's called a randomized response, and sometimes it's done.
But that could be a disaster as well, no?
I'm sorry?
That could become a disaster as well.
It could. But give me another alternative.
Safest alternative we could go for, right?
Which is safe? How does a computer know that? What condition? Is given the same x, its input is identical.
But the action, what are the consequences of this action? When you stop, is there anything happen? Any problem has happened?
See, that consequence has already been worked out in nature. In nature, if that consequence was there, that would have already have been baked in. So, if there is a consequence to it, and if there was a good consequence, then the test driver would have stopped. In all cases, the test driver would have stopped.
No, the action of stopping. The
Yes.
action of stopping and going.
Yes.
You take that in discretion, which is more fatal. Going is always fatal. Stopping is fatal.
That decision would have been made by the test driver as well, would it not have been? The raw data would also have shown that bias. Or are you teaching a computer to have a sense of value that the real human did not have? Two doctors look at the identical medical report. One doctor says cancer, the other doctor says no cancer. You are building an AI system for medicine. What should it say?
Go for another test.
Go for another test. Okay. You should see a very nice video of Watson. You know what Watson is? You should see the Watson videos. If you haven't seen it and you want to be an AI ML professional or an ML professional, then you should see the Watson videos. Wonderful videos. And you can see the decisions at the bottom. You can see how Watson decides. You know what Watson, this is the Jeopardy videos. So Watson playing Jeopardy. And so Jeopardy is a quiz question in which basically the answer is given and you have to sort of say the question or something of that sort. So when you see the video, you'll see at the bottom, you'll see a bar. And that bar is basically a set of probability statements as to how likely is this the answer, etc., etc. And based on those probabilities, Watson gives an answer. And sometimes Watson does not give an answer because it is unsure of even its best answer. So when you watch it, watch the bottom of the screen, the data that Watson is answering based on. This particular way of doing things, but in general, this problem is a hard problem in machine learning because in the real world, you will have this issue. If this was not the case, if it was the case that identical values of X give identical values of Y, the machine learning problem would be a mathematical function fitting problem. It would be a problem of simply saying if this is the X, map it to the Y. Just find the rule that maps it to the Y. It's not. And the reason it's not is because identical inputs do not lead to identical outputs. And resolution of that has many procedures and possibilities for doing that. One of them is a probabilistic way of doing things. To answer the following question, I will not tell you whether Y is 0 or 1. I will tell you what is the probability that Y is 1. I will not tell you whether you have cancer or not. I will tell you what is the probability that you have cancer. I will not tell you what the probability of hitting something will be if I continue. It's not a definite answer. So I'm asking for a 0 or a 1 and I'm not giving you a 0 or a 1. I'm giving you a probability. So at every time the car when it is driving is calculating a number. Given the scene, what is the probability that I will hit something? Continuously based on what it is seeing. Now you decide based on that probability whether you should stop or not. Based on your risks, etc. The learning system does not do that. The learning system does not say whether you should be diagnosed with cancer. It simply says what is the chance that you have cancer. Now you decide based on your logic as to whether that's enough for me to state whether you have cancer or not. The learning system will not say what is the probability that you have defaulted on it will not say whether you will default on your loan or not. It will say what is the probability that you will default on the loan. Now you decide how much risk you will bear. That's one solution to the problem. It doesn't even try to predict the right answer. It simply gives you a distribution on the possible answers. Now you decide. As I said, if you see the Jeopardy videos, you'll see this in action. You'll see the data on which it does.
The category is 19th century novelists.
What Watson wants to do then is preserve the lead, not take a big risk, especially with Final Jeopardy, because just like for humans, Final Jeopardy is hard for Watson.
Now we come to Watson, who is Bram Stoker, and the wager. Hello.
See the full video.
973.
It's enormous fun.
Total of 77,147.
I would have thought that technology like this was years away, but it's here now. I have the bruised.
Phenomenal.
Watson went on a tear.
Watson.
Look at that. What it's doing is it's given probabilities on the answers. These don't add up to 1. These don't add up to 1. But what is the chance that list is the right answer? What is the chance Chopin is, etc., etc.? This number, if it is below this threshold, Watson will say pass. It won't answer. And is there in the video a few number of times. It doesn't know. But it says that if I am more sure than a certain threshold, and if I am uniquely sure, it will also not answer if multiple of these cross here. Which means both of them are probably right and I don't know which is right. They both sound correct to me. Again, I might stop.
So for each question, Watson will check what is the probability of the...
He'll do that. Every question, based on hearing it.
So if probability is done by Python language or any of machine language thing, then what is that we are here for? Meaning, what is our role in deciding that?
Deep philosophical questions. Why are we existing at all? Why are we here at all? So one reason you're there is to provide test data to the system, or what's called ground truth. In other words, you need to give it spam, and you need to tell it once that this is spam. Just like he's saying, I need to tell it to stop. I need to say that this is a dangerous thing. So a human needs to initiate that. But yes, people are asking that question a lot. That is that human initiation necessary? Now the trouble with that is that the value system that is necessary to decide that this is a good thing or a bad thing is something that computers do not have. And it's extremely difficult to encode that. It's a lot easier to encode in a computer in some way this is good, or this is one decision, this is one decision, and also if you want to encode a cost to it. Then if I do this, this is what cost. If reinforcement learning does this. If you take a wrong decision, there's a penalty function that hurts the computer in terms of an objective. And the computer knows that if I want to reduce, shall I say, that pain factor, I should avoid doing this, like babies learn. That's called reinforcement learning. I don't know whether you'll do much reinforcement learning in this course or not, but you will do that. So you build algorithms of that kind. There will come a time where that will not be necessary. For us, it is not necessary. But even humans have to come with our genetically coded information. We also cannot begin from scratch. We already come coded with this. There's a school of thought that says that that's all that there is, that this information is passing along. In other words, a hen is an egg's way of making another egg. So an egg wants to make another egg, right? Now how does an egg make another egg? Through a hen. It makes a hen. And that hen makes the egg, another egg, right? So, which means that there is a basic information content. The gene is trying to say, I need to survive. So there's a sequence of A, C, Ds and Gs that has a survival instinct. And the only way it can do that is to get another organism to create a copy of it. Viruses do that brilliantly, right? The big war going on planet Earth for a few billion years and still continuing. It's a deadly war. It's got no winners and is going to continue. It's a war between bacteria and viruses. Nobody wins, right? These two are at each other for donkey's years because they have two very different ways of dealing with information. Right? A virus is a retrovirus type thing. A virus is basically just DNA with a protein around it. The way it reproduces is like certain birds we learn in mythology. That information gets into another organism, typically a bacteria. So a virus forces a bacteria to make another virus. And obviously the bacteria doesn't like it. And so the bacteria over billions of years have figured out how to prevent doing this. And viruses have consequently adapted and have repeatedly kept doing this. And so information transference has a long history in the real world. In the computing world, the challenge of saying that how do I input the information, how do I get the machine to learn, is something that we are rapidly evolving in. The reason this current generation is so excited about it, and I'm not that old, but even in my career, and I've been doing this for, I don't know, about 25 years or so, roughly speaking, I've seen 3 or 4 waves of it. It goes up, it goes down, it goes up, it goes down, and different. The current version of it essentially is based on certain deep learning algorithms that have come and have made it a lot easier to feed back information. So, recurrent neural networks, all these neural networks now have the ability to feed context and feed information a lot more efficiently, which means this idea that a computer can pick up context and use it to get better algorithms is there. And that scares a few people mightily. Because what it means is that as a car keeps driving very well, it's knowing that it's driving very well and it will keep doing certain things. So there's a school of thought that says that therefore maybe the car should have a few accidents. Just like maybe there should be a few nuclear explosions. Let's suppose that you go and get an HIV test done. HIV tests are routinely done. Let's say you have surgery or anything like that, etc. HIV tests are done. So let's suppose that for whatever be the reason, an HIV test gets done. And the test turns out to be positive. I hope it never happens to you, but let's suppose the test turns out to be positive. The question is, how scared should you be? Very, that's a reasonable answer. But let's work it out. So, to do that, trying to calculate the probability of HIV given positive test. This is what I'm interested in calculating because my life may depend on it. There are many ways to do this. Here's a suggested route. Now, what I'm going to do is I'm going to write this version of the formula down. Without necessarily, and you'll see what it means here. So what I'm going to do is this, I'm going to write this as probability of HIV and plus divided by probability of positive. Correct? Conditional is joint divided by marginal. Now, I am going to write the numerator as probability of positive given HIV multiplied by probability of HIV. I am going to twist it. Here's why. These are numbers that are much more available to me. What is this number? This number means that if I have HIV, what is the chance that the test will be positive? That's called the sensitivity of a test. A test maker has to report that. This is the proportion of people who have HIV. This is the incidence rate. It has nothing to do with me. It's like my dictionary. It's just the fraction of people who have HIV. So these are numbers that I know. One from epidemiology and one from my test manufacturer. Divided by positive. And I'm going to do something very interesting on the positive. I'm going to write this positive in 2 ways. There are 2 ways in which someone can become positive. HIV and positive plus not HIV and positive. Okay? Disjoint. There are 2 disjoint ways in which I can end up being positive. Either I have the disease or I do not have the disease. Now I can write this as This I had already calculated. It's the same number. Probability of positive given HIV multiplied by probability HIV plus probability of positive given not HIV multiplied by probability not HIV. This is this formula just exampled out. We're going to apply this and see what happens. What are the numbers that I need? I need a number of probability of HIV. Probability of HIV is a incidence rate for HIV. What's a good number for this? 0.01? Well, okay. Let's say 0.1%. That's actually very low. The HIV rate is a lot higher. Or let's say 1%. 1% of people have HIV and 99% don't. What this also means is that probability of not HIV is 99%. Okay. I also need a few other things. I need, for example, this probability of positive given HIV. This is a measure of how good the test is. If you have HIV, what is the chance that it will report that you have HIV? What's a good number for this? 99%? 95%? What does 95% mean? That if you have HIV, there is a 95% chance that I will find it. Equivalently, for 100 people who have HIV, for 95 of them I will find it. Yes?
Can you please repeat this part?
Which one?
Positive HIV, how we concluded that 95%?
I asked. This will come from the, called a sensitivity number. It comes from the test. A very good test may have this at 99%, 99.9%. A not very good test or a cheap test may have this at 90%. I'm assuming that this test has 95%. Pick your own number. Its sensitivity is 90%. The other number is sometimes called specificity. So for example, let's say I go the other way. Positive of negative given not HIV, which means if you do not have HIV, what is the chance that it will say you do not have HIV? Again 95%? Again 95%. In other words, I have a fairly simple test which is 95% accurate. Whatever your disease state is, 95% of the time it will give you the right answer. Okay? Now let me re-ask the question. I've given you a test that is 95% accurate. I'm now telling you that your test is positive. What is the chance that you are HIV positive? 95%? That's a reasonable guess. Right? Let's work it out. Negative not HIV is 95%. So what is positive given not HIV? 5%? Correct? Okay. Now I have everything that I need to calculate this. What is positive given HIV? 0.95, correct? Into what is probability HIV? 0.01 if he is given it as 1%. Downstairs again 0.95 into 0.01 plus what is this? Positive and not HIV? 0.5 multiplied by probability not HIV? 0.99. Correct? Someone please work this out on a calculator or on.
Sir, what is collectively exhausted means it is dependent on.
Means together they cover everything. Yes, which means in our particular case you have HIV or you do not have HIV. There are no other possibilities. They are exclusive. Why? Because either you have HIV or you do not have HIV.
Yeah, that is mutually.
But exhaustive events means there are no other things.
Sir, this P given HIV positive is 95. So
yes.
Because of that 95, we are not calculating this.
Which one?
The last one, 5%.
This 5%? This is, I think, 1 minus this. For not HIV, if negative was 95%, then positive will be 5%. What is this number? Point? I have high variance in my answers. Anyone else? 0.16? 0.16? There is 16% chance you have HIV if you test positive. Why is it that a fairly accurate test, a 95% accurate test, my wife and I have a biotech company, we're trying to release a product on molecular diagnosis for infectious diseases. If we get 95%, we'd be thrilled. Our investors would be thrilled, we'd be in business. This is not easy to attain, particularly cheap. We're trying to keep the cost of our test fairly low for things like UTI and stuff like that. But, so where is the problem?
For sample size.
False positives. 95% approx, but there is a problem of false positives here. So another way of seeing exactly this same calculation, or pretty much exactly the same calculation, is the following thing. So I'm going to rub out Bayes' theorem here, which is exactly this. I leave it to you to link this to BI, etc., etc. But sometimes it's easy to just understand it as an example. That's how it's done. But I'll show it to you as a picture. I leave this here. And now let's assume that I begin with a population of maybe 100,000 people. Let's suppose that I've got 100,000 people who are being tested, let's say. Now, of these 100,000 people, some of them have the disease, some of them do not have the disease, some will, I don't, the total is 100, this is my sample space, so to speak. Now, let's say, how many of them have HIV?
1%.
1%? So that's how many? 1,000? So 1,000 of them are here. So these are HIV, and how many are not HIV? 99,000, correct? Now of these 1,000, how many of them test positive? 950. And how many test negative? 50. Okay. Of this 99,000, how many test positive and how many test negative? So these guys should test negative. So what is 95% or what is 5% of 99,500 of 99,000? 4950 is 5%. So 5% is a wrong, which means 4950 are here. This is 5% of 99,000. And so how many are now here negative? 94,000. About that?
95,000.
This number won't matter much anyway. So you're okay with the situation here? Now let's look at all the people who've tested positive. Where are all the people who've tested positive? These guys have tested positive and these guys have tested positive. So how many people have tested positive in all? So 950 plus 4950. Of them, how many have the disease? 950. Calculate this. This is exactly the same calculation you did before. Arithmetically, it is the same calculation.
Sir, 4950 is the culprit here.
Here. 4950 is the culprit. What does that mean? It means that there were a lot of people who had a false positive. Now, why were there a lot of people who had false positives? Because there were a lot of people who did not have the disease. For that large number of people who did not have the disease, only a few positives will swamp the positives of the people who had the disease. Which means most of the people who are testing positive are actually healthy people who have had the misfortune of the test going wrong on them. But because there were so many of them, it affected the probability. Correct?
So if it is an epidemic, for example, which is not very rare, then I think
Correct?
the test is...
No, but what is it for you? So what is the moral of the story now? So therefore, what will happen let's say therefore, let's say you go and I'm pretty sure this hasn't happened. But if somebody gets a positive HIV test, what will the doctor say? Check once more. Get a retest done. Why? Because let's suppose this is my test. Let's suppose this is my test. And let's suppose now I've changed the test to saying that I will say you have HIV only if you test positive twice in a row. You test it twice and both times you show up positive. Now what happens to these numbers? What is now the positive given HIV and what is now negative given HIV? First of all, what happens to this? What happens to these? What is the chance of a false positive now? So the chance of a false positive, which was previously 5%, now becomes it must go wrong twice. So 0.05 into 0.05 and then 1 minus that. 5% of 5%. 5% of 5% is what? It's a quarter of a percent or something like that, or even less maybe. That becomes now a very large number. So this number becomes much smaller. The chance of a false positive becomes much lower. And because the chance of a false positive becomes much lower, this number becomes a lot lower. And now the number begins to approximate what you think it would. But for this to work, I must be able to multiply the two probabilities that both tests went wrong. That multiplication comes from independence, which means the second test that you should do should be from a different laboratory, which would have its own biases, it will have its own problems, but they'll be independent of the first guy, and you can multiply this out and this problem will go away. If it doesn't multiply out, if the same result happens, in other words, if the same thing shows up, then this 0.5 will not go down. So, now this difficulty with Bayes' rule, this also again, for example, this shows up in many things, even in business. So, if I'm trying to detect, let's say, fraud, I'm trying to detect fraud, and I have a fraud detection algorithm, and I now say, if I see this signal, what is the chance that it is fraud? By Bayes' theorem, that will be low. The reason that will be low is because most transactions are not fraudulent transactions. And so even if there is a small possibility of detecting a non-fraud transaction as a fraud transaction, I have messed up my algorithm.
Does it mean if we run it twice, will it give the accuracy more?
You have to do the test independently. Running the same program twice will not help you. So in the biological example, you need to run it again in a different test. In a machine learning situation, what does that mean? It means you have to give it fresh data. Different data from the same situation, shall we say. Which is a little harder, but that's fine. So this is Bayes' theorem.
Sir, that last world and spam problem, how does it kind of map to this?
How does it map to this? Okay. Oh, it looks completely different, does it not? Okay. We'll do it this way. What is the proportion of spam and not spam? Let's say this is spam and not spam. What is the proportion? So I need to know this. This is the proportion of things that are spam and not spam, independent of what is in the text. What's the proportion of emails that are spam? What do you think?
5%.
30% are spam? Okay. You guys know your inbox. It also points to a healthy social life, right? So now what? Now let's suppose that we fix the problem and I'm going to solve the problem not for words but for one word. So what's a spam-like word, for example? Bye. Congratulation? Congratulation. Right? Okay. Palm, cool. Congratulation. So now I want probability of congratulations given spam. What is probability of congratulation given spam? If congratulation is there, then If it is spam, what is the chance that the word congratulation will be there? 100%? That's a little too. Huh? 75%. Let's say this is 75%. Right? Then what else do I need? Because what is the problem I'm trying to solve? So I'm trying to solve the following problem. I'm trying to find probability of spam given congratulation. This is what I want to find. I want to say that if I see the word congratulation, what is the chance that this email is spam? That is the problem I want to solve. Now to solve that, I'm solving the opposite problem. I'm saying what is spam, what is not spam, what is congratulation given spam, and I need one more probability. Congratulations, not spam. What is this? 25%? Not necessarily 1 minus this. This is a separate calculation, but it could be 25% if you want to. Let's make it 35. Which means if it is a genuine email, if it's not spam, there's 35% chance that the word congratulations will be there. Now I don't need to make this up. As I said, in a laboratory I can look at all spam things and I can count how many times congratulations shows up in it. So now let's suppose this is here. Let's suppose I know this. Now can you do the calculation? You can do it using Bayes rule. You can do it using the drag diagram if you want to. Just try. What is the answer?
So what we are saying that congratulations given are not spam is 35%, that is known actually.
These 4 numbers are known to you. Well, actually, these are the same numbers. So 3 numbers are known to you. If it is spam, then the chance of congratulation is 75%. If it is not spam, the chance of congratulation is 35%. Now I want to find what is the probability of spam given that there is congratulation. Now how do I
Out of these 4, 3 are known, right?
All 4 are known. This is my, shall we say, the information that's available to me. Some of you can try using the formula, some of you can try using the picture. So if I do it using the formula, what will it look like? Spam given congratulations is equal to probability of congrats, I'm going to summarize this, spam multiplied by spam divided by probability of congrats given spam multiplied by probability of spam plus probability of congrats given not spam multiplied by probability of not spam. This. And this is what? Congrats given spam is 0.75 into probability of spam is 0.3 divided by 0.75 into 0.3 plus congrats given not spam 0.35 multiplied by not spam is 0.7. Point? No, is it? 0.47? Or you may want to draw a picture like this, like we had drawn before. Begin with another typical number, let's say 100,000. You'll do it as spam, not spam. On the spam side, this is 100,000 emails. On the spam side, how many will there be? 30,000. On this side, 70,000. On this side, how many will have congratulations? This is on the spam side. 75% of them will have congratulations. So 75% of 30,000, that's what, 22,500 or something like that. And the remaining will not have congratulations. How many here will have congratulations for not spam? 35% of 70,000. What is 35% of 70,000? Huh? 24,500. And so what is my answer? 22,500 divided by 22,500 plus 24,500, which is presumably my 47%. You can do this as well. So, without opening the email and seeing the email, the chance that it is spam is 30%. But if the word congratulations is there in the email, the chance that it is spam has gone up to 47%. Now, you would not do this just for congratulations, you do this for a whole bunch of words, which means that instead of congratulations, you did congratulations and something, etc. Which means that instead of congratulations here, it will be congratulations and something here. Which means for these probabilities, you will need to say congratulations and something else. Let's say another word. What's another word? Offer. So you would now say, what is the probability of spam given congratulations and offer? Now you would need congratulations and offer, but if you assume independence there, this can be congratulations given spam multiplied by offer given spam. So word by word the probability can be calculated and it can be put in. This approach you will see studying text mining, one of your courses, is called the bag of words approach. The words are put into a bag irrespective of their order and things like that. Yeah.
For one word, yes, it's spam and not spam.
Yes.
Here,
yes.
So it will be like 2 cases for each word.
Yes. So each of these, the A will then be a new event, and that new event would be different words. And so that those different words will be thought of as the product of each word. So the chance that the words congratulations and offer are there in the email is the chance that congratulations is there in the email multiplied by the chance that offer is there in the email. That's an assumption that is built into the bag of words model. If you don't like it, what you have to do is you have to give me the joint probability of offer and words, and those models are also there. They're called bigram models.
Offer and word plus spam and not spam.
Or no, spam and not spam are where? Spam and not spam are in the BI.
Right, but in the formula below, for each case,
yes,
we are adding 2 times. So
these two, spam and not spam. Yes. Yes, so you're relating it to 2. Here there are key possibilities.
yes, so the number of possibility will be combination of
no. The number of possibilities in this case, no, and there could be other possibilities here. Here the things I'm deciding between are just 2, spam or not spam. In this formula, the number of things that I'm deciding between are many. For example, in your Gmail, how many categories are there? There's social, there's promotions and primary. So instead of it being spam, I can define it as primary, social and promotions. So now I need to find what is the probability of primary given congratulation, promotion given congratulation and social given congratulation. There are 3 of these now. That now you can apply here. There's B1, B2 and B3. So we've already seen an example of a distribution.
So my appeal to you is, this is a foundation course, and 1 or 2 people said that I don't have any background before or I have forgotten. My answer is they have to pick up, because we can't start. What we have done is from the foundation. As I always believe, I can simplify, but it can't be simpler. You have to accept that. So some efforts people have to make. Okay, let's start now. Once the foundations are very strong, then you can do naive Bayes, which is another machine learning tool for classification. You can think about predictive models. You will have a solid foundation, ANOVA, regression and all, which will be done by some faculty in advanced statistics course. I have done that earlier, but today, because so many centers and all that, I'm doing only what is possible. Incidentally, DACP, they have recorded an online course on advanced statistics I have done that for them, like the foundation. So you can see whenever you have the time. So with this background, my appeal to you is everyone to me in the class is important. I'm not going to brush aside or ignore anyone, but given the quantum of time, very limited hours, it is definitely important that we focus on key topics, themes in the class, and rest of them you can read. You are all intelligent people. A little bit you can learn on your own. It's not a rocket science. So that is the message I want to give. And some of you are very happy with the outcome of the test. Some of you are unhappy because I have scored only 90. The gentleman says, centum I have missed. And I agree with him. Sometimes wordings could be a little bit misleading. But in a multiple choice, you select the best choice out of the 4 available, 4 or 5. So that does not mean every choice in the multiple choice is the best wording. Sometimes it can be a little erroneous, but you have to pick up the right one. Okay. The second part, the last month, we went up to the bell curve. Now the second part is the hypothesis testing, and it has a lot of related things associated, and I will do them quickly and get into the application part of hypothesis testing. This is one area where the entire world is confused, or a person with a 99.99 in the GMAT or a perfect score can be perhaps put into trouble by the faculty who is a statistics professor or something, type 1 error, type 2 error, alpha, and all those terms, and highly conceptually very heavy, but we will do it a little differently this time in the class. And some notation in the textbook I will change based on my experience, that where the students get confused, I will derive it in a slightly different way. Therefore, the terminology which I use in the class, please follow. Now, before we go into the hypothesis part, a hypothesis is an assumption, and we want to test the assumption. There are certain preliminaries we will have to go through. Very quickly, I will highlight that to you. One is, what is a sampling distribution? Very important. A sampling distribution. Let me just do this to you with an example. Suppose in the class, I pick up, let us say this class is the population. So I'll write here, approximately, I write here n is equal to 60. This is my population. 60 observations are there. I use the symbol, Greek symbol, to represent this is the average class mark. Let's say, let's be generous, the class is 70, excellent class, so 70 is the average mark. The standard deviation, let's say, equal to 4. Just write it. This is the class marks. Okay? Representing all the 60 students, what is the arithmetic mean average, which is the mu is equal to 70, arithmetic mean I use. Standard deviation, 4 marks. And this is the marks, the class. Supposing I pick up 3 students, let's say 4 students at random. Any 4 students. How many ways I can do it? 60 C4 ways. And every sample of 4 which I select out of the 60 C4 ways, I can compute the mean. So I can compute my X bar, let's say, for every sample of 4 observations. Because 1, 2, 3, 4, there is another 1, 2, 3, 4 I can generate. Let's say without replacement or with replacement, doesn't matter. But I keep on generating. There are NCN combinations when I use without replacement. There will be, let's say n is equal to 4. In other words, the sample size is 4. I pick up from this 60. So without replacement, NCN means, with replacement n power n. Now the distribution of all the means I have generated is called the sampling distribution. In other words, X bar is not a single value variable. It assumes number of values. Therefore, X bar is a random variable, and therefore I want to know what is the distribution of such of those values of X bar which I have generated based on this experiment in the class. 60 is the population, small n is equal to 4 is the sample. For every sample of 4 observations that I have selected, I compute the mean X bar, then I would have generated a number of X bars. I am asking the question, what is the distribution of X bar? That is called sampling distribution. And in statistics, X bar is called a statistic. Mu parameter, because this is the population. Mu is the parameter. This is a broad concept. So the first scenario, I will assume, so far what I have explained is the meaning of sampling distribution. Is it clear to all of you? Now I am going to dwell a little more deeper into the subject. Supposing I make an assumption, scenario 1. Original population is a bell curve. The marks follow a bell curve. That's the assumption I'm making. Don't say, suppose it is not a bell. We'll come to that. Supposing the first scenario I have here, this is the bell curve here. This is my mu, which is 60. This is the distribution of f of x. Now x represent marks. Marks obtained by the students in the class. Now this is a bell curve. So mean is 60, mu is equal to 60. So in short notation, I can say x follows the normal with marks mean 60, standard deviation 4. This is my mu, this is my sigma. Sorry, wonderful. So this is wonderful. 70. I put 70 here. Absolutely classic. Eagles of the class. 70. 70. Very good. Very good. Excellent. Mu is 70. Standard deviation is 4. Now this is a bell curve is given to you. Now if I pick up the first sample, let's say I put here 1, 2, 3, 4 and then X bar. I put here. Supposing the first sample which I take, people say 70, 70, 69, 71. What is the mean? Average? 70. Then I take another random sample, let's say 68, 68, 72, 70. What does it mean? Compute that. 69 point, but give me one decimal place, whatever. 69.5. Are you correct? Okay, 69.5. He says that. If it is wrong, you should ask him. 69.5. 140, 208, 278. Okay. Then I have another one here. 69, 71, 72, 70. 70.5. Brilliant. I keep on doing a number of times. Every time I select one X bar, I select a random sample of 4, independent random sample of 4 observations from this population, and I keep on doing that. Every time I compute X bar, I have generated a number of X bars. To be more precise, 60C4, you may say, 60C4 ways I could have generated a number of X bars. Large number of times. To be more precise this. And last, let us say that this is 70, 70, 70, 71, whatever. And this is 70.25. 70.25, I was right. So now what is the distribution of this x bar? If this is a bell curve, intuition says the mean of all this mean, x bar itself is a variable, random variable. What is the mean of x bar? X bar bar. X bar bar, you may say. And my intuition says, if I keep on doing this, given the fact that the original population has a mean 70, whether it is a bell curve or not, the mean will approach, the sampled mean will approach this mean 70. Whether it is a bell curve or not, it is going to happen. Because the same class, if we keep on doing, therefore x bar will approach mu, x bar bar. Now this is a bell curve. x1 is a bell, x2 is a bell, x3 is a bell, x4 is a bell, because they are all drawn from the bell curve. Therefore x1 plus x2 plus x3 plus x4 is a bell. Therefore x1 plus x2 plus x3 plus x4 divided by 4, which is x bar, is also a bell. It's a smaller bell. Compared to the other one, it's a smaller bell. X bar is also a bell curve. Because I am generating observations from a bell, intuitively it is obvious to me x bar cannot be other than anything other than a bell. Now, the standard deviation of x1, for example, if I say his mark is 70, the standard deviation of x1 for this person is 4, because it is identically distributed from a bell curve. So the standard deviation of x is 4. The x is a random variable. It takes values x1, x2, x3. So it's 4. Therefore, the standard deviation of x bar, which is x1 plus x2 plus x3 plus x4 divided by 4, must be smaller than the standard deviation of x. Otherwise, why the hell I should do a sampling? And therefore, I am saying x bar is a bell with a smaller standard deviation. Therefore, and x bar will have the same mean, just now I told, and therefore I will have an embedded bell curve, which is my f of x bar, and this is the sampling distribution foundation. In other words, the standard deviation of x is equal to 4, the standard deviation of x bar is less than 4. What is it? That's a question. Now, intuition says, mota moti, there are 4 observations. So you will say 4 by 2. Am I correct? 4 observations means 4 by 4. 4 by 4. The standard deviation of x bar will have to be 4 divided by 4 approximately. But it is not 4 by 4, it is 4 by root 4. Why? Because standard deviation is a square root of the variance, and the variance of a constant x is constant square times x. When I take the square root, this will be actually mota moti 4 by 4 will be 4 by root 4. When I deal with variance and this, and you simply take it. I don't want to derive it. In other words, the standard deviation of x bar is shrunk, is smaller, and it is inversely proportional to the square root of the sample size. It is inversely proportional to the square root of the sample size, and therefore I have a magnificent embedded bell curve of x bar which has the same identical mean, but the standard deviation is different. In other words, x bar follows normal, 70 as the mean, standard deviation 4 by root 4, which is 2. This is the sampling distribution foundation. Now, the spread here is smaller than the spread here. Do you all agree? And therefore, the curve inside is expected to give a smaller error. In other words, x bar minus mu is the error of the sampling distribution. Call this as E2. X minus mu is the error of the original one, call it E1. In other words, in the original, I have taken no sample, I have taken each one as a sample. And therefore, the error is, suppose somebody says the actual mark, class average, and the x bar, let's say 70, the actual mark, this is 70, but the actual mark is 69. So 70 minus 69 here. When I take a single observation here, it is 68. What is the error? 68 minus 70. In other words, in the original population, the error is modulus of x bar minus mu is equal to E1, E2, and modulus of x minus mu in the original is E1. Because I am subtracting mu from x, I have not done an estimation. Now the question is, which one, x bar minus mu is called the sampling error. Which one has smaller error? Is it E1 or E2? Which is smaller? E2 will be smaller. Why E2 is smaller? Because E2 has a smaller standard deviation compared to E1, which has a larger standard deviation. And therefore, the error is smaller here. And because of this, in statistics, when the sampling error is reduced, the standard deviation of x bar, the statisticians have started calling as a standard error. Otherwise, the term standard error is not required. It is a standard deviation of x bar. So, let me show you here. So, to summarize this and give a little bit of small mathematical expression here, if I have a generalized theorem, if x1, x2, x3, etc., xn are n independent random observations, random samples drawn from a normal population, all these are independent and random, whose mean is mu and standard deviation sigma, and then the distribution of x bar is also normally distributed with mean mu, the same mean, but the standard deviation sigma divided by root n instead of sigma. And because it is closely related to the sampling error, it is called the standard error of the estimate. So the standard error, the term standard error is used not to confuse you, but to say it has a bearing on the sampling accuracy. The sample, how far I can get an accurate result, depends on the standard deviation of x bar and not standard deviation of x alone. In other words, if I increase the sample size, sigma by root n will come down, greater is the accuracy because x bar minus mu will come down. If I increase it further and further, mathematically it can become 0, in which case I will have only one line. That's not possible. It's never possible. But what we are saying is, the sample size to be chosen has a bearing. In other words, the sampling accuracy has a bearing on the sample size, and the sample size, when I divide it by the square root of the sample size, the numerator sigma, it becomes a standard error, and the standard error has a say in the sampling error. In other words, the standard deviation is large, the standard error is large, the sampling error is large. The standard deviation is small, standard error is small, sampling error is better. So, when the original population is normal, the sample size is not a critical factor. Learning takeaway. Because original is normal, even two observations are enough for me to compute x bar. x1 plus x2 by 2. It will still be normal. In other words, if you are dealing in your project something where you are very sure it's approximately, it's a bell, then you can afford to take a little smaller sample size. Even then you can get result. Maybe you will say that I have to do some research with scientists in the CSIR. I have to interview them. I cannot do more than 10 or 15. But if you are sure it is a normal distributed, then you can escape with that smaller sample size. Supposing original is not normal, original is not a bell curve, original is not bell, then is it a hell? Suppose the original looks like this, original looks like this, something like a chi-square, original looks like this. Now this original, which is like this, has all these things here. 60, 70 is this. A distribution like this comes. I cannot say every population is normal. Supposing it is not normal, what will you do? This was the problem the world faced. Statistics would have come to a grinding halt, or there was a dark age of statistics. Then came the Lindeberg-Levy central limit theorem. What it says is sample size becomes critical now. Even if the population looks like a camel, donkey, horse or anything, from that population, if I draw independent random sample of size n, whose mean is mu, standard deviation sigma, then the distribution of x bar is still a bell curve, no matter what the shape of the original population was, provided the sample size is large. So now we will move to another fascinating area, decision making under conditions of uncertainty, probability. So I propose to do probability and the bell curve this time. Whether we have time for the binomial and the Poisson, you can read it, but I'm going to concentrate first on probability principles. I'm going to experiment with you some simplified way of doing probability. Only after the experiment, if you feel it's simple, you can use, otherwise you can use a formula and get it. But I'm going to do something else today for the first time with you. And I generate this with the idea, in the morning I must thank some people, when they saw me in the sofa, the melancholy face, they were a little worried and all that. And that gave me a hint that let me reposition based on the behavior of even a couple of people to do a full review in the form of this with one exercise, and we learn. This is called assurance of learning. This is one of the components required for AACSB in the US to do accreditation for a leading business school in the world. That are people really learning? You are claiming you do this, you do that. Assurance of learning. The assurance of learning is actually you are doing. And we have evaluated after you have done. And I am reasonably satisfied you have learned a lot. It's not that you have done a bad thing. All of you have good knowledge. So let's now move to another fascinating area, the probability part. Now, everything is uncertain. You have to make decisions. What will happen to the oil prices? What will happen to the petrol prices, diesel prices going up? Will it come down? Will it go up further? And what is the economic crisis? Have we completely come out of the effect or impact of demonetization? Lot of questions are there, uncertain things. Who will win the next election and all kinds of things. So there is nothing you and I can do about uncertainty. Everything is uncertain and you still need to make decisions. So decision making under conditions of uncertainty, you are talking about a fascinating thing called probability. Now a classic definition of a textbook definition. Typically, I will come back to this later. You have all done probability. In fact, if I tell you the problem, you will immediately answer also. All that is fine. But I am going to do something else today. I ask you a question to you. What is the probability that somebody born in this world will live 1000 years? A human being born in this world will live 1000 years. Huh? No. What is the probability that somebody born in this world, a human being, will live 1000 years? So what do you say? Very low. Huh? Approaching zero. Why do you say approaching zero? Correct. So if I paraphrase what all you have done, the 3 or the 4 statements which I have heard from the participants. One is, it is data driven. We don't have data today that says somebody has lived 1000 years. So based on the data available currently on the basis of the medical records all over the world, there is nobody to the best of my ability I know of who has lived 1000 years. And therefore it is unlikely an epsilon, a zero, closer to zero. When you say closer to zero, you are giving some chance 1 out of something, fellow. Therefore, otherwise you could have said 0 by 0, closer to 0. You have said that. So, empirical probability, data driven probability is empirically evidencing. That's one type of probability which is in practice we are using. Now, actually, William Feller, in the year he wrote a classic book, emeritus of the Princeton University, mathematician, probabilist, authority in probability, volume 1 and 2, Introduction to Probability, William Feller, the famous, very famous one. And not a comma has been changed ever since that was written in the 50s. In the first chapter, he asked this question. He, based on the world population in 1943 when he wrote that book, based on a model called the birth and death process, he said the probability somebody will live 1943 population he has taken, and census, and you know the census population is also not exactly accurate, because how many people you would have exhausted in the tribal areas, hills, how many people are homeless near the railway station, behind, back. So that's also not complete, but nevertheless the census population of the world. He says the probability is 1 upon 10 raised to the power 10 to the power 10, which means based on this model, Feller says it is 0.00 20 billion zeros under 1. That means if you start writing, as I told you yesterday, zeros, next 3-4 days there will be complete traffic jam in Bangalore. You will not be able to leave this HSR layout. Nowhere you will be able to go. You are stranded here. He wrote this empirical thing. He proved it's a data driven probability. Somebody said it is absurd. Absurd. All right. Then Feller is asking, can you give maximum lifespan for a human being who is born today? What is the maximum age a person will live? There is no standard. Somebody has lived 120, 110, we are saying all that. But you cannot say maximum lifespan is only this much. There is no standard. So somebody in Russia, somebody lived, let's say 130 years. If we take that as the maximum, so far, but if you take that as a maximum lifespan, 130, because somebody has lived 130 years old, Feller argues, supposing you say that, that is not exactly a maximum lifespan anybody will live, but somebody has lived. Suppose you take that as a standard maximum lifespan, then somebody has already crossed 129, you put some 8 or 10 people around him, including some doctors, emergency and all that, is going to complete 130 in the next 20 seconds. 129 years, everything, 365 days over, last 20 seconds, everybody is waiting. Something, emergency and all that. So 9, 8, 7, 130, out! He is not out. He may not be out. So we are waiting, out, 130. That's not going to happen. So it is equally absurd. In other words, I can't have a standard even today from the medical records that so and so will live maximum only this much. There is no standard. And therefore, I can always determine only empirical way at that particular point in time the world population. Then I rule out the possibility I cannot make it 0. So 1 out of this, if at all it happens. That is the logic of William Feller. The idea of saying that is it's an empirically driven probability. So some of you said data right now it's like this. You are only strengthening the argument of William Feller. And closer to 0 you said, William Feller says 1 divided by 10 to the power 10, 1943. Suppose 2010 you are putting this, it is 1 divided by 10 to the power 10 to the power 10 to the power 10, maybe. But the reality is, based on the census and the data, the probability is called empirically driven probability. That we use in life. Data driven probability, empirical probability, or relative frequency probability. Relatively, what is the data I have? 130 days, 300 days machine breakdown data I have. 100 days it has got the 0 breakdown. So many days it has 1 breakdown, 2 breakdown. Empirically I am determining what is the probability it will have a 0 breakdown, 1 breakdown. So this is empirical, data driven, which we all do. Last year I had got so much sales, let's say 20% market share. Given the fact that I got 20% market share, what is the probability I will exceed the same 20% market share? I will be able to work out based on the data. This we do day in and day out. Even though the order I put here, this is empirical. Then there is subjective probability. I learned. Initially I don't have any data. I call some experts, like a Delphi technique. Opinion makers, experts I call, and then ask them, what is the chance that such and such thing will happen? The steel prices will go up or down. Some experts come and they give some probability, likelihood. Then you, based on the consensus and the averaging it out, you say that this much is the chance. The experts feel like that. The experts can also make mistakes. They bring with them likes and dislikes, prejudices. But we believe the experts as a starting point. They are experts, we are not, so we call them. That's called subjective probability. That which is subjective. Once we start the subjective probability, in the light of information data that becomes available, I revise this subjective probability, which is called the posterior analysis. I improve my hit rate, my success rate. The revised probability is the contribution of Bayes theorem and all that you are saying. So I learn, I start with some probability. It's somewhat subjective based on experts, let's say. Then a learning curve. I learn how to improve that probability. When the new information comes, I try to plug in and revise this. Now look here, this is changing. This is subjective probability. In radial tire many years ago, people said there is an analogy, such and such company has failed, therefore if you go for that, you'll have to factor that into account. So this is subjective probability. Then a priori classical probability, some rules are there, rules of the game, addition theorem, subtraction, independence and all that, and that we apply even here. But these are classic probability where I have a rule. That rule is axiomatic and I apply those rules for solving a problem. So a priori classical probability, empirical probability, subjective probability, the three probabilities that are there. And in the classical probability, you will say in a pack of cards, some card is drawn, what is the probability, king, diamond, so many things you have done. In fact, that is one wrong way of starting sometimes the example, because 42, 52, people will start giving the answers. So the charm of probability is lost. But then sometimes we understand, toss a coin, what is the probability, it will be a head, you will say ha ha ha, it is half, very easy, you will say. But if the coin falls like this, it has to be an unbiased coin. So all those things are there. That is a classical probability definition. Now let's say a probability by and large to an executive is a ratio between two numbers. I will prove to you, only if you know this is enough for solving every problem in probability. No other rules are required. Even though I may tell you about the rules, we will follow the Boolean methods and very easily we can solve some interesting problems. Then you will say, oh my God, it is so easy. It depends on how you take the Boolean thing, very simple rules. But everybody knows probability is a likelihood, is a chance an event will happen. A ratio between two numbers m and n. M divided by n. M is the favorable cases to the occurrence of A. N is the total possible outcomes. So the ratio M upon N is the probability. That which is favorable to the occurrence of A to the total number of possibilities are the outcome. And therefore probability, such a definition warrants it has to be a pure number. Probability cannot be in kilograms, 0.2 kilograms and all. There's something wrong with us. It's a pure number between 0 and 1. A number can be 0 at the extremity, can be 1 at the extremity, but it cannot be more than 1, it cannot be negative, a pure number, 0 to 1. Sometimes art of exaggeration, we say, I am 200% certain. You are only 100% certain. It cannot be more than that. But still you say art of exaggeration. That's, I am very certain. 100% certain you can say. You cannot be 200% certain. Still, colloquially we accept it. I am 200% sure. How can you be sure? We don't want to pick up an argument on that, but we say all of us, but probability cannot be true. Similarly, we say I will try my level best. There is no level for best. I will try my best. Isn't it? These are expressions to emphasize what we are doing. In colloquial form, it is accepted. So probability is between 0 and 1. It's a pure number. And then an analogy I have drawn, a tumbler. Half empty, full empty, 0, half full, 50-50, and glass is full, 100% chance certainty. So the analogy, when you say the probability under extraordinary conditions can be 0, can be 1, can be 50%, but it's always a number between 0 and 100. Impossible event, certain event, and 50-50 of Amitabh Bachchan, isn't it? You've heard the Kaun Banega Crorepati. If you have watched the first 100 episodes when it started, it was brilliant. First 100 episodes. So in the first 100 episodes, somebody is trying to win the Crorepati. A lady from Maharashtra, I think, came, Alka, if I remember correctly. The lifeline is given sometimes. And she was coming, maybe she could have won the crore, whatever. But in between, Amitabh asked a question she was not able to answer. Lifeline? Want to use a lifeline? Ask that. 50-50? Call a friend? Audience poll? So audience poll is relative frequency, data driven. Based on the audience, what they say. 50-50 is the 4 choices are there. You remove 2, any 2 you can make a guess. Call a friend is subjective probability. You believe the friend. Now, 50-50. Then Alka did not use it. Oh, Alka, it's a wrong answer. And you know the case. That somebody else won that. Later, when he is asking lifeline, 50-50? Yes, 50-50. Computer Maharaj, he will say, and then there's 2 choices, some music will come, 2 choices are removed, only the other 2, they will make a guess. So, when you are doing a multiple choice question, if you are sure 2 choices are definitely wrong, you can make an intelligent guess. That's 50-50. So, these are the 3 rules. Now, therefore, probability is a ratio between 2 numbers, m upon n, which is m is the number of ways that are favorable to the occurrence of A, n is the total number of possible outcomes. So such a ratio is called probability of an event. So A is an event. So what is an event? An event is any phenomena or phenomenon which you observe. That's an event. An event is a phenomenon which you observe. The process by which you observe the event is called an experiment. The set of all possible outcome of the experiment is the sample space. That is mathematical definition of probability. So probability is an occurrence of an event. An event is a phenomenon that I observe. The process by which I observe the phenomenon is called an experiment. The set of all possible outcome of the experiment is the sample space, which is the mathematical definition of probability. All these things are a derivative of a classic concept called probability. An event, phenomenon, process by which I observe the phenomenon is an experiment. The set of all possible outcome of the experiment is a sample space. Mutually exclusive. Immediately we come to the Venn diagram. Then we say king, queen cannot be at the same time king and queen. So they are separated. There is no common point. Everybody does this example. And I want to caution you at this stage, this Venn diagram will work well only for one or two sets. More than 2 groups, 3, 4, 5, it will be Battle of Kurukshetra. You will not be able to solve problems using the Venn diagram easily. It's hard. But an initial understanding. So what is mutually exclusive events? The occurrence of event A prevents the occurrence of B, or B prevents A, one of them. Both cannot occur at the same time. It's a strong case of dependence. So if A prevents the occurrence of B, or B prevents the occurrence of A, then they are mutually exclusive. Both cannot occur at the same time. Several examples are there. Independent. A and B are independent events. A cannot exert any impact on B. In no way A will influence B or get influenced by B. They are independent. So you simply say toss a coin. Some examples you give. There are several examples that are possible. With another small classic drilling example of a Bayes theorem. When we were graduate students in the Loyola College, Madras, that Bayes theorem, at least the formula to look at it is frightening. First time in the college, the calculator and all are not there, the facet machine and all. In the exam, you'll have to use only, we were allowed slide rule, that numerical mathematics paper, but this paper, no slide rule is allowed. You have to calculate by hand something, 2 decimal place, whatever. And Bayes theorem application will come. Some example, 2-3 problems. I honestly, I can confess to you, I really did not know how I was doing. Some formula like this we were applying and doing it. After the exam, it was my practice. I will go home. I will never discuss my solution or question with anybody because I should think I am right. Otherwise, next day you will spoil your mood. But the other students who are my friends will not leave me. And they will be upset when I say I have done this. Oh, then we are wrong. So either way, it is a problem. But nobody had a clue whether our answer is right or wrong when it is Bayes theorem. Because the problem is probability of A given B, B given A, sigma probability, denominator they put a sigma also. Complete confusion, confounded. At least we were not able to understand. But we were doing the problem correct. So the question which I am asking is, what is peculiar in this expression? If you look at it as a layman, let's say you are going in the elevator. I am asking you what is peculiar in this expression that you cannot miss. That's the only fulcrum or the heart of Bayes theorem. The famous mathematician in the 17th century. What is peculiar here? Ulta. So, you have B given A, you are interested in that. But I cannot compute B given A unless I know A given B. A given B is called the prior probability, conditional probability, it is given to you. A given B means A is out of B. Boolean rule you should remember. A is out of B. Forget the subscript. A is out of B. But you are given B is out of A. In other words, B is out of A is called the posterior probability. I am revising the probability based on initial conditional probability and prior probability. This is given to me. I have to make use of it to get this, but this is not helpful to me. This is not helpful to me, but I need this nuisance, then only I can get this which is helpful to me. So in other words, inverting the probability is information power, is the hallmark of Bayes theorem. Let me give you 1 or 2 practical examples. In market research, you go to an agency for a new product development. Whether I should introduce the new product or not, I have to do. I have some prior information with me. 40% of the time the new product will be successful, 60% of the time it is a failure. Only that much data I have. So somebody says go to an agency and find out. They can predict it better. Okay. So the agency says, when I go to an agency, I also want to have some idea what is their reputation, how well are they capable of their competency, all that I want to know. So I have a hunch. Agency, let's say 80% of the time, agency predicts success. Given the actual state of nature is also a success. 80% of the time, agency predicts success given success. That is, out of the success time, 80% of the time they are right. 20% of the time they go wrong. 20% of the time they predict failure, but the actual is a success. They are wrong. In other words, I have data, agency predicts success given it is a success. Out of that success, 80% of the time they are right. This information I have. But what I want is not that. I want success given agency predicts success. Because that helps me to know whether it is worth employing the agency. So ulta has a terrific meaning. This I discovered unfortunately only when I started many years ago teaching as part-time in the International Management Institute, Delhi and all that. At that time only I started reflecting how to conquer the puzzle in Bayes theorem, what exactly it is. Then I realized it's a powerful tool. The inverting concept is Bayes theorem. But if I use the Boolean, I can solve without any problem. The rules and the association principles, I can have more than two class. I can say successful, can't say unsuccessful. The rules work same way. It is the association rules. Straight away. I need not always have a binary. I can have more than two classes also, it works. It will be A, S1, A, S2, A, S3. 3 classes. Same formula. 20 classes, same thing you can do. So the drilling company has estimated 40% chance of striking oil for the new well. A detailed test has been scheduled for more information. And historically, 60% of the successful wells have had detailed test. 20% of the unsuccessful wells have had detailed tests. Given that this well has been scheduled for a detailed test, what is the probability that the well will be successful? So the first one deals with detailed test given success. The second one question that is asked is success given detailed test, ulta, so that I can find out whether the detailed test is worth doing, soil analysis, the geological survey, spending money on them, is it worth? So is this information worth? What is the value of information? How can I financially quantify? Bayes theorem will help. But the Bayes theorem basic principle is inverting the probability. That inverting helps you, but to solve the problem, I don't even have to know by the name Bayes theorem or this. So what questions I will ask you is, what is this 40% chance of striking oil? Supposing I say S is equal to successful, US is equal to unsuccessful. S is equal to successful, US is equal to unsuccessful, then US. Successful wells, let's say they are 40, am I correct? Unsuccessful is 60. Am I right? Striking oil for the new well. In other words, probability of S is equal to 0.4, probability of US is equal to 0.6. These probabilities are called prior probability. In other words, let me explain, 40% chance of striking oil. So striking oil is successful. Not striking oil is unsuccessful. I can have one more, can't say, but here 2 outcomes. So historically, so this information is given. So probability of S is 0.4, probability of US is 0.6. If I use proportion, S plus S bar, US I can call it as, let's use the term here S bar. S bar is 60. This is S bar is 0.6. So if I use the Boolean rules, S plus S bar is 100 if it is frequency, S plus S bar is equal to 1 if it is a proportion. I just, whichever way convenient, you can use it. Now what it's the advantage of using a rule here is, let's say here detailed test, no detailed test, D bar, S and S bar. If I have, this is my DS, this is my DS bar, this is my D bar S, this is my D bar S bar, as before. Now the question says 60, 40, this total, this is 60. The question has clearly said that. Correct? Historically, 60% of the successful wells have had a detailed test. That means I can write this as 24 without any doubt, because 60% of the successful wells have had detailed test. The number of wells that are successful are 40. 60% of 40% is 24. 24 wells underwent detailed test. Am I right? And 20% of the unsuccessful wells have had a detailed test. So 20% of 60, this is 12, have had detailed test. Am I right? Now this is equal to 36. This total. Now I can complete the table, but I don't need to complete for answering the question. Still I will complete the table. If this is 36, can anyone say this is 16? Can anyone disagree this is 48? So association of attributes, all the terms are there, but primarily the question is, now when I multiply this 60 with this 60%, effectively what I am doing is joint probability. What I am saying is, I have got data, detailed test given success. Because successful wells alone, I have done the detailed test. But what I want is successful given detailed test ulta. So the question that I want to answer is probability of, what is that here, sir, madam? Question, given that it is well is detailed test, what is the probability to be successful? So S given D you want. You want S given D. Now what is D? D is equal to DS plus DS bar. So D is equal to DS plus DS bar, which is equal to 36. Now S given D probability, DS is the only term which is associated with success. Because I want success given detailed test, the second term it is not associated, and therefore the required probability is DS divided by DS plus DS bar, which is already 36. DS is your 24. 24 by 36, 2/3. Enjoy the solution. This probability is called the posterior probability. In other words, what is 24 by 36? 2/3? 0.67? 2 decimal places? What was your previous probability, prior probability? 0.4 prior probability of success. Initially with my data, I have a success rate of 40%, which is my prior probability. Now, using the Bayes theorem, I have got a better success hit rate, which is 67%. Therefore, prima facie, cost considerations being taken into account, it is worth doing detailed test, because this probability is much higher, which is the singular contribution of the great mathematician Bayes theorem in the year 17th century. But the basic principle of Bayes theorem is, when I multiply this by 60%, it is the prior conditional probability. Out of the 40, 60% underwent detailed test. So 60% of 40. So detailed test given success. Into success I multiply. Whereas I want success given detailed test. Without going into the conditional probability terminology, by now you would have realized you can use the basic principles and solve any problem. There is no problem any problem you can solve. There is no problem for you to solve any problem. And if you have understood, there is no problem at all to solve any problem. And see this expression here, DS alone is associated with success. And what have I used here? Basic principle, my dear friend. Number of ways favorable to the occurrence by total possibilities. Frequency approach I have put here. You could have put proportion also. Same thing will come, my dear friend. This is a different problem. I will reserve it for me to ask you. This is a 3 case. Instead of 2 outcome, 3 outcome table, I leave it to you as a homework or a test in the thing and fill in the blanks so that some tougher question can be given to you in some other test. Not tough. One more. Same principle. Marginal probability, conditional probability, A or B, A and B, joint probability, simple probability, Boolean rules, counting, proportions, signed, sealed and delivered probability. The basic foundation. Now you can do anything. I feel you are a wall of China or rock of Gibraltar. Should not have a problem. The last part, this residency, I am planning to give you some concept of the bell curve and stop. Because next time when we visit, we will have to have some hypothesis testing and all that. So let us just address the bell curve, and I will do one problem only, example problem, leave it there. Because it is also extremely important, bell curve. Probability rules, I want to start here and then go to some Boolean principles, and then you may laugh at them. You can easily solve. When they are mutually exclusive, you are saying A union B, probability is probability of A plus probability of B. The sum of the individual simple probabilities I am adding. Some textbooks say A or B. Technically it is correct. A or B means either A or B or both. But both will not occur when it is mutually exclusive. If A occurs, B will not occur. If B occurs, A will not occur. This is mutually exclusive. I'll just come. If A occurs, B will not occur. If B occurs, A will not occur. Both A and B will not occur in the case of mutually exclusive. But when they are non-mutually exclusive, it can occur. We will come to the examples and then it will be clear to you. First of all, mutually exclusive means A or B. Either A or B in set theory and or mathematics is A or B or both. But both will not occur when it is mutually exclusive. I'll just give you several examples. If you say percentage people who have paid income tax is 40%, 60%, 70%, then 30% of the people have not paid income tax. So paid income tax, did not pay income tax. If I have 2 classes, they cannot be at the same time occurring. Only one of them will occur. If a person is a complier with the rules or not. Now a sampled space can be thought of as an exhaustive, mutually exclusive, completely exhaustive set of events. That depends on how we attack a problem. When they are not mutually exclusive, some formula comes here. A union B, probability of A plus probability of B minus probability of AB. A and B. This is what all of us have been taught something, and we are doing that. Everybody knows this. Let me take one example. Again, first from the cards. What is the probability from a pack of cards if I select one card at random? It is king or a queen. So, you will say here probability of king or queen. So, okay, or I put a union because we have got a set theory thing here. And straight away, we write here is equal to, I know you know the answer, just give me some time, I will make it a little different, plus probability of queen, which is equal to 4 divided by 52 plus 4 divided by 52. You can simplify 8 by 52, 2 by 13, I am not interested. In fact, I gave one example, this is 8 by 52, I just multiply the numerator denominator by 3, 24 by 156. They said none of the above people wrote. Because I gave one of the multiple choices as 24 by 156, which is same as 8 by 52. Then they were angry with me. I said, you should discover 24 by 156 is same as this. So let's not simplify, let's leave it. So this is the answer, 8 by 52. The second one, you are saying probability of king union diamond is equal to probability of king plus probability of diamond minus probability of king diamond, which is equal to 4 by 52 plus 13 upon 52 minus upon 52. When I had the opportunity to work with a top person in the industry, was a director and a brilliant man. He had very limited time, but he was curious to have interest in quantitative ability, statistics and all that. So you say during lunchtime or tea break or something, I'll have some 10-15 minutes to devote. So simple concept every day you should tell me and give some example. Simple concepts I want to know. A terrific business sense. When you take a report, you can say that there is a flaw in the report without knowing the subject, but practical validity. He had the ability to have the seventh sense. So the time limited is this and very busy. So very simple concept. Explain it with anything you like. Where the curiosity. This problem. He put a question to me. Why are you subtracting this here? King and diamond this, and you are doing something. Confusion. First one I understood. King or queen. Why are you subtracting? What is your answer? Huh? You are in the elevator exercise, my dear friend. 30 stories it has to go, and he has to understand. Double counting. You are saying, why are you counting twice? He asked me a question. Why not you properly count? Supposing I say, because he is a great person, even this simple thing, I can't. You can't say that. Tell to your superior. That's one. Second one, the question made me think. Why are you subtracting? You said double counting. Why can't you count properly? What is the answer, sir? This has happened. I am sharing with you. And you may have to communicate to people who have got the extraordinary business sense to you make use of you. This is where all of us have to rediscover our strategy. Why are you counting twice? That question made me a different person from that day. It happened some 25-30 years ago. I will never forget that. And that question is not a stupid question. Why are you counting twice? Why can't you count properly? I know only formula, I do this. Now, if you use the Boolean principles, forget all this set theory and all. King or diamond is equal to, I am not using probability first. King without a diamond, KD bar, plus diamond without a king, DK bar, plus king diamond. K or D is equal to, either K will occur, in which case D will not occur, that is D bar. D plus D bar is equal to 52, the cards. Is a frequency. Either it is a frequency, if you are using frequency, you can use D plus D bar is equal to 52. If you are using probability, D plus D bar is equal to 1. So, king without a diamond, diamond without a king, king and a diamond, only these three possibilities. This is equal to 3, because one diamond is not there, plus 12 plus 1. Only once I have counted, which is equal to 16. Therefore, the probability is 16 by 52, because definition says favorable event by number of possibilities. Number of possibilities is 52, favorable is 16. I use the basic principle of probability and convert this. He has understood. You get the point? This is the crux of the matter. Anybody in the world will have no confusion. I have reduced them to mutually exclusive, collectively exhaustive events. Now I will show you KD bar is equal to, you know, K is equal to KD plus KD bar. Association. Either it is associated with the D or without this. Therefore, KD bar is equal to K minus KD. KD bar is equal to K minus KD. Now dk bar is equal to D minus KD. Therefore, if I substitute here, this expression itself will be K minus KD plus D minus KD plus KD, and kadak it cancels, K plus D minus KD, which is your formula. The formula itself is derived only from the Boolean. Why the hell you highlight the formula and confuse the word is the question which you will have to answer. You don't need it. You don't need this formula at all. You can solve. Very simple. A or B is always equal to A plus B minus AB. If AB is independent, it's a null set, finished. It's a Boolean rule you apply. Why do you want to confuse the world by a formula? The question I am raising to you now, based on the question that my superior asked, why are you counting twice? Why not once? Why can't you count properly? So you can do this problem like this also. But to a standard audience, they will say, why not we use some thing, it's not, the formula is not wrong. To satisfy them, we have to say the Venn diagram, and you will say, this is the intersection, all this. This is uninteresting. That is one probability can be done. You agree with that? And later I will show you some complex problems. You can do it with a decision table and Boolean rules. And that today is called association rules. In R they are writing some computer program. Actually, I was laughing in the bathroom when I was taking bath. I was thinking about a problem. Then wife said, what is wrong with you? You're laughing. I said, no, I'm thinking about a problem. You won't understand. The association rules. And these people are using this 1950, Yule and Kendall wrote a book called Association of Attributes. And the same thing is being used today with R. It is 68 years old. And our Bhaskaracharya Leelavati in India has done this many years back. We have not documented. So I'm just laughing. Now I find a new opportunity to teach this, our probability and rules. It's a remarkable thing. They have discovered it long back. This Yule and Kendall's book in British Council, when you go, there is one chapter called Association of Attributes. Some statistical tests are also used, chi-squared and all. But if you learn that Boolean thing, principles, he is using some Greek symbols. A is the presence, alpha is the absence. I use A bar, but the same thing. You will be able to do all kinds of problems on probability without an iota of doubt. Even the so-called Bayes theorem, you don't have to know by the name Bayes theorem, but the problem can be solved by you, which I will demonstrate to you today. And I am trying to write a book on discovering probability, some new ideas and insights using some of the old Boolean principles. Bhaskaracharya Leelavati, he is singing a song, Leelavati is dancing and solving indeterminate equation. But we should learn from the West the documentation. They are masters, they have got everything documented. We are very poor in that. If we document, even the Western world will appreciate and take this in their curriculum. But we are not documenting. It's all very simple rules. And Yule and Kendall, 1950, is the person who inspired me. And I will show you it is easy to do probability. I'm just a demonstration I'm giving you. And this, the trigger was my superior asked, why are you counting twice? Why can't you count properly? I will never forget that statement. And any other person would have told you don't even understand basic probabilities, double counting, single counting, subtract. And you are in the danger of losing the job also. You cannot talk like that to your superior, right? However, you may think, right? See, only it will be difficult to deal with a very simple concept. Supposing I say you should draw some scatter diagram to a person who does not know x-axis, y-axis, then it's a problem. We assume people know x-axis, y-axis, isn't it? To that level we can go, but anyway, it's a basic thing. Now let us look at independent events. When the events are independent, you multiply the probability, simple probability, A and B. Everybody knows, am I right? The whole world knows. Several examples are there. Pack of cards, or some two events are independent, multiply. B given A. This is another area when the events are not independent. You multiply probability of A with B given A, or probability of B with A given B, depending on which one has occurred. If A has occurred, it will be probability of A into B given A, or B has occurred, it will be probability of B into A given B. And this probability is called conditional probability, which is information power. And to understand the conditional probability, let me just say here, what is this expression mean? Let's say B given A. What does this mean? The question is asked you. You are multiplying. B given A is the condition. A has occurred. I want to find what are the possibilities in which B will occur given A. That means B should be out of A. B should be out of the population A. I must have counted. That is the basic principle of Boolean rules. B is out of A. B is out of A. Are you with me? B is out of A is important. I will tell you an example. Supposing you go for a master checkup after some age. There are a lot of vulnerabilities, health hazards and all that. And above 50 years old, they say you have to go for that. And you go with the report to your doctor, your physician. And they are saying that your age group, the probability that a person will have a heart attack is, let's say, 11% or 12%. 12% chance of a heart attack after 50 due to the age and the conditions. There is a record. That means I have a medical population of people in the age group of 50, and that population 12% are vulnerable to heart attack. That is the meaning. Am I correct? It is not to the entire thing. The population of above 50 years old. Okay. Then family history, and something is asking, oh, you are a diabetic. Then heart attack given diabetic. See, heart attack, if I represent this as a proportion or a number, it is 12. Let's say 12 out of 100. Now heart attack given diabetic. That means the doctor will take the diabetic population, and in the diabetic population, the first is the diabetic population is also above 50. That is there, part of that. In the diabetic population, how many people have a heart attack? You get the point? That is conditional probability, which tells something to the doctor. Not only, my dear friend, there is vulnerability, you are a diabetic also. Oh, you have cholesterol. Then heart attack given diabetic cholesterol. Then finally, what does he say? Some black tea in the morning, or a black coffee, or something without sugar, no fruit, no juice, no root. And some continental breakfast we want. Shuka bread, something, some toast without butter, no cholesterol. That is given. Black coffee, and Mari biscuit is allowed to, with a tea, something like that. Then one small bowl of rice for the lunch, 2 shuka chapati, little bit of dal. And you can have some cucumber. Not interesting. That's all it is. Then he says you have to jog. How can anyone jog? All this. Whole thing is gone. But condition probability is UC. Because the doctor has the medical record, above 50 years, how many have diabetic, non-diabetic? And in the diabetic, how many got heart attack is heart attack given diabetic. So the conditional probability is out of the population of A, how many B are there. So this is the basic principle of conditional probability. You get the point? The first problem is an interesting problem. Suppose you are running some club and all that. Smoking, drinking, all these are there. I do not know how many in the class are smokers and those who drink. I am a teetotaler. So you are talking to a wrong man, but I got a right example. These are counting problems. And how do you handle a problem of this nature? And let us put this, probably some of you can solve. Supposing I ask you an algorithm, the recipe, the step-by-step method of doing the problem. We are going to, in other words, use the basic probability principles, marginality and all that in an intuitive manner. An experiment which I am performing with you, and with your help, we can conquer the world. We can disseminate knowledge in an entirely different way. It is not that we are doing everything completely new, no, but we are simplifying some of the very complex things in a highly heuristic and intuitive manner using some basic principles of Boolean rules, which are association rules or association of attributes today. People are using software today. Lift confidence level, lift ratio, support and all that they do. And look at this problem now as a counting problem. Some of you might have done similar questions, problems. But the question I will put that is, if this problem is given to you, can you program it? Can you automate it? In other words, it's not so much the answer which you are giving, but how do you approach the problem? How do you solve a problem? And you may develop tomorrow your own algorithms. We will popularize it because that is the way we march forward. Knowledge creation from your side. Out of the box thinking somebody has. Any one of you may have. Develop that. And problem solving, puzzle solving skills, creativity are the three ingredients required for success in analytics jobs. It's not simply doing something from a book. And some of this we discuss may not be in a traditional standard book, including the book which I have written with some authors. I want to revolutionize education and make things easy with your cooperation because you are the ambassadors. If I am able to prove to you that you are able to follow, look at this problem. 37 men and 33 women are there. Total 70. 36 are teetotalers. Completely abstain from alcoholic beverages. That means they can smoke. They can smoke. A teetotaler is one who is only from what I would say abstaining from alcoholic thing, but not necessarily a non-smoker. He or she can smoke. 9 of the women are non-smokers and 18 of the men smoke but do not drink. 13 of the men and 7 of the women drink but do not smoke. How many both drink and smoke, and what is the probability? What is the probability is straightforward. Suppose we say how many both drink and smoke is what you have to solve. When this problem was given to the last year, some full-time students and all that, they said you are always like this. They tried with the Venn diagram and all the circle, and they were coming in the corridor when I was coming, smiling at them. You are always like this. You gave some problem. We were not able to. That problem is gone and all that. Out of syllabus. It is not out of syllabus. But then the emotion. Then, in order to motivate them, I also did with the Venn diagram and all that. Then, when this method was told, the students were jumping with joy because it's so easy to do. Now I am asking you, whatever method you do, you can solve the problem. But that method must be capable of being instructed to somebody to develop a kind of an algorithm where I can do it. That you should be able to tell me. You get the point? It's not the answer I'm looking for. Probably you can solve. All of us can solve. But how do you go step by step and how do you solve this? Supposing 36 are teetotalers. Let's start with that. Supposing I say here M for men, M bar for women. Isn't it? Supposing I write here M for men and M bar for women. M plus M bar is equal to 70. M is 37. And then M bar is 33. Okay. This is the total. This is the frequency approach because here counting, everything is counting. 36 are teetotalers, the facts are given. They don't drink. So can I say D plus D bar is equal to 70 total? Those who drink, those who don't drink. Now in this, what is D bar? 36 people are teetotalers, so this is 36. Am I right? Therefore, D is equal to 70 minus 36 is equal to 34. You agree? You agree or disagree? Okay. Now, no, I told you, you have not heard, I repeated twice. They are teetotalers does not mean they will not smoke, they can smoke. Only completely devoid of alcoholic beverages. Now, D is equal to drink. Now, drinking is associated with smoking without smoking. Am I right? So, drink is equal to, let us say S is the smoker, S bar is the non-smoker. So, S is smoking, I can have S plus S bar also. S is smoking, S bar is non-smoking. So, D I can write it as DS plus DS bar. Yes or no? It is associated with smoking, it is not associated with smoking. Attributes. In other words, I just construct the table D, D bar, S, S bar. I look at the combination. Now, this is already given equal to 34. Do you agree? This is 34. Yes? Since this is 34, I want drink and smoke has to be 34 minus DS bar. You agree? From 34, if I subtract DS bar, I will get drink and smoke. Right? All of you agree? D is associated. I have a D here, drinks, smoke, not smoke. So this is DS and DS bar. Marginality principle. Drinking is with smoking, without smoking. Possibilities are there. Because the attributes are gender, drinks and smoke. We are dealing with attributes now. So DS plus DS bar, from this 34, if I subtract DS bar, I have solved the problem. I have solved the problem of DS. Am I right or wrong? DS. Is it correct? Okay. Now what is this DS bar? Now listen, 1 minute. DS bar, 1 minute. That is true. This drink and not smoke DS bar, which I want to solve, can be among the men and the women. So the DS bar is equal to MDS bar plus M bar DS bar. MDS bar plus M bar DS bar. Now look at the question. 13 of the men and 7 of the women drink but do not smoke. 13 of the men and 7 of the women drink but do not smoke. This is drink but do not smoke occurs among this, and therefore this is 13 plus 7, which is equal to 20, and hence the answer is 34 minus 20 is equal to 14, and hence the probability is 14 divided by 70, which I have answered. Therefore the probability is favorable occurrence 14 divided by the total. I am using the basic principle of probability, ladies and gentlemen. The probability of an event is the ratio between two numbers. I am using this. M is favorable to drink and smoke. Total possibility is 70. 14 by 70 is the probability, signed, sealed and delivered, the famous Boolean principle by which we can solve the problem. And now you have not made use of 9 of the women are non-smokers, 18 of the men smoke but do not drink. That information is not required here. But logic, drink, do not drink. Drink is equal to drink smoke plus drink do not smoke, S bar. Therefore drink and smoke is equal to 34 minus DS bar. Now DS bar is associated with men and women, MDS bar plus M bar DS bar, or DS bar M, DS bar M bar, whichever way you take it. So you got the answer. Subtract, enjoy the solution. This is introduction to another way a simplified way of looking at problems, and very complex problems you can solve. And if you are able to define all of them, then find out the association. You can have more than 2 classes, 3 classes, everything. The rule works very well. And this probability, this total is called the marginality principle. I am marginalizing D based on S and S bar. In other words, primarily it says D, D bar, S, S bar among men, and then D, D bar, S, S bar among M bar. I have that association. It is associated. So I can construct even a 2 by 2 small table. If I don't follow that, I can just write all the entries there, DS, DS bar, everything, and enjoy the solution. In case this intuition I want to further expand and understand, I can create T, D bar, S, S bar, men, D, D bar, S, S bar, M bar, and plug in the numbers, and I have clarity. I can do that. I don't need any formula per se from a textbook, but I use the fundamental principle of William Feller's probability as a ratio between 2 numbers, mutually exclusive, collectively exhaustive. We can solve that. Is single or has a college degree, A or B? If you look at the last one, A or B, single or has a college degree, that is A union B type of a thing, A or B, but using some basic principles, can you solve the problem? That's a question which we'll have to answer. So when you have to think about it, probably you have an answer, but what I'm saying, how do you handle this problem? A frequency approach. How do you handle? In other words, this example deals with A or B type, either single or has a college degree. Supposing I put here M bar. M bar is single, M is married. Then I put here college degree D and D bar. Okay? And this is MD, MD bar. This is a joint probability principles, MD, MD bar. This is M bar D, M bar D bar. This is given. And from the total, the marginal total, this is a total. Let's just keep this at the back of the mind. Those who are single is 100. So this total is 100. Am I right? And there are 600 people. If 100 are single and the total population is 600, we can say 500 are married. Am I right? That is the basic idea. And then it says 400 are college degrees. This is 400. Therefore 200 do not have college degrees. This we can make out. Am I right? And it says 60 were single college graduates. Single is M bar. 60 were single college graduates. So this is equal to 60. And therefore this is equal to 340. Am I right? And therefore this is equal to 160. And therefore this is equal to 40. The association attributes completed. Now what we want is single or a college degree is M bar or D. Am I right? M bar or D probability is wanted. Now let us say what is M bar or D. M bar or D is equal to M bar occurs with D, D bar, that is only married but no degree, or married, so M bar or D. So M bar occurs with D and without D. So M bar occurs with D is M bar D, and M bar occurs without D is M bar D bar. Only M bar and M bar D. Both places it occurs, plus those who are degree holders but not married. So, so D bar, in other words, D bar M bar will come. So plus M bar D bar. Am I right? These are the only three possibilities. Now let me circle this here. Let me, one minute. Let me have a red color. Let's not jump to gun. Sir, M bar or D. 1 minute. M bar or D. So M bar or D, these two terms are included. That means M bar occurs with D and without D. So M bar D, M bar D bar, both are included. Then it is D. The degree D is not here, but there is a D here. Now D M bar is already accounted. So we have got only three terms, which is, let me write it here very clearly in red color here, from the table, that both M and D is a possibility. Then M bar D, then M bar D bar. Only these three. Yes or no? Now what is MD? 340. What is M bar D? 60. What is M bar D bar? 40. So this is equal to 440. Hence the probability is 440 by 600. In other words, what is M bar or D? M bar is single. So M bar occurs with D, that is this cell. I want to find out M bar. M bar occurs in both the places. Which one? That is because this is 60, this is 400. The question has given 400 at college degrees. This is 400. Since this is 60 by subtraction, I am saying this is 340. M bar or D. So M bar has to be included. So M bar occurs in two places, M bar D plus M bar D bar. Then D, degree, occurs in two places, but one is already accounted. Therefore, this is MD only to be added here. So this MD plus M bar D plus M bar D bar is either married or degree holder, either unmarried, either single or degree holder. And we are adding all the terms. It comes to 440. Therefore, the required probability is favorable is 440, total is 600, 440 by 600, signed, sealed and delivered. And that is precisely what I have attempted here. You agree? This is frequency approach. So we have solved another example. Now here is a mutually exclusive where you can also have M bar and D occurring together, D bar occurring together. In other words, I have completed all the enumeration process. I am not using per se a word from a formula, but basic Boolean rules. I am constructing association attribute tables and I am solving it for you. So primarily this is given 400, this is 60, therefore this is 340, this is 200, 600, this is 40, therefore this is 160. These three terms are all computed. Now M bar or D is equal to MD plus M bar D plus M bar D bar, which is like a child. I am writing all the terms here, adding 340 plus 60 plus 40 is equal to 440. I am explaining to some of you who may be wondering how you got by subtraction. Since then, even then I am explaining these three steps are unnecessary for brilliant students like you. From the table, you enjoy the solution. Let me explain to you what was the first problem. Joint probability principle. Drink and smoke is a compound probability. Drink and smoke. The second problem involves R. Then the third, I'm building concepts. Let me explain this. If you have a pack of cards, king or a diamond, if I use a frequency, king plus king bar is equal to 52, the total number of cards. Supposing I use a probability principle, king plus king bar, the proportion concept is equal to 1, where king will be defined as 4 by 52, king bar will be defined as 48 by 52. So I can use either proportion or frequency to calculate depending upon the nature of the problem. A plus A bar is 1 if it is proportion, A plus A bar is equal to n if it is frequency. It's counting. Out of 100, it's easy for me to do some cases. That's all I'm doing. I'm not doing anything totally new. You get the point? Does it make sense to you? Any doubt you have? Is a very simple thing. Then the third one, the probability that the household sales will increase in the next 6 months is estimated to be 0.25. The probability in the same period, the housing loans will go up in the same period will be 0. The interest rates on housing loan will go up, will be 0.74. Interest rate will increase. The probability that the household sales or interest rates will go up during the next 6 months is estimated to be 0.89. The probability that both household sales and interest rates will increase during the next 6 months, you will have to compute. This is another example. Let's say the interest rates and sales. So S bar, I bar. Okay, this will be SI, this will be SI bar. I cannot multiply the two unless I have the data with me. This is S bar I, this is S bar I bar. You agree with that? Now, the sales it is given as how much? 0. The probability says 0.25. This is the total here. And then it says the probability that interest rates on household will go up in the same period is 0.74. Am I right? This is given. And now the probability that interest rate house sales will go up or interest rates will go up is 0.89. So what you are given here is sales or interest rate. So SI is given plus SI bar plus S bar I. Am I right? This is equal to 0.89. This is equal to 0.89. You are supposed to find out SI. Am I right? You are supposed to find out SI. Therefore, this will be SI bar. This part is SI bar. SI bar is, I can write this as, let's use the other one, SI plus SI bar. SI bar is equal to S minus SI, okay, plus S bar I. Am I correct? I minus SI. So this is equal to S plus I minus SI. In other words, it is convenient for me to use the traditional one here. It gets cancelled. So S plus I minus SI. S is 0.74. I is 0.25. 0.99 minus SI is 0.89. Sorry, minus SRI. I have to subtract. So when I have to subtract this from 0.89, I get 0.1 as the answer. So in other words, S plus I minus SI is equal to 0.89 is given. I minus 0.89, which is 0.74 plus 0.25 minus 0.89, which is 0.1. So 0.1 will be the correct answer. SI plus 0.25 minus SI plus 0.75 minus SI, and simplifying I get this. I have not written like this a formula. I have taken the table. This is SI, this is SI bar, this is S bar I, this is S bar I bar. You can see it here. Hello? It will be very clear to you. This is 0.74, 0.26, 0.25, 0.75. SI plus SI bar plus S bar I is 0.89. that is SI plus 0.25 minus SI plus 0.74 minus SI is equal to 0.89 because this is 0.74, this is 0.25. So simplifying, we have 0.25 plus 0.74 minus SI is equal to 0.89. Therefore, SI is equal to 0.1. I have not used the formula. I have just used the table and taken the numbers. Similarly, S bar I will be 0.26, 0.74 minus SI. I substitute. So when I simplify, I get 0.25 plus 0.74 minus 0.89. The answer comes. Anyway, I have not used the formula, but you can use it. S plus I minus SI, which is same as this. Hello? Is it clear to you? So put the table. Yes. Yes, I bar. Yes, I bar is equal to S minus SI. S is 0.25. So 0.25 minus SI. S minus SI. S is 0.25. Similarly, I is 0.74. So I minus SI. I minus SI. So that is what I have written there. But the basic idea is presence and absence of attribute is the basic principle. If you use, you can solve the problem. And here it is a case of proportion. As you say, it's not frequency. I can even use the probability as a proportion and directly get the answer. This is completely proportion. All are proportions here. It's not a number. All are proportions. Let me take you a little more complex problem. Mission production case. Probability is number of ways that are favorable to the total possibilities, a chance. But I can count. I can count actually in income tax how many people have complied with income tax procedure and submitted the returns on time. Probability that somebody will submit the income tax on time, I can find out only if I know how many people have submitted. So both are important. So how many people have submitted to the total income tax holders will be the probability. Other fellows are defaulters. You get the point. Somebody is not paying the tax, is a defaulter. So probability involves learning takeaway, two terms very important. What are the ways that are favorable to an event? How many possible ways are there? The ratio is the probability. If you remember that, the entire thing you can conquer. Ultimately, that is what you are doing here also. So here it is a proportion, so I don't have to divide. I have the direct probability directly given, so I can do that. When it is a proportion, A plus A bar is 1. When it is a frequency, A plus A bar is equal to N. So king plus king bar is equal to 52 if I use all the playing cards. But king plus king bar is equal to 1 if king is a probability. 4 by 52 and 48 by 52. Child's play. Its proportion 100. Out of 100, how much is there is a proportion. Probability is a proportion. It's a chance. That's all you're saying. They are all related. Supposing I want to do it as a frequency. Excuse me. How will you do this? 25, 75, 74, 26. I can still do that. Then I will have the number of ways possible is 10 out of 100. I'll solve the problem. My answer will be here 10 by 100. In the second case, when I use the frequency, I'll have to divide it by 100. Here it is already given proportion, so I use it directly. So S plus S bar is 1, I plus I bar is 1. The previous problem, M plus M bar is numbers, is 100, it's a frequency. Here it is a proportion. When I have a proportion, I don't have to solve the problem, answer directly comes. I don't have to divide it by the denominator, 0.1 directly comes. This is 10 out of 100. Supposing in this problem itself, I have taken this as 25, 75, 74, 26. This would have been 10, then I will divide it by 100. No big deal. Try to see the bigger picture. Proportion is probability. Frequency is a number. Number divided by the frequency is a probability. That's all we are saying. And table, you construct a table, you will never go wrong, and put this Boolean rules. Association table. S is associated with the I, it is not associated with the I. The only care you should take is you cannot directly multiply because it may not be independent. You have to be careful. Now look at this problem. Two missions are there. New mission, old mission. It's a commonly faced problem in production operations and all that. So the older mission produces 23% defective widgets. Defective rate is 23%. The new mission produces only 8% defective widget, okay? Widgets. In addition, the new mission produces 3 times as many widgets as the old does. So I am complicating slightly. If the old mission produces 25, the new mission produces 75, total is 100. That's a trick. Given a randomly chosen widget was tested and found to be defective, what is the probability it was produced by the new mission? See, suppose you have new mission, old mission. Let's say old mission is O, new mission is L, new mission is N. Okay, now just see here, I will just shift gear. I will make it a little simpler and different. Old mission is O, new mission is N, and the output total, if the old mission is 25, new mission is 75. It produces 3 times, that's what it says. Total output is 100. New plus old, am I correct? If instead of O, I can have N bar as the, I can even put this way association so that it is clear to you. Let's say N is the old new mission. Let me put it this way. N is the new mission, then N bar is the old mission. This is 75, this is 25, and this total is 100. This is the output. N plus N bar is equal to 100. Now the defective rate for the new mission, for the old mission is, new mission is 8%, so 0.08. The old one, it is 0.23. This is the defective rates that are given. You agree with that? Now, if I ask you a fundamental question, out of the output 100, how many would be defective? That means you will say 75 into 0.08, 25 into 0.23. You will multiply and get the answer. The question that is asked is, a particular randomly chosen widget was tested and found to be defective. What is the probability it is done by the new mission? Are you with me? In other words, new mission, it is found to be defective means defective is given. You want N new mission given defective. Am I right? What is, it is found to be defective. That means it is somewhere here in this total output. So, new mission given defective is what is wanted. Am I right or wrong? Now, defective is, if the defective is there, the new mission is part of the defective. In other words, new mission is a subset of the defective. It cannot be otherwise because it is given defective. So, if I write defective is equal to defective new mission plus defective old mission, which is equal to 0.08 into 75 plus 0.23 into 25. You agree? This is defective definition. Boolean DN, that is defective occurs with new mission or defective occurs with the old mission. Association. Now you want the answer, the probability that it is a new mission given defective. That means this term is the only term where the defective occurs, this term does not occur. Do you agree with me? Therefore, the required probability will be dn divided by dn plus dn bar. Dn plus dn bar, you have already computed the denominator. Dn is the one which contains associated with the new mission, because it says the probability that it is found to be defective, what is the probability it has come from the new machine? So the second term deals with the old machine, and therefore the given probability is dn alone is associated, divided by this, enjoy the solution. So this will be equal to 0.08 into 75 divided by 0.08 into 75 plus 0.23 into 25. You simplify in the calculator. You don't even require a table. This is another Boolean thing. I need not complete the other ones because it is asking what is the probability it has come from the new machine. Defective given new machine. So defective is equal to defective n plus defective n bar, which is 0.208 into 75 plus 0.23. So new machine given defective has to be the only term in this expression which is associated with the new machine is the first term dn. Therefore dn by this, which is the famous Bayes theorem. You have got, in other words, this probability 0.08 and to this, effectively in the probability you have got defective given new machine, but you want to find new machine given defective. Ulta. Inverse probability is Bayes theorem. What is this 0.08? It is defective given new machine. What is this 0.23? Defective given old machine. And when I multiply these two, my basic rule A given B into B is satisfied. But I don't want defective given new machine, I want new machine given defective. Ulta. So the Bayes theorem, even without knowing Bayes theorem you can do, but I am just explaining what's Bayes theorem. 0.51. Okay? 0.51. Bayes theorem. I give this as a homework for you. Right now you do it. Please do this problem. This is a different problem. And then I will cover Bayes theorem once more with another example, then conclude probability. What is Bayes theorem? Let me explain to you. This is a class exercise for you. Of course, I will expect you to do. This is not a test. I expect you to do. So the first one is 50 cars have AC but no CD player. The second one probability is 20 by 70. Because the AC population is 70, AC plus AC bar, the only term that is favorable is associated with the air conditioner is this, because you want the car as a CD player given that it has air conditioner. So this is the air conditioner part, and this as a CD player, this is not applicable. Therefore AC by AC plus AC bar, which is 20 by 70. Anyway, AC plus AC bar is given as 70. Now incidentally, AC plus AC bar are the probability the car has a air conditioner. What is the probability? The car has a air conditioner, 70%. This 70% is called the marginal probability. Why? Because it is not a simple probability. The air conditioner can occur with a CD player. It may not occur with the CD player. A is equal to AC plus AC bar means the probability A is a marginal probability because I am marginalizing for the effect of the CD player. It can occur with CD, without AC, without CD. Therefore, probability of A, probability of A bar, probability of C bar, they are all marginal probabilities. When I take C, it can occur with A or without A. So the moment I have the table, the answer is straightforward, and I am using a very simple rule here. Even a table is not required, but it clarifies, so we can have that. And now the first question is, it has 50. Why? This term is 50. This is what is wanted. The second one is AC plus AC bar because the first term alone has air conditioning associated with the CD player. Therefore, this is 20 by 70. AC by AC plus AC bar, A bar C, sorry, AC bar, which is 20 by 70. Now, AC probability is called the joint probability of A and C. A or C, they are the marginal probabilities of A and C, A or C, because A occurs with C, without C. C occurs with A, without A, they are marginal. And then C given A is the conditional probability. So conditional probability, marginal probability, simple probability, simultaneous occurrence. In this case, there is no simple probability because air conditioner is associated with C or not. So simple probability means simple event. Only one event is there. Suppose I take that. That's a simple probability. AC is the joint probability. A bar is the complement. And A or C is the union. A into C is the joint probability. A is the marginal probability because it marginalizes for C and C bar. So marginal probability, joint probability, conditional probability. C given A is conditional. That means C should be out of the A population. Population of A is 70 and AC is 20. So 20 by 70, child's play, answered. Straightforward formula. AC by AC plus AC bar. This is the A. And I am giving an expression here that air conditioning is the AC is the term, the first term that is associated with air conditioning. The second term is not. Therefore, AC is the favorable event. Number of ways it is favorable. Denominator is the total possibilities. So you get the straightforward answer. Basic probability principle alone I have used. I have not used any complicated formula. Simple Boolean table. Enjoy the solution. You will have terrific clarity. You have to have a mastery of construction of the tables. It's a very simple rule. After some time you will realize you don't need a table. AC is equal to AC plus AC bar. You will do. Left hand you will write a GMAT exam or anything. You don't need the table because you have the table. Table is inside your heart. Initially you need all this. This is what I am telling about R also. You can go on typing, you will get the answer. No problem. You don't need me, you don't need anybody. You need you. Because you are the architect of your own destiny. Okay, so let me just wind up this. Let us now look at the bell curve, which is extremely important for us. And binomial Poisson you can read, but this is very important. So let me go give you the perspective. In the video you have binomial Poisson by me, but I feel this is the most critical, the pivotal point. So let's play safe and do some justice to that. The first question which I ask is, because it looks like a bell shaped one, it's called a bell curve. And it can deal with fractions, it can deal with continuous variables, it can deal with 22.23 kg. What is the probability that it will meet the customer specification with this kg? It can do all that. And it is a distribution which has an outstanding property. Mean, median, mode, all are friendly with each other, they are equal. If I can say in a lighter vein, normal distribution is secular. All mean, median, mode, all are equal to one another. Mean is equal to median is equal to mode. So mean, median, mode, all the three are equal. It looks like a bell. Then the property of symmetry, empirical rule we said, it's symmetrical about the mean value, 1 standard deviation, 2 standard deviation, 3 standard deviation. Yesterday we did that. This is extremely important for knowledge, standard, specifications and all. There is another property. When I extend the tails of the distribution, it will run parallel to the horizontal axis without actually touching the x-axis or even cutting it. Even if you cry, nothing will happen. From Kanyakumari to Kashmir, it will run parallel and nobody can enter the territory anywhere. You will have to keep on drawing. It will meet at infinity, you say in mathematics. So this property is called asymptotic property to the horizontal axis. Mathematicians unfortunately call it asymptotic. I have not called, but I go by them. But what it primarily means is I extend. So you have 6 sigma, 7 sigma, 14 sigma, 99.999, it will not touch. It will run. Even if you cry, no, nothing. As a child, if you cry, they will give you chocolate. Here, nothing. It keeps on. You cry or laugh, it will not tire. Then, the normal distribution has two parameters, the mean and standard deviation, which will have to be specified to understand the normal distribution. For the sake of academics, since our friend asked, the density function fx is written as 1 upon sigma root 2 pi e raised to the power minus x minus mu whole squared by 2 sigma squared minus infinity less than x less than infinity the domain, and all real numbers it is this. Now, if you look at the exponent, it is an elliptic function. Suppose I take different values for a specific mu and sigma. You take an example where mu is 20, sigma is 5, let's say, and keep on varying the axis and plot this fx, it will look like a bell. It will look like a bell, but the bell may be, if your standard deviation is very high, it may look like this bell, or I shrink the standard deviation, another bell may be there like this, but it will be a bell. Why? Because one side is the mirror image of the other, and this will go. In other words, even when you start drawing this, one side will keep on going like this, and then there is a plateau here, and then it goes like this. So that is the property. Hence it is called a bell. Now why I am using the word density function here? How do I, in other words, compute probability for a continuous distribution? Supposing I want probability x greater than 3, how will I find out? Normally, how do you find out? Integrate that. So the area of the curve for a continuous distribution is the integral value. You integrate and with the limits that are given there for you. That's called Riemann integral because it's the area of the curve. So area of the curve at a point is what? Suppose probability x is equal to 2. How will I find out? 0. Because area at a point will not exist. So integral 2 to 2 fx dx is 0. So in a continuous distribution, probability x greater than 2 is same as greater than or equal to 2. So it's the area of the curve. So the area of the curve I need to find out, I have to integrate this. Now mu is the parameter, sigma is another parameter, both you have to specify. Then a problem, suppose x is measured in centimeters. I need a normal curve, area curve, I need a table, or Excel of course can do software. Suppose x is in kilograms, I need another area, I have to find out. Suppose x is in dollar, currency, I need another table. So what statisticians have done, if you are writing an exam where they say computer is not allowed, only calculator and a textbook table they provide, then they say we can solve the problem by standardizing this. Z is equal to x minus mu by sigma. When I standardize this, I have a normal distribution with mean 0 and standard deviation 1, and make a substitution z is equal to x minus mu by sigma. This will become z squared by 2, sigma is 1, root 2 pi, 1 upon root 2 pi e to the power z squared by 2. And with this I can solve because z is independent of the unit. The mean of the z is 0, standard deviation is 1. In other words, all problems I can convert. It is just a transformation of scale and origin. I am not doing anything else. In other words, I am expressing the normal distribution in z units. In the American style, z units you can say, or z units. This is one word which I always feel both are correct. Zebra you are saying, you don't say ZTV, ZTV, zebra, but zest word, Z pronunciation comes. So both z and z, whatever you want, you can use. Now this e raised to the power minus z squared by 2, 1 upon root 2 pi makes me say the original normal distribution I am expressing in z units, so that z does not depend on the scale. I can straight away get the answer. The textbook tables, others are built around that. When you are writing a professional examination, they will not allow you to use the other ones. Is it clear to you? So in that case, necessity is the mother of invention. In Tamil you say Vallavanukku pullum ayudam. The meaning is, if you are a Vallavan, if you are an expert, even a grass can be a powerful weapon for you. Standardized normal distribution has mean 0, standard deviation 1. The classical books used to say it has mean 0 and standard deviation unity. They use the word. Unity means 1. Unity. You can check that. Google, you can Google and do that. Unity. Fisher has used unity, so we can use that. So mean 0, standard deviation 1. Everything is same. There is no change. Now, quality control, process analysis, mission capability, demand projections, vendor rating, everything revolves around the bell curve. Six Sigma, bell curve. Kaizen, bell curve. Deming cycle, bell curve. Plan, do, check, act. Everything requires this bell curve. And in fact, the world has been, and it is still somewhat intoxicated with bell curve. If it is not a bell curve, they are disturbed. You cannot do process capability, you cannot think of a Six Sigma standards unless you bring the system in a state of stability and control using the bell curve. So this is extremely important. But let us understand how the normal curve works. The morning breakfast cereal pack weighs 0.29 kg with a standard deviation of 0.025 kg. The random variable weight of the pack follows a normal distribution. What is the probability that the pack weighs less than 0.28 kg? What is the probability that the pack weighs more than 0.35 kg? What is the probability that the pack weighs between 0.26 and 0.34 kg? Let me answer the question first using Excel, then using R, and conclude the session. The first step you have to do in a normal curve is to plot the function. You just plot it. So I am not drawing it to scale, but I am just sketching it now. So the basic thing is, the first part, if I take it, it is a bell curve here. This is 0.295. Am I correct? This is 0.295 is the mean of the normal distribution. Standard deviation sigma 0.025. That's all same for all. And you want the probability that the pack weighs less than 0.28. So intuition tells you 0.28 must be left of the mean. So let us say I put it somewhere here. 0.28. Therefore, this area is wanted. Am I correct? This area is wanted. What is this? We have answered the problem. Now, the second situation is more than 0.35. So let me just put here. .35, more than this is wanted. I am not drawing to scale, but I am just explaining this to you. The third one situation is between 0.26 and 0.34. Let's say this is 0.260, this is 0.34. This area is wanted. this is what? If you answer, you have done the normal curve. Am I right? This is the basic idea. So the first step is understanding the problem, sketching the graph, very, very important. And if you do that, even if you make some mistakes, you can correct it because you have a very clear concept. You've got the diagrams in place. So let us answer this. In the Microsoft Excel, there are functions norm.dist, norm.inv, norm.s.dist, norm.s.inv. 4 functions are there. Depending upon the nature of the problem in the normal distribution, you are supposed to use them. So let me demonstrate that to you first. Excel's convention is, if I have any normal distribution, I need not convert it to Z. I can do it in Z also. It gives the cumulative probability X here. From the left to X it gives. X can be on the right or the left. In other words, it can equally do cumulative probability if X is here also from left to this. In other words, when it is left of the median, it is straightforward. Suppose I want the cumulative probability for this, I will have to subtract from 1 the cumulative up to this because it is on the positive side. Of course, you can have a minus X here. One side is a mirror image of the other. You can do that, but this is Excel's convention. Now I can do in Excel for the original distribution directly without having to convert. I will also show you standardized variable of Z. In other words, if I convert this into Z, how to use that I will show you, and directly also I will show you. So what you do here is insert function. You don't have to memorize. There is an icon here, fx. Everybody can see. So you insert that function. Insert function. Then in the category statistical you put here. Are you with me? In the category statistical you put. Is it clear? In statistical you just type n. You have here norm.dist is appearing to help you. Is it there? Now norm.dist you put OK. You get a dialog box. X ordinate. Now first diagram what I want. So the directly Excel will give me the cumulative here. Am I right? Because it is the left of that, and therefore what is that I want? 0. So 0.280. Mean of the normal distribution 0.295. Standard deviation 0.025. Am I right? Then cumulative. This question is a logical operator. Do you want a cumulative probability or a simple probability? In the case of the binomial and the Poisson, this has relevance. Here, the continuous distribution is always the area of the curve, so you are talking only cumulative probability. And therefore, the logical operator must be put as 1. If you put 0, try. What is that you are getting? 13 point? 13 point this. You know what it has given? It has given the value of the density function. X minus mu whole squared by 2 sigma squared e power 1 upon sigma root 2 pi. It has faithfully done. When student asked, I actually demonstrated it was 13.3, then he was convinced. If you write it as false also, that means it will give the value of the density fx, but we want the probability, so put 1. Put 1 is true. So you get here 27.425% of the packs will weigh less than 280 grams. Is it clear? So supposing I want to use the Z distribution, ladies and gentlemen, Now Z is equal to x minus mu divided by sigma. Am I right? So this 0.28 will become 0.28 minus 0.295 by sigma 0.025. How much is it? Minus 0.6 is equal to minus 0.6. So the area less than 0.28 is minus 0.6 units of Z. So in Z less than minus 0.6. Area x less than 0.28 is same as area Z less than minus 0.6. Now norm dot S dot dist. So let's go to the next column here, next row, insert function. As before, statistical n, and you have this function norm dot S dot dist. Supposing I use that norm dot S dot dist, Z, what is Z? Minus 0.6, cumulative S1, and you shamelessly get the same answer. So with this background, can you do the second one on your own in Excel? 0.35, more than 0.35. So let me ask you the question, can you do the second problem, second part in Excel based on what we have done? Is left of that, my dear friend. So that's why I am giving you right of that now. Let's see whether you do. Hello? Ladies and gentlemen, I draw your attention. Probability area, the pack weighs more than 0.35 we want. So more than 0.35 is the second graph which I have. So what is the probability? It is more than 0.35. If you have to do it, it is the right of that. There are two ways to do. One way is equal to 1 minus cumulative. Please do that. Is equal to 1 minus cumulative 0.35. Let us see whether everybody gets it. Can I say that I am 99% confident that you are 95% confident you can do the problem? Okay? Excel gives the cumulative probability up to an ordinate x, and x may be on the right or the left. When it is in the left, the cumulative is straightforward. When it is on the right, when I want more than x, I have to subtract 1 minus this.
But the x-axis here, is that absolute number, weight?
We are using the norm dot dist of Excel. Excel takes the original distribution as it is. We can also use norm dot S dot dist, which I have demonstrated to you, by converting this into Z. If you convert this into Z, what will you get? 2.2. Now let me tell you the advantage. The cumulative probability when Excel gives, two cases arise. The ordinate x may be on the right side of the mean or the left side. When it is left side, the answer is straightforward. When it is on the right side, I want more than x, it is 1 minus. But I can prove a corollary to you by the symmetry of normal. If I subtract the deviation 0.295 to 0.35, it is 0.055. That 0.055, if I subtract on the left hand side, I get actually 0.24. So if you are very particular, I have to use that. I can take the ordinate 0.24 on the left side as a symmetry and shamelessly get the answer which I have put there. Because I know you will ask this question, I wanted to forestall, still you have asked, I have put that shamelessly, you are getting 1.39. If you still want to use only left side, you can use it. The deviation is 0.055, symmetry 0.055, I subtract here, no big deal, kindergarten stuff, so you get the answer, left hand side. Is it clear? See, whenever you are asking question, let's have clarity. you place, excuse me, let me make it clear to you. This is, hello, ignore this, you don't follow this. This is for some special query that comes. Symmetry, from this side, this is same as 0.24 here. But all I want to say, cumulative probability on the right of the mean means 1 minus I should do. When I want more than 0.35, I am saying 1 minus up to 0.35. Logic. That's all I am saying. The last one, how do you do that? It will be 0.34 area minus 0.26 area. Yeah. So, and you can use Z also, you will get this. Now, let me show you in R. The cumulative probability P norm. There is no confusion. You can just substitute. So, I just show you here P norm. So, let me first clear this console. P norm. P norm. Okay, sir? Mean is equal to, what is mean? 0. First the ordinate I have to write. What is the ordinate? 0.28 is the same as left tail of Excel, same thing, 0.28. Then mean is 0.295, standard deviation 0.025. By default it takes the left tail in R. In R by default it takes the lower tail. You get the same answer shamelessly. The advantage is I don't have to say cumulative operator 1 like Excel. Excel I have to enter, R straight away accepts it. Mean is equal to this, standard deviation is equal to this. I can write it also, the first one is the ordinate, second one is the mean. I can do like this also to be on an orthodox way, P norm of 0.280 comma mean is equal to 0.295 comma SD is equal to 0.025. Then also you will get the same answer here. In other words, I want to be sure that I am entering mean and standard deviation. The order, supposing I have changed, I have a doubt. By mistake, I put standard deviation first, then I may get a wrong answer. So I put mean is equal to this standard deviation. It accepts that. What is the second one? Greater than. By default, R takes left tail, like the Excel. So 1 minus P norm this, you can do that. But the another way of R is, I put here P norm of 0.350 comma mean is equal to 0.295 comma SD is equal to 0.025 comma lower dot tail is equal to false. Is equal to false. Kadak. Straight answer. Which pleases our friend. Directly you are getting. Lower dot tail is equal to false. I don't have to subtract. Excel we don't have the luxury. Here, because by default it takes lower dot tail, I get your point. See the upper tail it does it here in the R. Directly you will get. So the confusion is resolved. There you have to remember. See, why am I doing Excel and R? It's a simple thing. In the initial stages, let us not undermine Excel. Excel is still a force to reckon with even in advanced analytics, big data and all that. There are so many functions and capabilities today in Excel which are mind-blowing. So, let us not think it is inferior, it is superior also. And second, people who are comfortable with Excel also should have something initial stages of learning. So this is R. Is it clear? Similarly, the other one, what will you do? P norm is this. This is P norm 34260. 88.33% of the packs. Have you done that? The last one. Now a question comes. I will put a puzzle for you. Probability is equal to this. Put a bracket here. Talk 100. Now print probability digits is equal to 4, let's say 88.33. Digits is equal to 4. 88.33%. So you can get that. And some more formatting, floating constant and all available. You can do all kinds of stuff. It's possible. If you use the libraries, it's available. Digits and all that, and you can do that. But I prefer a decimal. Decimal is always convenient. Because in Excel also, when I make it percentage, by mistake, if I put another percentage, some stupid things come and then trouble you later. Play safe with a decimal. So last question before the closure is a puzzle to you. See whether you can solve. A puzzle is the same problem. The mean is 0.295. Standard deviation is 0.025. Everything is fine. Now, what weight of the pack was exceeded by 80% of all packs produced? What is the weight that 80% of the packs produced would have exceeded? You get the point? What is the weight? This is same 0.295. 80% of the packs would have exceeded. Let's say this is X. This area must be 0.8. That means 20% of the packs would have not have achieved this weight. So what is the weight of the pack that 80% of the packs would have exceeded? What weight 80% of all the packs produced would have exceeded? Ulta, inverse. So norm dot in function. Norm dot in is available in Excel. So when I say 80% of the packs would have got this weight, 20% would have got less weight. So you simply put here norm dot in function in Excel. Let's say here norm dot s dot in is later, I will tell you next time when I come. So norm dot in mean probability you want 0.2. I cannot put 0.8 cumulative. Less than weight. 80 would have exceeded, that means 20 would have got less, 0.2. Mean is how much? 0.295. Standard deviation? 0. So 273.96 grams or approximately 274 grams or 0.273 kg. 274 kg. 0.274 kg or 274 grams is the weight which 80% of the packs would have exceeded. 20% of the pack would have got less than 273 grams. Now how do you do it in R? Q norm, P norm, Q norm. ST, isn't it? OP, QR. So Q norm, Q norm. So put here Q norm. Q norm. Either I can put 20 Q norm. The probability is 0.8 comma mean is equal to 0.2 295, comma, SD is equal to 0.025, comma, lower dot tail is equal to false. Directly, like a laddu, you get the answer. But if you put 0.2 also, you'll get the same answer. But I don't have to do. Lower is false. Right, I get the answer. Let's stop here. I have done the bell curve basic concepts, how to do it in Excel and R, and descriptive part, and the concept of probability in this residency we have covered within the allotted time. It has been a great pleasure interacting with you. Let's hope our paths would cross again in the next residency on the 24th and 25th. The remaining part we will do. Wish you the best. We'll meet. Thanks a lot. Thank you for the time. Yeah. Insert function, statistical, norm dot inv, I take here, norm dot s dot inv. Let me take 0.95 because positive, or some value 0.05 itself I can take 0.005. Are you getting minus 2.575? So approximately, with your permission, I know this is minus 2.58, this is plus 2.58. Are you with me? Minus 2.58, this is plus 2.58. And since I am using a modulus sign, I can say 100 by sigma by root n is equal to 2.58. It has to be. Solve for n. Because modulus z less than or equal to 2.58 alone can make the probability 99. And therefore this 100 by sigma by root n has to be equal to 2.58. And sigma from an earlier pilot study is given to be how much? 500. So you can solve for n. Are you with me? Solve for n. Based on this, you will get the sample size. In other words, this is the foundation of how to determine the sample size from first principles. Okay? From first principles. Now, I can make it even simpler and then tell you a very, very simple thing where you can straight away get that. Okay? So, is this clear to you? Now you can solve for n. Root n is equal to 100. Root n is equal to 100 by 2.58 times something. You can solve for n. So, in other words, 100 is equal to 2.58 into 500 by root n. Therefore, root n is equal to 2.58 into 500 by 100 with 2.58 into 5. N is equal to 2.58 whole square into 25. It's about 166 sample size. 160?
6.4. So we can round it up to nearest.
Yeah, okay. 166 or 167, whatever. That's the sample size. Now, is it clear to you? Another way to look at the whole problem is, supposing I ask you a question. In other words, another simple way to do that. I ask you a question, margin of error, you said all that. From this distribution, Z all of us know is equal to x minus mu by sigma by root n. So, if I write here 99% confidence interval, for mu. In other words, a two-sided confidence interval. I don't know mu, but I want to estimate mu and generate an interval in which the probability the true value mu will fall is 99%. So, this is given in statistics by x bar plus or minus z alpha by 2 into standard error. And this part is called the margin of error. In other words, x bar plus minus z alpha by 2 into standard error. When I want 99%, the data says this is minus 2.58 to plus 2.58, and therefore I can write this formula as x bar plus or minus 2.58 times standard error is what? Sigma by root n. Now sigma by root n, this portion is called the margin of error which I commit. Now in the survey, this is the theoretical margin of error. Practical margin of error, you want x bar minus mu modulus must be less than or equal to 100. This is practical margin of error. Equate the theoretical margin of error to the practical margin of error, solve for n. In other words, 100 is equal to 2.58 sigma by root n. Solve for n. This is the easiest way to understand. The first one is from first principles. The second one is how confident I am, if I want 99% confident that the mu value of the population mean mu will fall in this interval, and this part plus minus is called the margin of error, which is theoretically computed margin of error based on statistical bell curve, and I equate the theoretical margin of error to the practical margin of error which I want to achieve in the survey, solve for n. It's the easiest way to remember. In other words, whenever they give some error should fall, that is practical margin of error, find out the theoretical margin of error and solve. Supposing I give you 95% confidence level, this will be equal to minus 1.96 plus or minus 1.96. Mota moti you can even do 2. Empirical rule says 95% of the values will fall within 2 standard deviation. So all I can do is x bar plus or minus 2 times sigma by root n. Mota moti, or 1.96 to be more precise, and solve for n shamelessly. In other words, I want 95, this 2.58 will become 1.96, no big deal. I want 90, I can look at the table, no big deal. I want 70, I can look at the table, no big deal. I can use Excel. In other words, the principle to remember is margin of error, which is theoretically done, is the bell curve. The practical error I want to commit in the survey is plus minus 100. Equate this to this, solve for n, because n is unknown. That's it. Is it clear to you? I'm connecting this. Now in the hypothesis, incidentally, this will be a two-tail hypothesis confidence. That's a relationship. But we are not doing hypothesis test. We are just building the confidence level. How confident are you? In other words, you will say there is a 99% probability that the true value of mu will fall in this interval. Plus minus 99% probability. There is 95% probability that the true value of mu will fall x bar plus minus 1.96 times standard error. So this part is the margin of error. Equate this theoretical to the practical, solve for n. This is what is done in survey. I thought I should just share with you this because this is a frequently asked question by all students and participants. I don't want to ignore this. It's an important aspect. How do you determine the sample size? Now you may ask a question. Am I measuring only one characteristic? I may have several mu's. I know you will ask that. You are in a very thought-provoking questions you ask. I like it. Suppose I measure only one characteristic, it's okay. But I have 5 or 6 characteristics or parameters I measure in a survey. For each one of them I will compute the sample size, then take the max of all the sample size as the sample size for the survey. Are you with me? In other words, the first one gives a sample size of 166, second one gives 300, third one gives 200. What should be the sample size? 300, because I have to satisfy all. So the max of all the sample sizes that I could generate using this rule will be the sample size for the survey. I'm just showing how to do that. Is it clear to you?
Right side, just to come it down from you. Right side, you are considering that all the samples will fall within the mean or
No, this is what I want to achieve. It should be within 100. I want to achieve that.
So 100% all the.
Not 100%. Here 100 rupees. Error. If my estimate is 1000, my mu may be 900 or 1100. The error has to be within that 100. I'm setting. If I say the estimate is 1000 rupees.
At the 95% confidence level.
So first this is margin of error.
Sorry, 99%.
This is margin of error. There is no 99% here now. I want this margin of error. I want this margin of error 99% of the time I am using this principle. In other words, if I have to achieve this 99% of the time, this has to be equal to 2.58 times sigma by root n. In other words, the margin of error which is desired by you will have to be equated to the theoretical margin of error based on the normal curve. So 99% margin of error in a normal curve will be plus minus 2.58 sigma by root n, and that has to be equal to 100. Then only I will achieve this 99% of the time. Otherwise I may not achieve this 99% of the time.
Achieve that for 99%.
Yeah, that's what you want in a survey. Yeah. That's why if you read the question here, the question says that. Just see here. You want the estimate to be within 100 with a confidence level of 99%. The sample size calculation for large sample only we are calculating. We do not want to calculate the sample size for a small sample. For large sample, central limit theorem holds. Excuse me, it's a good question our friend has asked. Hello, you are assuming only normal distribution, what about the rest? The answer is, if you have got small sample size, you do not spend too much time because you have got limited things, you have to determine the sample size. The only thing which you can assume is a T distribution and work out the sample size. But in most of the survey which we do in life, they involve large sample only. So when I have large sample, the distribution of x bar is a bell curve. X may be anything. So hence bell curve. We are assuming the distribution of x bar to be a bell, not x to be a bell. That's the beauty of this. And achieve this normal curve. Now the second issue which I want to discuss with you. Supposing you come out with a sample size of 10,000 according to the formula. Okay? 95%, 99% it will give. Now the company says 10,000 people we have to contact in person. We need so many investigators. Every day if they interview, let's say each investigator interviews 5 or 6 per day, and we put 5 people, 30, and we want, let's say 50 we interview. In a month we can interview only 1,500. It will take 6 to 7 months. And each investigator we have to pay some 5,000 rupees, say 10,000 rupees per month, 50,000, 6 months and all that. Suppose you say this budget, oh my God, 10,000 I want, it will cost me 9 lakhs. No, my budget is only 4 lakhs. You give me a plan. Then you will have to tell 99% confidence level you want, you have to select 10,000. The cost will be 10 lakhs. They say, now you want only 5 lakhs. You cannot get 99% confidence level, mutually exclusive. One of the two only you will have. You cannot have 99% confidence level and 5 lakhs. Select one of them. And okay, we can do that. Then what is my confidence level? Some 65, 70. You better accept. Because the sample size 10,000 is required. You say you cannot afford. So the cost of the budget will have to be interwoven with the sample size accuracy, and then you need a trade-off. Okay, I don't want 95, let me satisfy with 80%. Tell me the sample size. You can tell. So you can generate a curve. Sample size and cost of the survey. And accuracy. You get the point? Trade-off. Are you with me? These questions will come in practice. 35,000 sample size is required for the cola test in America. 35,000 people you have to contact for Pepsi and the famous Coke experiment. The largest historically publicized consumer research in the United States. Confidence level. They want that. And it is a failure finally. Can fail also. Because they were researching only taste matters. See what has happened was April 2000 something, I do not remember the exact year, I don't remember, historically most publicized one. Coke introduced all new Coke. All new Coke. They did that test of the taste. Brands were marked all new Coke, existing Coke, Pepsi. They were masked and people tasted it. They found all new Coke is the best. Next is Coke, next is Pepsi. And when the mask was removed and they showed this is a brand, the percentage gap went up even further. The new Coke was far superior. Originally it was 55, old Coke was 50, Pepsi was 45, now it became 65 or 70. Then they thought new Coke should be introduced in the market by the survey result 99% confident. Yet it failed. Why? Because they thought only taste matters. They assumed the consumers will completely switch over to new Coke. But then the market said, what about the old Coke? We also want to have it side by side. And during the 3 months period in which Coke was troubled, Pepsi took full advantage, and one of the consumers of using the Pepsi Cola looking at Coke, oh Coke, why did you do it? There's an advertisement. And then the Pepsi was advertising, Coke said they will offer lemon. Now they are not offering lemon, they were offering only lemonade. And 3 months they were rattled. In June 2001, that exact year, June 1986, I think it's a classic example. Coke went back to the old Coke and they have removed the new Coke at that time. The reason was they thought taste alone matters and the 99% confident and all that, they were jumping with joy, but the consumers did not want the old Coke to completely go away from the market, which they have not captured. And therefore, the sample size determination has something to do with your objective and clear understanding of the perception of the people. Perception matters. And according to the perception, sample size will change. The famous example given in Parshuraman's book or Philip Kotler's marketing, I pick up those examples to say, even with 99% confidence level, if your problem is not properly defined, you go wrong. Therefore, that is supreme overriding factor, and I am assuming all of us do it correctly. Then the sample size, this is the way it does this. Okay, now the second problem which I want you to look at it is this problem. How do you handle a problem like this? For proportion, population proportion, I put a, let's say pi, 1 minute, this is 95% confidence level. This is given by P is the sample proportion plus or minus, in a normal curve it is 1.96. I can draw the curve here. This is 0.025, this is 0.025, this is 0.95. Are you with me, right? Now 1.96 into standard error will be root of P into 1 minus p by n. Actually, the standard error is sigma by root n. You have to, strictly speaking, put pi into 1 minus pi by n. Is a population, am I correct? Sigma. But I want a confidence interval for pi. How can I have an expression root of pi into 1 minus pi when I do not know pi? Plus or minus sigma by root n. In the case of proportion, this should have been pi into 1 minus pi. But I want the confidence interval for pi. I cannot have an expression root of pi when I do not know pi. So I have to put p. This is the formula. The sample proportion is known. And now what we want is, the margin of error is, theoretical margin of error is 1.96 into root of p into 1 minus p by n. This must be equal to the practical margin of error. How much is it? They want the margin of error between p and pi to be within 0.03. So the margin of error is 0.03. I equate, solve for n, enjoy the solution. So what is p here? Cricket. The company wants the estimate to be this. Earlier study reveals 80 high school students, 36 play cricket. So 36 divided by 80. In fact, if you can argue, a pilot study done earlier reveals that out of 80, 36 by 80 to be the population, the value of p. So the confidence interval, if I put that here, you substitute, what is 36 by 80? 0.45. 0.45 into 1 minus 0.4555 divided by n, solve for n. Please solve for n. So I have to put here 1.96 under root 0.45 into 0.55 divided by n is equal to 0.03. So if you solve, what is the value of n? You can put goal seek in Excel and find out also, isn't it? You can put some goal seek in Excel and find out, otherwise solve. Am I right? Proportion 36 by 80. 36 out of the 80 people play cricket. Cricket players, I want to estimate. Actually in India, if you do it now, it may be even 70 out of the 80 will play cricket, possible. But this is an example. This may be a place where people generally do not love cricket too much. It's maybe 36 by 80. In the US, with all this, they play baseball and all that. A person runs over the other fellow several times and some funny game, but no cricket. So cricket is only here, isn't it? So this is the example. Sorry. How much are you getting?
9 points.
Sample size cannot be 9 point. 1050. That's correct. 1057 or something like that. Okay. That is the sample size required. That's the sample size required. Are you with me? Okay. Now I want to just kindle your curiosity. Only in the case of proportion this is possible. In other cases it is not possible. Suppose the same problem, I write this like this now. What should be the sample size for this study? Earlier pilot study, all those things are not there. Only in the case of proportion it is possible. Earlier pilot study and all that is not there. I want to estimate, and 95% confidence interval 0.03 should be the error. What should be the sample size? How is it possible to solve? Puzzle in statistics. Puzzles and problem solving, you should be experts if you want a career in analytics. Think about it. I have not, only in, and I am giving you a hint, only in the case of proportion it is possible, in the case of mean it is not possible.
So we can decide on the.
Huh?
Because we can decide on the proportion and then.
No, sir. 0.03, 95% probability and all that is there. Now, Siddharth Basu, I give 10 seconds. Any one of you answers this? Nothing is given, sir. Okay. Let us say P is not known. It's not given. I know this expression P into 1 minus P is maximum when P is equal to 0.5. P into 1 minus P is maximum when P is equal to 0.5. Am I right or wrong? Suppose I have the expression P into 1 minus P. It will be P minus P squared. You can either draw a graph or differentiate. 1 minus 2P is equal to 0, P is equal to half. In other words, the expression P into 1 minus P is maximum 0.5 and therefore I need a large sample size, not 1057, little larger than this. Put 0.5 into 0.5 and solve and enjoy the solution. This is a puzzle which I want to give to you. It's not in the textbook problem. This is created by me while having a dialogue. The other case, when it is mu, it's not possible. But in the proportion, the advantage is P into 1 minus P, I can figure it out. You get the point? Because this is proportion. Is it? Are you clear? Now you can do the very same problem, take 0.5 and 0.5, find out the value of n. It will be a little over 1057, little larger. In other words, you can do a problem like that when it comes to proportion. All I need is, but of course, one more thing. I don't specify this also, then I am mad. Nothing can be done. You have to go home. How is it? Margin of error. I will not specify anything. It's not possible.
1067.
1067. That's all. A small error change, but you can still calculate. So now the basic question I ask is a 0.5 you substitute. In this place you substitute 0.5. P into 1 minus P is maximum and P is 0.5, 0.5. You are an engineer? Computer science? No. Where? BCom graduate, but you have done in your plus 2 some high level calculus, isn't it? Maxima, minima. Differentiate P into 1 minus P. P minus 2P squared, P squared. So 1 minus 2P is equal to 0. P is equal to half. Or the easy way is you plot P starting with values 0.05, 0.1 in Excel. You will find P is equal to half. When P is 0.5, it is maximum. Shall I show it to you? Without calculus. I will show you. Without calculus. I will quickly show you. Intuition. Let me create a sheet here. So let me put here, let's say P 1 minus P So this is maximum. Insert a graph if you want to, line graph. Okay, this is incorrectly drawn, doesn't matter, but I have the value here, 0.25 is the maximum. When P is 0.5, P into 1 minus P is 0.25. You can check that, okay? So, as if you don't want the calculus, the highest value is 0.25. And there is some symmetry between this, but the highest is 0.25. You can check that. So that means when P is 0.5, I reach the highest. Okay, simple Excel. Even a poetry student can do with a graph. There is no big rocket science. I have put a formula. I have taken P from 0.1 to 1. 1 minus P by formula. Then I multiply P into 1 minus P, these products. I find when P is 0.5, this expression P into 1 minus P is maximum. So P is equal to 0.5 is the value which maximizes the function. Yeah, around that. Maximum. You will have to take the maximum sample size is 1067. Yeah, see what happens is when the margin of error is less than or equal to 100, as a practical person you will have to always equal to 100 because that is going to be the largest sample size. Ideally, within 100 means I am allowing you to go up to 100. So you just take the maximum limit, which is the sample size. Equate the theoretical margin of error to the practical margin of error, solve for n. That's a golden rule. We are assuming normal distribution, multivariate normal. I am just saying this is on group 1. The group 2, let's say group 1 is defaulter or something, group 2 is this. Now the separation is not good. In other words, I am not able to differentiate. The overlapping cannot be made equal to 0 in segmentation. There are always undecided people. Supposing I take another example here. This is my G1. This is my G2. Now this is discriminating, differentiating better than this. So how to achieve the largest separation possible between the two groups? Now what is your support vector machine saying? I have generated a number of hyperplanes. Using the best hyperplane, can I achieve the largest separation between the classes? In a way, support vector machine also does that, but the algorithm, kernel, the other methods are completely different. But the largest separation which I want to achieve between the classes is the aim of support vector machine as well as discriminant, even though both are entirely different in their approach and other things. But this part, as a classifier, if you take support vector machine, you can also use support vector for regression. As a classifier, if I use, the largest separation can I achieve between the classes is the aim of support vector machine, which was the aim of Fisher in 1936 when he wrote that immortal classic paper in taxonomy called Fisher's linear discriminant analysis. The objective is to, so the key word which you have to remember is, when I do an exercise, can I achieve the largest separation between segments? Market segmentation. How to achieve this largest separation? That means what are the clusters which you do initially and then separate the clusters. So it is a supervised learning, But I can't do a supervised learning unless I know the clusters.
What is the binomial distribution? The binomial distribution is a distribution of simply counting the number of things, the number of defective products, the number of customers that receive service, etc., exactly like the applications that we were talking about. This is the statement we have already seen. The probability of getting x successes out of n trials is p of x is equal to n choose x, p to the power x, 1 minus p to the power x, where the individual p is the probability of getting success in one trial. You remember my formula of 0.1 to the power 2? So it's that formula. What does this formula say? This formula says that if P is the probability of success of a single trial, then what is the probability of getting X successes out of N trials? N trials, P is the success probability of each trial. What is the probability of X successes? N choose X, P to the power X, 1 minus P to the power N minus X. How do I think this through? What is a trial? A trial is the total number of attempts that I am making, the total number of products that I am making. I am making 3 products. The probability of each product being defective is 0.1. What is the chance that I will get 2 defects? 3 cheese 2, 0.1 to the power 2, 0.9 to the power 1. P successes, P into P into P, N minus X failures. What is not a success is a failure, whose probability is 1 minus P, and there are X ways of choosing that original N.
Sir, in this case, it's like these trials are like with replacement.
These trials are not just with replacement. Yes, they're with replacement. It's not like it's a population, so to speak. In other words, an actual experiment is not being done. It's imagined that someone is doing this experiment repeatedly. So yes, if you want to think of it as replacement, it's replacement. It's a model. For example, here, a bank issues card statements to customers under the scheme of MasterCard. Based on past data, the bank has found that 60% of all accounts pay on time following the bill. If a sample of 7 accounts is selected at random from the current database, construct the binomial probability distribution of accounts paying on time. What is the question being asked? The question being asked is this, that I am looking at 7 accounts and I am trying to understand how many of those accounts are paying up. How many of those accounts are paying up? Now, what values can it take? What are the possible values that my X can take? 0, 1, 2, 3, 4, 5, 6 and 7. 6 means none pay on time. I'm sorry, 0 means none pay on time, 1 means 1 pays on time, 7 means all pay on time. The chance that every one of them individually pay on time is 60%. And I'm going to make the assumption that these people aren't talking to each other. So they're behaving independently. The 60% chance applies to everyone separately. Which means that if one person has paid, that has had no impact on whether another person has paid or not. Correct? Let's do one of these calculations. Let's say, what is the probability that, let's say, how many people? 2 people pay on time. So 2 pay on time. What is the answer to this? You can use this formula directly, but 2 people pay on time means 0.6 into 2, 0.6 into 0.6, not into 2 to the power 2, 0.4 to the power 5. These are the 5 people who have not paid on time. These are the 2 people who have paid on time. So this 0.6 into 0.6 into this 0.6 into 0.6 into 0.4 into 0.4 into 0.4 into 0.4 into 0.4, the 7 people. Now that is one arrangement. How many such arrangements are possible? 7 choose 2 arrangements are possible. Those 2 could be the first 2. They could be the next 2. They could be the first and the last. There are 7 choose 2 of those. For each of them is a pattern: paid, paid, not paid, not paid, paid. And every time you see a paid, 0.6. Every time you see a do not paid, 0.4. The 0.6 you are going to see twice, and the 0.4 you are going to see 5 times. Therefore, this formula.
So can you expand choose one, 7?
7 choose 2 is a formula which simply says how many ways can I pick 2 things out of 7. The formula for it is 7 factorial divided by 2 factorial into 5 factorial, which is 7, in this case 7 into 6 divided by 2, which is I think 21. The 21 ways to pick 2 out of 7.
To 5 factorial.
Because I asked for 2. I can do it, and the problem asks for all combinations. I've just solved it for one particular answer. I need to do it for 0, 1, 2, 3, 4, all of them. If I add them, what answer will I get? I'll get the answer 1. Because something must happen.
Isn't the number of trials 8?
No, the number of trials is 7. The number of outcomes is 8. If I toss one coin, I can see 2 things. So there are 7 outcomes. There are 7 people. So 0, 1, 2, 3, 4, 5, 6, 7. That's 8. The 8 possible outcomes. Alright. So now there is a file here. It's called, I think, binomial distribution example. You'd import a few things for plotting and for the stat functions. Then I'm going to set up the problem. How am I going to set up the problem? In this particular case, just by specifying an n and specifying a p. What is the n? In this case, n is the total number of trials. Why is it 7 for me? Because there are 7 customers. Correct? P is 0.6. Where do I get this 0.6? Here, right? This 60%. What am I doing here? What I'm doing here is I'm creating the sample space. I'm creating the set of numbers for which I want to calculate the probability. So this one here, the range function 0 to 8. So when I do this, it creates an array of 8 numbers 0 to 7.
Do that 0 really has a value? We don't need it.
Of course we do. There is a reasonable probability that nobody pays on time. Same place, wherever you got the other one from.
Can you repeat once more the basis of the formula, how it was?
How it was formed? This is X people have paid. So this is P, so think of it as P into P into P X times. And think of 1 minus P into 1 minus P N minus X times. Because X people have paid, and what allows me to multiply the probabilities? Because if there's 60% chance you pay, there's also 60% chance you pay. And so when I figure out the chance that both of you pay is going to be 6.6 into 0.6. And if he doesn't pay, and I want to multiply those, so 0.6 into 0.6 into 0.4. Now how many 0.6s are there? How many successes I want? How many 0.4s are there? How many non-successes are there? And how many such possibilities are there? How many ways can I get 2 successes? That is what I'm calling 7 choose 2, which is 21. Why is it 21? You are going to pick 2 people out of 7. How many ways can you pick them? The first person you can pick in 7 ways. The first person who pays on time. The second you can pick in 6 ways. 7 into 6. But if I pick you first and you second, that's the same as picking you first and you second. So I've double counted. So by 2. So 7 into 6 by 2, which is my 21.
So one quick question: when in practical world,
now he gets it.
Look out for binomial distribution.
This application, this kind of application, or another kind of application. For example, I can change this to saying in sales, I am selling my, or I am approaching 7 leads. The chance of a conversion for a lead is 60%. What is my sales distribution? Okay, so I'll use that information, for example, to figure out, let's say that how much budget should I have for the sales team? For example, I could say, you know what? I'm going to approach 7 leads and I'm going to get sales. However, how are those sales going to be made? The sales are going to be made on the phone. But to confirm the sale, I need to be able to send a salesperson to the person's house and get their signature. This person is going to take a certain amount of time to travel through the famous city of Bangalore and get stuck in the traffic jam and get there. So I'll be able to get at most 3 signatures in a day. And if I lose it, I lose it. Or 4 signatures. Or so let's suppose that therefore I employ 1 person. Is that good enough? So now I'm asking the question, what is the probability that I'll end up making more than 3 sales in a day? Because if I end up making more than 3 sales in a day, I'll not be able to close all the sales. So this becomes a Salesforce question. It becomes a question of saying that based on my ability to sell, I should have a sales team. If my sales team is too short, too small, there's a probability that they will not be able to close out all my sales and I'll leave money on the table. If my sales team is too big, I'll be paying for that sales team, but they will not have enough to do. So yes, the binomial distribution is used left, right and center. In contact centers, yes. It's used big, same argument. In contact centers, for example, one reason it's used is how many escalations do you expect? So in many of these. So how do I execute on this? So I've given the, I've created the array. Now here's the command that you need to know. This command calculates that formula. That n choose k, that formula is calculated. Right? By the way, you can manually do this if you want to once, which is your 21 into 0.6 to the power 2 into 0.5 to the power 4. Does anyone want to manually do it once? No one has any, just to check, otherwise you'll just trust the output, that's fine. But if I do this, binomial stats.binomial.pmf, PMF stands for probability mass function, in case you want to know what on earth that means. Probability mass function. So this thing is called a probability mass function. Probability clear? Mass means it's almost as if you're thinking of a solid material and the probability as being physical mass. How much mass is in each number? How much mass is in each number? So
what it represents, that PMF?
This number. The PMF simply is this number. It's a calculation of this number. So now if I ask for binomial, if you do it without the equal to, it will just give it directly. Alright. So it's done. It just takes a little bit of time. So binomial is an array. So what is this number here? For 0. So what is this in the business context? This is the chance that nobody pays on time. The number of people who pay on time is 0. So it's about 0.16%. What is the chance that 1% pays on time? 1.7%. 2 people pay on time? About 7.7%. 3 people pay on time? About 19%. 4 people pay on time? About 29%. 5 people pay on time? 26%. 6 people? 13%. 7 people? About 2.7%. Okay. Curiosity question. How many people would you expect to pay on time?
7.
No. Remember, there is a 60% chance that everyone will pay. Yes, 4 or 5. In fact, the right answer is 7 into 0.6, which is about 4.2%. So you would expect to see about 4 or a little more than 4 people pay on time. And the chance of 4 people paying on time is what? 0, 1, 29%. And the chance that 5 people pay on time is about 26%. If you want to plot this, there's a slightly sort of, jazzed up version of a plot here. So the first line says plot it. It says binomial. Then there's a title. There's a labels. And then finally the plot command itself. I think that's a plotting artifact. I mean, it tells you what to plot. You can remove it and see what happens. Here's an interesting thing. Someone's asked, what happens when I add up all the probabilities? Which is what I get here. I don't need it. It's a checksum. So one possibility of a business outcome is, what is the probability that say more than 6 people do not pay their bills on time? Now in a collections team in a bank certainly is interested in that, because you have to go after that. There's also a question of what is the entitlement on a specific month. So a bank is going to make money, or let's say a telephone company, whoever is going to make money on the amount of bill that's actually paid. Now the fact that a bill has been given to a person doesn't necessarily mean they'll pay it, like here. So how much money does the bank actually expect to make? It has to have an estimate of its revenue per month. How does it get that? By doing a calculation of this kind. Here's a little formula if it wants to help you. The average of a binomial distribution is given by n into p. We just discussed that. Total number of trials into the probability. 7 into 0.6. Which means, for example, that if I think that my success probability of a sale is 10% and I approach 10 people, the number of sales I expect to make is 10 into 0.1, which is 1. Does that mean I will make one sale? No. The distribution goes from 0, 1, 2, 3 up to 10. But the average is at 1. Similarly, the average of this distribution is where it's at 4.2. But where is the picture? Where is the average? Where is 4.2? Somewhere here, right? Somewhere here is 4.2. This is the center of gravity of the distribution. There's a standard deviation formula, if you want to know, NP into 1 minus P. The standard deviation will make a little more sense when we talk about the normal distribution. I hope I'll get there. Now there's another distribution which is used a little less in practice. You guys are all very practical types. How is it used? How is it used?
Any examples where would we use a mean or a standard deviation on the binomial?
The kind of question he asked. So I want to make an estimate, for example, as to how many people will pay my bills. Because based on that I will decide. So I can do it 2 ways. I can, for example, say what is the number of people I expect to pay my bills? 4.2.
So in linear regression, it's one of the most popular algorithms in production because it can be used for classification, it can be used for regression. It also happens to be one of the core algorithms that is used by many other algorithms. Logistic regression is a linear regression based model, right? If you take support vector machine, another very famous algorithm in data science, it's a linear model. Or if you take, if you do linear models using binned data, what you call binned data sets, then the model that you get behaves like a decision tree, right? So many of the other algorithms which are very popular in the industry, internally they're linked to linear models. You can spend your entire lifetime studying linear models. It has so much of depth and breadth that it takes a lot of time to actually get used to all these things. So today I'm going to start by introducing you to simple linear models, the core concepts, and then subsequently I'll leave some advanced discussions for the next visit where we'll be covering FMT, feature engineering model tuning. There we'll discuss some further advanced concepts of linear models. All right. So I hope these people have loaded my team has loaded the data set, everything. I'm going to give you 3 codes today, of which I'll cover 1 in the class. The other 2 is for you to go and explore further, okay? Based on what we discussed in the class. This PPT is accessible to all of you. Can you access this PPT? I think she's gone to, you can, okay. The code is also available. The PPT, the code, the data set. You should have received 3 codes. All right, let's start. As the name suggests, this algorithm is called linear regression. And the reason why it's called linear regression, as the name suggests, is it's based on the concept of a line, a plane, a hyperplane. We call it by these names. Okay. So to begin with, I need to ask you whether you know how a line is represented. Line in mathematics. Are you all comfortable with this? All right. So let's start. Imagine I give you 2 dimensions. This is x. X is one of your independent attributes. We call it columns in our data frame, right? So I have loaded a data from a table into my data frame, and one of the columns in the data frame I call it x. This is my independent variable. The other column which I want to predict, the target column, I call it y. Could be anything. Y could be the miles per gallon, and x could be the weight of the car. The more the weight of the car, the less the miles per gallon, right? So y is my dependent variable, x is my independent variable. Imagine this x has 4, 5, 6. These are the units, 1, 2, 3, 4, 5, 6. These are the measurements of x. And let's assume, for sake of discussion, let's assume that whenever x is 1, y is also 1. So whenever x is 1, y is also 1. That is what you're seeing in the data. You take another record, there you see x is equal to 2, then y is also equal to 2. Take the third one, x is 3, y is also 3. So when you try to draw a line, a relationship between them, you see it's a straight line. The straight line tells you the relationship between x and y. How are these two related to each other? We in data science call these things as models. Models are nothing but surfaces in your feature space. What is a feature space? Feature space is collection of your independent attributes and the dependent attribute. You are trying to explore how this y and this x interact with each other. That interaction is what we represented as models. So models are nothing but lines, surfaces, hypersurfaces in your feature space. So when you build k nearest neighbors, okay, in k nearest neighbors you have different classes of data points. Suppose these are different classes, okay, and okay, let me make it slightly more complex. What k nearest neighbor does is, we call it breaking your mathematical space into regions. It breaks your mathematical space into regions. So it says this region belongs to the circular point, This region belongs to the triangular point and he has things on the wrong side. K nearest neighbors splits your mathematical space into regions. Those regions are called Voronoi regions. So this imaginary surface is the model in K nearest neighbor. So in linear regression, this line which represents the relationship in x and y, this line is my model. So I want to predict the value of y given the value of x. What the line is saying is y is equal to x. So the prediction is whenever x is some value, y will also be the same value. Can I write this expression as y equal to 1x? Does it make any difference? 1 into x. This 1 in mathematics, it has a meaning. This 1 is nothing but this angle that line makes with the x-axis, the tan of that angle into x. Whenever y is equal to x, this angle will always be 45 degrees. Okay? And in trigonometry, tan of 45 is always 1. Now you might be wondering, what is this trigonometry, tan, theta and all? These are all jargons. Actually, it's all common sense. Look at this. When we studied in school, we came across trigonometry. In trigonometry, we came across sine theta, cos theta, tan theta. What are these sine theta, cos theta, tan theta? What are these things? These are names given to certain ratios. So tan theta is, tan means the ratio between, we show it as dy by dx. How much y changes whenever x changes by 1 unit? That ratio is called tan. How much y changes when x changes by 1 unit? How much y changes in this graph when x changes by 1 unit? So 1 by 1 is equal to 1. Dy by dx, how much y changes by small change in x, 1 unit change in x, that ratio is called tan theta. Sounds very high-fi, but that's what it is. Okay? So whenever both of them synchronize, whenever x changes by 1, y changes by 1, it will always happen when this angle is 45. So we say that tan of 45 is 1. So when you say tan of 45, dy by dx will be 1 by 1, it will always be 1. Alright? Let me modify this a bit. So right now, this expression is represented as m. Okay, this is a standard practice where we represent it as m. So y equal to mx is the expression, mathematical expression of this line. Suppose I put a line here, okay, and it's parallel to this line. It's parallel to this line, okay, which means this line is also making 45 degrees to the line parallel to x-axis. I'm not going to show this line here, okay, just to make it less cumbersome. So I have another line here. This is L1, this is L2. Now can I say y equal to x? When x is 0, y is not 0, y is 2. Correct. When x is 1, y is not 1, y is 3. When x is 2, y is not 2, y is 4. So we add a constant to this. This constant is equal to 2 right now for this line. This constant is nothing but what is the value of y when x is 0? What is the value of y when x is 0? That is called c. It also goes by the name of intercept. Where in your mathematical space on the y dimension, where on the y dimension does the line intercept or cut the y-axis? So this is the generic equation of a line, y equal to mx plus c. It tells you how y and x are related to each other. If you look at this line L1, then this becomes 0. So y equal to mx. If you look at L2, this becomes not 0 but 2. So this relation continues to remain same. In both the cases, the m is same. M is nothing but tan of the 45 degrees. We call it slope. Right? So this is the generic equation, one way of representing a line, y equal to mx plus c. So in this expression, y is given in your data set, it's the target column. X is given in your data set, it is the independent columns, the independent attributes. From this data that you have given to the algorithm has found out for you the m and the c. We call these coefficients. Coefficients of the model. This m and the c, they reflect the relationship between y and x in your data set. So the m and the c is what forms the model for you. Shall I complicate it a bit more? We'll complicate it a bit more. Suppose instead of having 1, or let me just continue with this only. So you have one target variable y, one x. In this case, tan of 45 happened to be 1. But suppose your line is like this. It's a straight line, but it's not at 45 degrees, it's at 15 degrees. Right? Then in that case also the equation of the line will be y equal to mx. The reason why I'm not putting c is 0 here. C is 0. You can put c, but c is 0. And this angle m, this value of m, will not be 1. It will be 1 only when it's 45 degrees. It's less than 45 degrees, so tan of 15 degrees into 1 into x plus c. This will be equation of this line. What is tan theta? Tan theta is nothing but how much y changes for 1 unit change in x. We call it tan. Okay. All right. Let's complicate this a bit more. Suppose instead of only one variable x, now you have x1 and you have another variable x2. And you have only one dependent variable y. In such case, the algorithm will find out the relationship between x1 and y, x2 and y. So it will express that relationship as y equal to m1 x1 plus m2 x2, and there will be only one constant term, because now instead of having a line, you will have a plane where the plane goes through the y-axis at some point, it cuts the y-axis at some point. So now you have two edges. One edge is on x2, the other edge is on x1. The two edges may have different slopes, different angles with x-axis. Those are reflected over here as m1, m2. The c continues to be the same c. Where is the plane cutting the y-axis? Which means, what is the value of y when x1 and x2 are 0? That is called the intercept.
So
we're going to have only one plane, like we can't have a multiple plane, like in case of a 3D.
In case of?
Like if we have a Z also, so then will be having a...
It'll be called a hyperplane. We don't know how it looks, but it'll be only one. Yeah. So human minds can imagine only 3 dimensions. But suppose you go beyond 3 dimensions, there also the linear models work. Those planes are called hyperplanes. Hyperplanes, how do they look? We can't imagine. So we don't know that, but they will also be one single plane. And there will be no ups and downs, no curves, nothing. It will be a straight plane. What do you mean by straight plane in 4 dimensions? No idea. It will have the same properties as the properties of a plane in 3 dimensions.
So these x1 and x2 need to be in the same plane, or it can be in a different plane, like x1 is in one plane and x2 in different plane. Is it possible?
They will be in the same plane.
Yeah.
They can't be in different. Right? And
actually, x1 is one axis and x2 is another axis, and they are like separated with some angle.
90 degrees. This angle in linear models, this is a 3-dimensional isometric view. This angle is always 90 degrees. We say that they are orthogonal to each other. Look at this laptop. Okay, in this laptop, now this is my x1 dimension, this is my x2 dimension. There is a plane. This plane is your model. This plane is making some angle. I can't make it right now. I can't, right? It will make some angle with x1 axis. It will make some angle with x2 axis. This is my m2. This is my m1. So at what angle the plane is to x2 and x1 will decide the value of y. Okay. In this case, the value of c will be 0 because the plane is touching the y-axis. Y-axis is perpendicular like this. It's touching the y-axis at the origin, the 0 point. So imagine I can remove this. If this was a yoga tablet, I could remove this. Okay, and imagine I'm putting it in some angle, cutting the y-axis at some point. Then this angle is my m1, m2. The point at which the plane cuts the y-axis is my c. We cannot imagine beyond 3 dimensions how the planes will look, but they will have the same mathematical properties as a plane in 3 dimensions. A point that you should probably keep in mind, it will become useful to you down the line when you do deep learning and so on and so forth. The number of dimensions of a model, this is the model right now, the surface. The number of dimensions, how many dimensions is this model? 2 dimensions, length into breadth. The model is only 2 dimensions. The feature space is 3 dimensions. So the number of dimensions in a model will always be 1 less than the number of dimensions in the feature space. Right? All right. You can call it anything you like. That's not a problem. X, Y, Z. Okay, that's what I say. You want to call it Z, you call it Z. Doesn't matter. It just replaces the Z. Basically, these are independent variables. This is the target variable. So we are trying to understand how the target variable is influenced by these.
Say you have 3 x1, x2, x3. So how in that case the model dimension will be, so still the model dimension will be 2 only, right?
No, x1, x2, x3 are 3 independent variables. So therefore on target variables, no? So that makes it 4. 4 dimensions.
4 dimensions. What is the dimension of the
Model will be 3 dimension in that case. I mean, however it looks, I don't know how it will be. How will it look? It will have three edges. We don't know how it looks, so that's why we don't talk about it. But the properties of that model will be similar to properties of a plane, a line, so on and so forth. So don't imagine, you can't.
So independent variable we have to always consider as the orthogonal in nature.
That is what the algorithms assume. All the algorithms assume that your independent variables, okay, suppose you have a data frame. In the data frame, you have multiple columns. These are independent variables, IV1, IV2, IV3, and this is my target. All algorithms assume that independent variables are independent of each other. they don't influence each other. They only influence the target. That's what they assume, but in real world that is not true. Suppose I want to predict miles per gallon of a car, given the weight of the car, given the horsepower of the car, we know that they are related. So we can build a model, but we also know that horsepower and weight are also related to each other. More the weight of the car, more the horsepower. They're positively related, but the algorithm assumes that they are not related. This problem in linear models, it's called the problem of collinearity, where assumption is each dimension is independent of the other, but in reality they influence each other. That problem is called collinearity. Okay? This collinearity, where independent dimensions interact with each other, they are not independent. This collinearity can lead you to a problem when you productionize your models. The models may be less effective, less predictive power than required to be because of the collinearity. So one of the things that we do when building models is we see what the collinearity is between the dimensions. If the collinearity is very strong, they are very strongly related to each other, the independent variables, then we may have to resort to some techniques. Suppose this is my horsepower and this is the weight of the car, and if I plot a graph between these two, can you tell me how that will look? This is weight of the car, this is horsepower of the car. If I plot a graph between these two, take all the data points, you will see some linear trend. Okay? All of you know what is R value? Coefficient of correlation, R value. Statistics, you've done statistics, right? Hey, go on. Okay, R value of measurement of how these two variables relate to each other, how strongly, you will see that R value comes very close to +1 in this case. The maximum it can be is 1. So it will be very close to +1. Okay? Which means these two variables are not truly independent of each other. But the algorithm wants all the dimensions to be independent of each other. So in such cases, we resort to a technique called dimensionality reduction, which is not simply dropping the dimension. I may convert them into a composite dimension. Both the dimensions put together, I create a synthetic dimension. And I use that synthetic dimension in my model building rather than these two.
Just a question here. In this case, the horsepower and the weight of the engine is the same, almost same. Like it's increasing the same in non-linear line. It means, well, if I put both of them, it will have the same effect in the model. Right? If I remove one of them also, then it will have the same effect in the model. The model will not change anything. Right?
If that removal is an option to you when the relationship is absolutely a line, but you will see that it's generally not a line, it's a spread, and the spread is also curved. So which one should I drop? Should I drop this or this? That depends on which dimension is more prone to errors when you're capturing the data. So instead of doing all that analysis, I might convert into a synthetic dimension using a technique called PCA, Principal Component Analysis.
One question. So in the previous example, we took two variables, independent variables, x1 and x2, and they are separated by 90 degrees, right? Yeah. So in that case, we can have only 4 independent variables. Because 90, 90, 90.
No, that's what I'm saying. That is our brain. Our brain can see only 3 dimensions. But the algorithm can work in 300 dimensions. All the 300 dimensions mathematically will be orthogonal to each other.
Why is there a problem if these variables are actually very collinear and very collinear? So why is that a problem?
Okay. You please keep this question parked for a minute. I want to cover some ground before I answer that question, because that's a very important question you asked. All right, let's move on. The term regression indicates that we're going to predict some values. Whenever you build models to predict values, we use the word regression. The term linear, now you understand where it comes from. So your linear model is nothing but a combination, addition of weighted variables. This weighted variable, this is another weighted variable, you're adding the two to predict the value of y. It's a linear combination of one or more variables with weights. The weights are called coefficients. Okay, so once again I repeat, what is this M1? M1 is how much y changes whenever x1 changes by 1 unit, keeping x2 constant. What is this M2? M2 is how much y changes whenever x2 changes by 1 unit, keeping x1 constant. Okay, so this is the relationship between x1 and y. This is the relationship between x2 and y. The relationship is how much y changes whenever input changes by 1 unit. That is a relationship, and that relationship is what we call linear models. We already seen this. I'm going to move on. So before we start building our models, we actually need to analyze our data set. And what I mean by this is, suppose this is my data set. I'll go and analyze between this IV1 and target, IV2 and target, IV3 and target, which one of these is strongly related with the target. If suppose IV2 and the target, the distribution is scattered all over the place. It's like a cloud. The data points are spread like a cloud. There's no trend you are seeing in that spread. Then in that case, IV2 is not a good predictor of the target. How can you say that? Take any value of IV2. Draw a straight line. For that value of IV2, you have multiple values of target. Which one should I take? I don't know which one to take. So we say that we say that IV2, independent variable 2, is not a good predictor of the target. On the other hand, if suppose between say IV1 and the target, we see the data points are scattered in some form of a trend, then we say that IV1 is a good predictor of the target. So the first filter that you will apply in your data set is, of all the columns given to you, which columns strongly relate to the target. Those columns which don't relate strongly with the target, you are going to drop them from your analysis. You are not going to build your linear model on them. Okay? So the relationship could be positive, or the relationship could be negative. It could be downwards also. I want a strong relationship. Doesn't matter if it's this way or that way, I don't care. But I don't want to include any columns in my model which have this kind of a spread versus the y. Okay?
Sir, but it has to be linear. Like it cannot be a parabola or something like that. Suppose there exists a strong
Ideally, it should not be a parabola. It should not be parabola. Linear models are built only when you see linear relationships. If you see non-linear relationships, then you might want to resort to non-linear models. Okay, linear models, they expect a linear relationship between y and the independent variables. Then your model's predictive power will be very high. However, as you will see now, those are all very perfect conditions. In the real world, we hardly have such perfect conditions, right? So sometimes, even when the relationship is not linear, we go up, build a linear model. We'll see that down the line. Okay, how do you measure the strength of the relationship between independent variable and the target? For that, we use a metric called coefficient of correlation. How these two variables, the target and the independent variable, how they correlate, how they relate to each other, which we express using a character called R. I'll tell you what this R is. This R metric can have a value of +1, -1 to +1 in this range. The least it can have is -1. The max it can have a value is +1. It cannot be beyond this range. R value can be 0. It can be 0. When you have it spread like this, your R value will be very close to 0. When you have a spread like this, your R value will be very close to -1. When you have a spread in the other way, your R value will be very close to +1. Okay? So R value is an indicator of how strong the relationships are. So let's understand this R value slightly more detail. The formula for R value is this. This is a formula for R value, okay? So, shall we begin? Don't worry about the formula. Don't worry about the formula. Understand the concept. All the formulas are there in the library. We just need to call those functions and get our things done. But get the concept in place. Yeah.
So, if I have different units of measurement, independent and independent variables, how does the R value then in that case work?
Doesn't matter. R value is a measurement based on the spread of the data. No. Have you heard of scaling? Scaling? Linear model is one model, linear regression, where scaling has no impact. Whether you scale the data or not, it's going to give the same result. All of you know the formula for variance? What is the formula, please?
Square standard.
What? Variance. Variance. X minus means xi minus x bar, you can call it mu, the whole square n. Okay? I is equal to 1 to n. Let's keep it n, but otherwise we use n minus 1. If sample size is less, we use n minus 1. Okay? All of you okay with this? Don't worry about these things. What is this variance? That's what you need to understand, not the formula. Thank you. I know it's spread. What is it telling you?
It means how the mean means how the data, what is the distance of the data and how it is.
I know, but what is it telling you?
How is it related with the data?
The distance between
how it varies with how it varies. What is the similarity?
What is central value? What is x bar or what is mu? What is the central value? Don't give me the formula. Don't give me the formula. I know the formula. Central value is a value which represents all the data points that you have. Okay? So if I take all your heights, add it up, divide by a number of students in the class, that will be average height of a student in this class. Now, how good this average is? First of all, why do we take averages? Why do we need mean and median and all? Why do we do all these things? There are many. That is statistical answer. Yes, you're right. But many times in data science, you will come across a situation where you have a function and the function takes as input only one value to predict something. Now, which one of the values should I put? There are 30 students in the class, each one has a different height, right? I want to say order some kind of a code for all the students in the class, a great learning stamped code. Now, what size should I tell the manufacturer? I can't give different sizes and one unit of every size. So I have to give some size which will represent all of you so that all of you can fit in comfortably, right? That is the idea, okay? In such situations, we need to input only one value. So what we do is we find the x bar or the mu. But the question is, how reliable is this x bar? Suppose the average height of the student in this class comes to 5.5. Some of you might be 6 footers, you might get offended, you will say, boss, I'm 6 footer, how can you say I'm 5.5?
Depends on how spread this particular, what is the difference between mean and
exactly. So how reliable your central values is, based on which you're going to do further actions, how reliable your central values is, that reliability is given by the measure of variance. If the variance is too large, the central value is not reliable, right? So the variance gives you the reliability of the central values, how reliable the central values are. So the formula for variance is this, right? Just look at the numerator. Just look at the numerator. This is the case when you have only one variable, x. Now I have two variables, x and y. I want to see how they vary together. How they influence each other, vary together. That is called covariance, which is given by xi minus x bar. We don't square it into yi minus y bar. So we find out xi minus x bar multiplied by yi minus y bar. That tells me how the data points in the feature space, they vary together. That is called covariance.
So they should not vary together to have high covariance.
Independent variables. Independent variables. Independent variables should not have covariance. Target variable and independent variable should have strong covariance. Otherwise, you don't use those independent variables. When you're building linear models, the target variable, the y, and the independent variables, IVs, should have very strong covariance. But within the independent variables, the covariance should be 0. That is an ideal situation. Practically, it never happens. All right. Now, given this covariance, now look at the formula for R. Okay. On the top, in the numerator, you are seeing covariance. Right? And if you look at it carefully, the units on the top and the units on the denominator are the same. This is also xi minus x bar, this is also xi minus x, this is yi minus y bar, this is also yi minus y bar. It is squared term, but there is an under root. This is also squared term, but it's an under root. So both numerator and denominator are going to have same units of measurement. Agreed? So if I have a kilogram by kilogram case, then the units cancel each other out. It becomes a unitless quantity. It is a ratio. R value is a ratio. Okay. Now, when you have a diagram, when you have a plot like this between two variables, could be independent variables, target and independent, could be anything. When you have this kind of plot, you will see that R value is close to 0. We'll see why this happens. When you have this kind of a plot where you see a trend, but as x increases, y decreases, they are going in different directions. X increases, y decreases, they're opposing each other. Then we'll have R value close to -1. Whenever they go hand in hand, when x increases, y also increases. They go in the same direction together. Then R will be close to +1. And it's not very difficult to understand why. Let's look at this particular case closely. I'm going to look at this particular case closely. Yeah, this is my mathematical space or feature space. Both x and y have some x bar and y bar, the average, right? X bar, y bar. Keep in mind, all linear models that we build, linear regression models, they will always go through the point where x bar and the y bar meet. So the linear model that we saw a few minutes ago, this model will always go through wherever the x bar and the y bar meet. It will be hinged onto that point. That point will act as a fulcrum. All right? There's one particular point that linear regression models will always go through x bar, y bar. I'm really surprised and I find it very difficult to understand why this is not told. Now look at the points over here, okay? Let's look at these points carefully. Take any point, like let's take this point. For this point, what is xi minus x bar? Xi minus x bar is this distance. This is my x bar, the vertical line. Xi minus x bar is this distance. Agreed? All of you agree? What is yi minus y bar for this point? It is the distance between this point and the y bar. Agreed? Xi minus x bar is positive, yi minus y bar is positive. So when you multiply these two, it is like finding the area of a rectangle. Length into breadth. So xi minus x bar into yi minus y bar for this point is nothing but the area it covers over here. This is the area. This area is a positive area. All of you okay? Let's take another point at the bottom of the screen, say this one. For this point, xi minus x bar is greater than xi, so xi minus x bar is negative. So for this point, xi minus x bar is negative, yi minus y bar is also negative. Negative into negative becomes positive. So all the areas over here will be positive, all the areas over here also will be positive. Agreed? Take this point. Xi minus x bar is negative because xi is less than x bar, negative. Yi minus y bar is positive. So positive into negative will give you negative. All these data points will have negative areas. All these data points will have negative areas. When you total this up, sigma, you see sigma over here? Sigma means sum up all the areas. When you sum up all the areas here, all the positives and the negatives will cancel each other out. The reason why they will cancel each other out is each quadrant has same density of these points. The points are distributed like a symmetrical circle. So whenever r value is close to 0, that is because your numerator is becoming 0. Numerator becoming 0 means your distribution is like this. For a given value of x, I have multiple values of y. Which y should I take? I don't know. So we say that x is not a good predictor of y. On the other hand, if you take this plot, if it becomes tighter, then positive areas is greater than the negative areas. So r value will be close to +1. It will become 1 only when all the data points lie on a straight line, which will never happen. If this plot was this way, all the negative areas will overwhelm the positive areas, then r value will be close to -1. Right? All of you okay? So this is the concept of r value. So what we do in linear models is we test the r values of every independent dimension with the target variable. We select only those whose r value is either close to -1 or +1. Any dimension with r value close to 0, that dimension is a useless dimension. How close to 0 is useless? That depends on your particular problem statement. So generally any r value greater than 7.7 minus or plus, it's considered as a good variable. Any variable with r value between 0.5 and 0.7, it requires further research whether this relationship is real or is it a fluke by chance that you're seeing in your data set. Any r value close to 0, not worth considering.
What about the second case you told, fluke? What does it exactly mean? I don't understand. Why you said fluke?
Okay. It could be a sampling error. The way you selected your samples from the population, that leads to the r value. Okay. Now observe this. Since you asked this question, let's discuss this out. For r value to be 0, okay, if this is my x and this is my y, this is x bar, this is y bar, okay? X bar, y bar. I'm not showing you the coordinates. For r value to be 0, the data points, suppose I give you 10 data points, the data points have to be absolutely symmetrically distributed for r value to be 0, absolute symmetrical distribution in all the quadrants. What is the probability that when you're doing random sampling, you'll get data points in such a way that they get symmetrically distributed around this? What is the probability? Probability is 0. That particular configuration of data points that you want from the universe, which symmetrically distributes itself around these two x bars and y bars to give you the r value of 0, that probability is 0. It will never happen. So even in the real world, if there is no relationship between x bar and y bar, because of your sampling brings in some asymmetry in the distribution. There will be some asymmetry in the distribution. You will end up with an r value greater than 0. This r value we call it statistical fluke. So when R value is very close to zeros, it could be by chance sampling problem. It may not be a real relationship. So you have to go and further investigate whether the relationship is real, it might be real, or is it fake?
It might be possible also R value is greater than 70, but it might be a fluke.
Probability is very low.
Yeah, probability.
That will happen when your sampling is completely gone case. You have done some mistake in sampling. Then it can happen. All right. Shall we move on?
One question. So what is the application of this? So one thing is when we have independent variables, how they are closely related, so that we can come out with composite.
Yes. You're talking about R value.
Yeah. Another thing is finding the relationship between how independent is closely related to the target. So in both cases we can use.
Yeah, both cases we have to use this. We have to use for both the situations to select the independent dimensions, and within the independent dimensions knock out those which are very strongly correlated.
So is this the only Pearson only the way to find out?
No, there are other methods. So Carl Pearson is the most commonly used for coefficient. There is one more available. There are many such other methods, but this is one which we mostly use in our cases. Shall we move on? Okay.
Now this algorithm that we are going to use, what this algorithm will do is, given the data set you have, okay, suppose this is the distribution in X and Y. In your data set you have only one independent column and the one target column, and you see, notice the distribution is like this. So this is a good predictor of this Y, but let me understand in precise terms what is the relationship between Y and X. I see that there is a relationship, but what exactly is that relationship precisely? I want that. That precise relationship between Y and X will be your model, represented by a line in this case. Okay. The algorithm, what this algorithm will do is, it can find out multiple lines here. Multiple lines can be shown here, right? What the algorithm will do is, it will start with some random M and random C. Y equal to mx plus C. Y equal to mx plus C is the expression. Hey guys, I'm talking to you, not to them. Y is equal to mx plus C. So by changing M and C, whenever I change M and C, the relationship between X and Y changes, which means the line changes. The line represents a relationship. So whenever I change M and C, the line will change. Okay. This algorithm will start from some random M and random C. And it will evaluate the different possible lines before it finds what is called the best fit line. Okay. Now what is this best fit line? Amongst all the lines possible that it has checked, best fit line is that which goes through the maximum number of data points. It can't go through all of them. It goes through maximum number of data points, and at the same time, it minimizes the distance between other points and the line. The distance between other points and this line, this distance, you see the distance over here, this distance is called error. What it means is, for a given value of X, your line says the value of Y should be this, but your data available in your data set is saying the value is this. The blue line here is the predicted values for the different X. Actual values are the black dots. So whenever you have a black dot above the line or below the line, that means there is a difference in prediction and actual. That difference is called error. Okay. Don't mistake the word error. Error doesn't mean anything negative, but it's used for something that you already know. I'll tell you what it is. So amongst all the different possible lines, there will be only one line which minimizes the sum of all these errors. If I sum up all these errors across all the data points, the minimum sum error will be given to you by only one line. That line is called the best fit line. The algorithm will find out for you from infinite number of possibilities the best fit line for you. It's like looking for a needle in the haystack. And to do this, it makes use of a process which is called the gradient descent. All algorithms use, under the hood, a learning process, a process which they make use of to find the best model for you in the given data set. That process in this case is called gradient descent.
So the errors that we're talking about, basically that will be very significant to what our alpha level is.
What is alpha level?
For example, if I'm taking that as the level of significance that I'm taking, I'm deciding for business, that I can have maybe 5% of errors there and there. And 95%
You're talking about type 1, type 2 error. That comes in classification. This is regression. However, the same concept will come into play here also in a different way. I'll tell you what that way is. Yeah. So we'll see that way. So again, once again, you have to park your question. We are too far away from those points, right? Shall I move on? Any questions? Yeah.
So the number of points is the priority to the distance is more than the number of points, right? Distance. There are two things you told: the maximum number of points it should go through, and also the distance. But the distance is the most priority because the errors will be less.
Yeah, error will be less when the points sit on the line, no? So it has to be taken together. Both of them are equal priority, but there's only one line which is satisfy that condition. The driving condition is the error should be minimized. That is only condition, okay? So there are no two-step process here. It's only one step. So let me explain this to you. If I plot, okay, equation of a line is y equal to mx plus c. I'm going to take one simple case, mx plus c, where in your original mathematical space you have x, you have y. One independent variable, one dependent variable. Okay. So now we have two parameters that we can modify, and whenever I modify m and c, I'll get different lines. This is m1 and c1, this is m2 and c2, this is m3 and c3. I'll get different lines. Each line has its own m and c, right? But not all lines are good lines. So if I have this line, for example, this is L1. If I take the L1 is made of M1, C1. I see that many of the data points are away from L1 on both the sides. So the error E1 is very high. If I take, say, the next one, L2, I'll call this L2, I call this L2. I see that L2 has its own slope, its own this intercept, and it also does a lot of errors, but not as much as E1, E2. I try out various lines, then I come to LBF, best fit. Best fit line is this, which has its own M, best fit, C, best fit, and E, best fit, and of all these errors, this will be the least. E best fit will be the least. Now the question is, by changing my M and C, but just a small minute amount, I'll get a different line. So there are infinite lines possible, which you will have to evaluate. Out of the infinite lines, you have to find the best fit. Brute force will not work here. You can't use brute force.
So when you talk about gradient descent, right? Say I'm actually trying out, or say I started with a particular MNC, and slowly I move on. I'm correcting my errors, or errors are getting reduced. All of a sudden, it again started increasing. Right?
That will not happen, right? Except for when you cross the best fit point.
I'm coming to that now. Okay. So instead of looking at this mathematical space, I can actually look at another mathematical space, which is related to this. That mathematical space is between M and C, and this dimension is error, where error means sum of all the errors put together. Okay. In linear regression, this error is calculated as y hat, that is predicted value of y, minus y actuals, okay, raised to power 2 divided by n. N is the number of data points. I is equal to 1 to n. We call it squared error, sum of squared errors. Sum is sigma, squaring the errors. So the error done by model is nothing but a sum of squared errors. N is the number of data points you have. Isn't this formula for variance? So error is nothing but variance. How data points vary, scatter across the best fit line. The lesser the variance, more reliable the central value is. The lesser the variance of the points across the model, the better the model is. Same concept comes to you in a different way. So, sum of squared errors is nothing but variance, variance of the data points across the model. So, I want to find that model where the variance of the data points across the model is the least.
It's slightly confusing. See, when you say covariance, right, and you said like if you have more value of covariance, then it is better for dependent versus independent. Right?
More value R.
That is not
R is measurement of degree of covariance.
Okay.
Okay. The stronger the R is, the better the predictor is.
So degree of covariance should be higher, whereas variance should be lower.
Variance in individual dimension should be low.
That is comparing with some other box model.
That is also
always we are we are omitting the outliers and all. So in the data which we are collecting, we are removing the outliers. It will always in the like a group of data which is affecting the some model. So always it will be in the linear model, right?
Yeah, I didn't get your question. Come on again. Yeah, you said box plot, you identified outliers, you removed
so we are removing it. So we are collecting the data which is affecting, which is going to affect the model. So if you are plotting in the any linear regression model, it will be always in the linear model.
Not necessary.
Varun, I'll take your question. I'll just hold on a minute. I'll take the question here. Within 1.96 standard deviation on this side and this side, the data points might still have noise in them, which causes a spread across the model. You're talking about outliers, which is lying 1.96 standard deviation greater. So by removing that, yes, you're cleaning the data, but within the 1.96 standard deviation, still you have noise. That noise will appear as scatter around the models. It will appear as variance around the model.
But once we are omitting the unwanted data, so it will be in the like linear regression model, but with some noise.
It will never be one single line kind of.
Actually, no, you have asked a very, very important question, which I will just answer this because this is a very important question which will be helpful down the line. Just hold on a minute. I'll answer the question first. Okay. Now, if I take any axis, any variable x, it has a spread. Okay. This spread, variance, what you call variance, there are two types of variances. One is called stochastic variance, which means nothing but probabilistic variance. The other one is called deterministic variance, which means variance that happens for reasons that I know. I know why that variance happens, okay? That is called deterministic. But variance also happens in your data set for reasons that I don't know. We call them noise. Okay, that is called noise, all right? Now, if I have a plot like this, a linear model, and I have distribution of the data points around this, okay? For a given value of x, now look at this. Actual value is this in your data set, but the model is saying it is this. Similarly, there's another actual value which is this. Why is this variance occurring? I don't know. I don't know why that variance is occurring. This is called, I don't want to use the words right now, I'll use it down the line. This variance that you see, for a given value of x, you have multiple values of y, but they're very close, but still there is a variance in them. That variance is called stochastic noise. Okay? For a given value of x, the fact that the value of y is spread around its central bar, this is deterministic. We know that this is going to be this way. All right? So when you address the outliers is something which is lying 2 standard deviations away or 1.96 standard deviation away. You're addressing the outlier, okay. But you're not addressing the random variance which exists in the data points within the 1.96 standard deviations. Those will cause a scatter of the data points across the model.
You were talking about the real actual data point or the prediction point?
Prediction is your line. Actual is the black data points. Between the actuals and line, there is a gap. That gap is my stochastic. Unexplained variance. I don't know why it happens. Yeah, in the actual data. Deterministic is, I already know my y bar has this spread and my x has this spread. This spread is also variance. I already know it has this spread. I know it will be like this only. I have no reason for worrying about that. What I'm worrying about is, for a given value of x, why are there multiple values of y?
That is stochastic. We don't know why it happens. That is what we call noise.
Is it because of lack of domain expertise? Nothing to do with
even the domain expertise, you'll have this problem.
So when we have a multi-dependent variables, right? So here we are talking about trying to find out the only one and then y. Okay, but maybe when we are we have to analyze it in the togetherness
multivariate analysis.
Right. Maybe that is creating this kind of noise because we are trying to target on a single one, right?
That can happen. That can also happen.
When the different variables actually interact with each other, there's collinearity in your data set. You can have trouble with this noise. That can happen. The noise may get cancelled out, or the noise may get magnified.
What can happen?
One more question. So we are looking for best fit line which gives us the least error.
Least sum of squared errors.
What is the definition of least? Mean like
I'll tell you what is least. That's what I'm going towards now. Okay. So I have different combination of M and C. So I moved away from my original mathematical space into another mathematical space where the dimensions are the different slopes and different intercepts, different lines. Okay. Each line gives you some error. Okay. The formula for this error is the sum of squared errors, which is nothing but variance across the line. Whenever you have a squared term, this is called quadratic equation in mathematics. All quadratic equations, they have a property. The property is called, they are convex functions. Convex functions means when you plot them against their independent variables, M and C, they will always acquire a bowl shape. Three-dimensional bowl. Such functions which acquire this kind of a shape, a bowl shape in the 3 dimensions, such functions are called convex functions. They are guaranteed to have one absolute minima. Parabolic structure. One absolute minima. So for some combination of M and C, I'll get the least error. That combination of M and C, which gives me the least error, is my best fit line. So the algorithm will start from some random M and C. So maybe this is the random M and C. This is my random M and this is my random C. When I use this, I get a line, but the sum of squared errors across the line is very high. So each point here is one line in the original mathematical space. So in the original mathematical space, between X and Y, if this was my L1, maybe this is the L1, it had some M and some C. That M and C is this point represents this line. This line had some sum of squared errors. The sum of squared errors is this.
So you talked about one M, but if it is multiple, still it will be like similar?
Still 100%, guaranteed.
Okay. But we can't visualize.
We can't visualize. Okay.
All right, no kidding. Let's move on. Now what this algorithm does is, it starts from some random M and C, and it uses a concept called gradient descent. descent. As the name suggests, we have to descend. Okay, gradient descent algorithm, which internally makes use of what is called partial derivatives. Partial derivatives. And this term partial derivatives, I'll tell you what it is. It's not a rocket science. It is dy by dx. It's exactly dy by dx. What it does is, for a small change in m in this direction or this direction, for a small change in m in this direction or this direction, from the first m, the random m, for a small change in m in this direction or this direction, dx, how much the error drops or increases. So when I change it in this direction, I'm going further up, the error increases, dy increases. Whereas if I go in this direction, I reduce my m, my dy decreases. So it notes down that I have to move in this direction. But you have taken only m right now. How about c? So do the same thing with c. If I increase the c slightly here, what happens to my error? If I see it slightly here, what happens to my error? I'll go in that direction where my error decreases, descent. So using this concept of partial derivatives, which is nothing but dy by dx applied on individual dimensions one at a time, that's why it's called partial. It finds out, it moves from this line to the next line to the next line to the next line until it reaches this point. At this point, what will happen is, whichever direction you move in beyond this, the error is only going to go up. Whether you go this side or that side, error is not going to come down further. So it realizes that it has reached the global minima.
This is your best fit line.
Which is the relation between M and E plus C.
Correct. M, C and E put together. This is the best fit line. That best fit line happens to be this line, BF.
So it does not evaluate infinite lines. It uses this gradient descent concept and finds out for the next best fit line, next, and reaches the global minimum.
So is there a chance of jumping that?
Yeah, there is.
And there can be local minimas as well in case of...
Not in quadratic functions.
Not so in linear regression we'll never have local minimas.
You'll never have. If you use neural networks, you can get stuck in local minimas.
Okay.
Linear regression, the error function being quadratic, it guarantees you will reach absolute minima. Okay? But in the process of jumping, there is something called learning step. Okay? We are too far away from this, so I'll just tell you the concept, which is used along with this partial derivatives. If the learning step, the amount of change that you do in dy and dx, if the learning step is too high, you might jump and oscillate. You might jump the global minima, go on the wrong side, and keep oscillating backward and forward, infinite loops. So the learning step is adjusted. As it keeps jumping down, the learning steps become smaller and smaller. There are various ways of handling this to prevent the oscillation. One of the ways is, as you jump towards your objective, the goal, the steps become smaller and smaller. This algorithm is called bold driver algorithm, which is part of your gradient descent, one variant of gradient descent. When you do deep learning, this partial derivatives will become very important for you to understand how the neural networks work, how the back propagation of errors happen. Those things will come into play. Okay, but we still have a lot of time before we reach there. So hopefully I'll spend some time on this one day and tell you what this is.
Both in bold driver as well as gradient.
Yeah.
In both we can.
Yeah, you can. Yes.
But you have various other algorithms now which have come up, which are apparently better than this. Okay, we'll talk about those things down the line. Shall I move on? All of you? Okay. Your questions are still parked, right? The two questions. What are those two questions?
One is the standard deviation, like talking about error data.
He doesn't.
So it's basically the first one was the collinearity between that got answered. Okay. Within the variables, within the set of the dependent variables, why there should be no collinearity.
why should there be no collinearity? What happens if there is collinearity? That was one of the questions which came up. I remember that. Good. So my strategy worked. Okay, let's move on. We'll discuss those things in detail, right? Okay, so keep in mind, we are looking at these data points closely. The distance between the actuals and the line is the predicted values. For a given value of x, the predicted value of y is the blue line. The distance between the actual, which is shown by the black dot, and the line, that distance is shown by yellow dashed lines. This distance is a measurement of error. Okay. The objective is square of these errors, all these errors squared, that sum should be minimized. Okay, which is not very difficult to conceptualize once again. So if I have my linear model drawn like this, best fit line, the data points are scattered around this. You look at the data point from this angle. When you do that, you will see a spread. This variance, this is called sum of squared errors, which is nothing but xi minus x bar. X bar here is your predicted lines. So formula remains same. That variance is called sum of squared errors. That variance we have to minimize. The minimal the variance is, the better your model is. All right. So let me explain this to you, because you're going to come across these terms down the line. So let me explain this to you in slightly more detail. We're looking at this model, and the distribution of the points, the red points is given to you. The blue lines are x bar and y bar. And keep in mind, your model, the best fit line, will always go through the point where x bar and y bar meet. Always. Okay. Now look at this. Don't worry about these terms. It's all, not very difficult to conceptualize, visualize. What happened? Yeah, there you go. Now, if I take the red point is the actual point in my data set. In your data set, in your data frame, there is a record with value of x, and its corresponding value y is red, the P1. But the model, the best fit line, says the value should be yellow, P2. The distance between P2 and P1, this is what we call error, the variance. This is what we call sum of squared errors. Okay, I'm showing you only one data point here, but you have to imagine there are multiple data points here. Sum of squared error applies all together. Okay, so this contributes to the sum of squared error. There is another term that we use, which is called total error. Total error across all the data points put together. The total error is nothing but the difference between y bar, the expected value of y, and the actual value of y. In your data, there is a distance between the actual value of y and the predicted value, the expected value of y. Expected value is y bar. That distance is called total error. Of the total error, your model has captured this much. Your model is a regression model, hence the name given to this is regression error. Of the total error, your model has predicted this much error. Of the total error in your data set, your model has predicted this much. The difference between predicted and the y bar. This distance is called regression error. What it has not been able to explain is this. This is called sum of squared errors. Sum of squared error has another term which is called residual errors. Residuals are those things which we don't have a reason for. We don't know why they occur. They're called residuals. Sum of squared errors is also known as residual errors. So when you build these models, especially when you go to your deep learning part and all these things, you'll come across these terms. Total error is the distance between your actual data point and expected value. Okay, so if the average height of this class is 5.5, the difference between your height and 5.5 is the total error. Now you built a model to predict the height of a person in the class based on the characteristics of the person. So your model predicts some value for you. So the model predicts the height to be 5.3. Your actual height is 6. 6 minus 5.3, that is 0.7. 0.7 is the distance between, 0.7 is this distance. Your actual height minus predicted height. Right? The distance between your height and the class average, that is the total error. Okay? So you'll come across three terms: total error, sum of squared errors, and regression error. Keep in mind, regression error and residual errors, these two together is your total error. And don't mistake the word error. Error means variance. Error means variance. Of the total variance in your data set, I told you one part of the variance is caused by the deterministic, the other part of the variance is caused by the stochastic, non-deterministic. Same thing. Non-deterministic is your residual errors, sum of squared errors.
So also you told this, see, total error or regression error, what a residual, is particular to particular point, right?
No, in this case, I'm showing you only one point, but you have to imagine all the points together, because this SSE, SSR, they're across all points put together. What I'm saying is what contributes to SSR and SSE. That's what I'm showing you. So you have to imagine all the points here. That becomes too cluttered. That's what I'm showing you. What contributes to SSR, what contributes to SSE, that's what I'm showing over here.
So least error is belonging to SST, right?
Yeah. Least error is belonging to SST means?
I mean, we are talking about total error.
Total error is this. I want to minimize this. Unexplained error. That is what my objective is. The gradient descent works in finding the best fit line for you, where best fit line is that line where this error is minimized. Because I don't want a model which is not able to tell me why. I want a model which tells me why this error.
So you will not try to reduce the regression error?
No, we will not try. We will not do that. Because that is deterministic. I know why it happens.
It's because of the variance of the...
It's because of the natural variance in the process. Okay, when you're running a process, many things come into play, factors come into play, because of which the values change here and there around the expected value. That is okay with me. But for a given value of input, there are multiple values of y that I don't understand. So for given value of input, there should be only one value of y. Why are there multiple values of y? That I don't understand. That part is my unexplained error. I want a model which unexplained error is minimized. I don't want a model where unexplained error is very high. What is the use of that model? It will not predict anything.
Okay.
When you say given value of x, you have one value of y. So in this case, in this case, the P2 is that one value. That's what you're talking about.
P2 is predicted value, but you have multiple values of P1s spread around the line. That gap is unexplained. That variance is what we call stochastic, random variance. We don't know why it happens. So basically the idea is to minimize SSE, that's all. The bottom line is minimize SSE. So increase the SSR to SST ratio. That is what our objective is. Yeah. All right, let's move on. So before you build the model, you have to evaluate each independent dimension and see what is the R value. R value, coefficient of correlation, comes into play to help you identify good predictors given the target. Okay. Once you build the model, I want to see how good the model is, how reliable the model is. For that, we use another metric. That metric is called coefficient of determination. And this is represented as R square. But before you jump to it, I should caution you, R square is not always R into R. R is a coefficient of correlation. So natural to think that R square will be R into R. That is true only when you build a simple linear model between one dimension, one target. It's only true at that point. In multi-dimensional, multivariate analysis, where you have more than 2-3 dimensions, you can't say R square is R into R. Okay? So R square is just a symbol which represents another metric called coefficient of determination. How much of the total variance in your Y has been explained by your model? Keep in mind, the total variance in Y is consisting of two components: deterministic, non-deterministic, stochastic, random. How much of this total variance in your Y has been explained by your model? That measure is called coefficient of determination. Obviously, a model which explains maximal of the variance in Y, it leaves behind very small residuals. That model is the best model. So R square, it ranges between 0 and 1. 0 means your model is not able to explain anything. Absolutely useless. 1 means your model is able to completely explain all the variance in your target. There is no residual. Such models don't exist. We can never build such models. Usually R value will be between 0 and 1. The closer they are to 1, the better the model is. Because in simple linear models, it's a squared term, it can never be negative. But keep in mind, in multivariate analysis, it's not just a square term. It's something more than that. So it'll always range between 0 and 1. Are you all okay?
How much variance in Y means? Like,
if say this is 0.8, that means your model is able to explain 80% of the total variance in your Y. Total variance, which includes stochastic and deterministic. Right? So your R square should be as close as possible to 1, your model will be good. So this metric is used to evaluate the performance of the model, while R is a metric which is used to evaluate the independent dimensions when you're building the model. Geometrically, okay, if you take one simple linear model of one X and one Y, okay, that's what I'm showing here. So this is where your X bar and Y bar meet. Please look at this carefully. This is my Y bar, this is my X bar. Okay. So there is an actual data point. Xi minus X bar is this, Yi minus Y bar is this. That gives us an area, a rectangle. We saw that earlier, right? That area represents the total variance in your data point. The total variance in this data point, the covariance in this data point because of X and Y. This is that area, the light gray area. The light gray area is this. It's behind this dark gray. Okay, the light gray area is this. That light gray area is a geometric representation of the total variance because of X and because of Y in this data point. Of this total variance, for a given value of X, your model is predicting a value of Y to be this. So this predicted value of Y minus Y bar, X bar, this dark area is the explained variance. How much of this total variance has been explained, captured by your model? R square is the ratio of the dark area to light area. What you're seeing on the top, this is the residuals, unexplained variance. So R square is again a ratio, where the ratio is between the total variance in the data points and the variance explained by your model. That ratio is called R square. Obviously, the lesser the residuals, unexplained variance, the better the model is.
So we want more R square actually.
Yes, exactly. But there's a problem. There's a problem here.
The problem I can explain to you in simple terms.
The problem is, go back to our discussion on R, where I told you, if there is no relationship between these two, the target and the independent variable, you have to get a perfect symmetrical distribution. But the probability of getting a perfect symmetrical distribution is 0, which means you're going to get some asymmetrical distribution. The moment you have asymmetrical distribution, your R value will be greater than 0. Magnitude, this way or that way, which means R square will be greater than 0. R square is not considered as a very good metric for evaluating the models because it is easily impacted by fluke relationship. So we make use of another metric that is called adjusted R square, which is nothing but R square minus fluke. There is a formula for this. How do you find out the fluke content? Which I am going to avoid right now because it's too detailed to discuss. In case you're interested, let me know, I can share it with you. Conceptually, it's easy to understand, but the argument is very lengthy. We won't have time for that. That's why I'm going to ignore it right now. So the metric that we'll make use of to evaluate our models is adjusted R square, not R square.
But in real time, we don't calculate this fluke.
We do. It calculates. The algorithm does automatically.
We do. Okay.
We know.
The beauty of adjusted R square is, whenever in your model building exercise to predict your target, when you include useless variables which don't really have any significant impact on the target, but their relationship is statistical fluke. When you use such useless variables, R square will keep on going up and up and up. It will come closer and closer to 1. But adjusted R square will go down. It will decrease. So when you include useless variables in your model, adjusted R square will go down. It will reduce, whereas R square is likely to go up. Adjusted R square will go up only when you include good variables in your models. Good variables are variables whose relationship is significant, strong. So we use adjusted R square for evaluating our models. One thing that you need to keep in mind, conceptually get it clear, any attribute that you use in your model building, any attribute, that attribute will always have both the components, good R and fake R. It will have both the components. But in a good attribute, the percentage of this will be very, very high compared to this. In a poor attribute, useless attribute, percentage of this and this will be almost similar. That is why when R value is close to say 0.5, 0.6, part of it will be caused by fake R, part of it will be real R. How much is real, how much is fake, I don't know. That's why it calls for further investigation before you decide to use that in your model. When R is close to 0.5, 0.4, 0.3, we don't know how much of that is fake, how much of that is real, we don't know. That's why you need to further investigate.
Before you include or exclude from your models.
How we get the explainability of the fake? What is actually causing fake?
Randomness in the your sampling techniques itself will bring in fake part.
When you use random function to sample from population, since you asked this question, whenever you do sampling, any technique you use, clustering, layered sampling, mixed sampling, whatever you do, your sample will never be a true representation of the real population. It will never be. So its distributions will be slightly different from the distributions in the population. That change in distribution is what will introduce fake R's.
It's only sampling which introduces fake?
Sampling is the source of this.
Oh.
Right? Did I show you that video where I showed you universe to be under flux, continuously changing? It's never static, whereas your sample is a snapshot.
A frame in the video.
Inside when the keeps changing.
We'll keep checking, right? Shall we move on? Okay.
I'm just taking you through the concepts. I'm not telling you what is the formula for all these things. They'll become too heavy for you right now. But I will eventually take you through in case you're interested. Some assumptions that this linear regression models make. We already discussed this. Assumption of linearity. The relationship between the target and the independent variables are expected to be linear. Oh, that brings me to another point. Please be careful. When your R value is close to 0, what does it mean?
Okay, I think that's what I ended up saying.
There is no linear relationship between x and y. Okay, when R value is close to 0 between y and x, that means there is no linear relationship. That does not mean there is no relationship. For example, if I give you a distribution like this is x and this is y and this is parabolic, there is no linear relationship. When you find R value for this distribution, it will come close to 0. But they are related. There is non-linear relationships. So whenever you do this analysis, R value is close to 0, go back and check your pair panels, pair plots. Is the relationship non-linear? If the relationship is non-linear and you're building a linear model on that, you're doing a mistake, a fundamental mistake. Okay? Same way, if you have a distribution like this, R value will come to 0. But there is a relationship between y and x, A sine omega t. A is the amplitude. Sine theta, you know what theta is. So when R value is close to 0, that does not mean there is no relationship. It means there is no linear relationship. If you have such attributes in your data set, then you may have to think twice before you use linear models.
So unless we draw this pair plots, right, we'll not come to know that we have this kind of non-linear relationship. So is it always suggestible to draw pair plot for each?
100%. If you ask me, I'll always say pair plot is the most important tool you have in your toolbox, which you should use to understand your data.
And suppose we got some pair plots, so we should not try those attributes at all for the model.
Try a different model, maybe a non-linear model. Okay. So now that brings me to a question: what is linear and what is non-linear? Okay. Now look at this. This is slightly funny and at the same time something which is actually serious. This y and x, okay. Mathematicians will say, suppose this is x, this is y, and the expression is y is equal to x square. Mathematicians will say this is a non-linear function. Data scientists call this linear function. Okay. What we can replace this with some value k, so y is equal to k. So I can convert this into a linear and then build linear models on this. So when you build linear models, y equal to mx plus c, the reason why they're called linear models is these coefficients, they are not raised to the power. They're raised to the power 1. That's why they're called linear. They're linear in terms of coefficients. If I have a model like this, y equal to mx square plus c, for us, it's a linear model. Okay, so don't get confused with this. A lot of mathematicians will say this is not linear, but for us in data science, scikit-learn or R, this is a linear model. It'll show us a trend. You'll see that if you do an auto MPG case, in auto MPG case, MPG is the target, and your X is a weight of the car. You will see that the data points are scattered like this.
You can still use linear model on this. You can still use a linear model on this.
if R is close to 0 and if my scatter plot showing quite dispersion, so in that case I can say it's a real one. So I can remove it.
Yes.
But if R close to 0 and if there is some parabola kind of thing, in that case.
Non-linear models you might have to go to. Non-linear models are models where these coefficients themselves are complex coefficients. They are not simple coefficients. They are not simple ratios. They are something like e raised to power I theta and all those kind of things will come over here.
If we have in multi-independent variable case, if one is showing linear relationship, other is in that case.
So you will have to try both. Build a linear and non-linear. See which generalizes. Finally, what is the objective? Objective is it should have minimal bias variance errors. Which one gives us that minimal bias variance error? Put that in the picture. Combo is what we call ensemble techniques. In production, we never put one single model into play. We always put a multiple models grouped together in a play. We always install multiple models put together. Varun, good morning. No problem, sir. That's okay. Camera is facing me, not you. It's okay. Right? Okay. But don't knock the camera off here. He is also sleeping. Right? So what we do is, have you seen this Kaun Banega Crorepati? Have you noticed that the audience never go wrong? Though the audience individually may not have very high IQ, but put together they rarely go wrong. This concept is called wisdom of the crowd. The same concept is used in data science also. When we productionize our models, we don't put one single model into play. We always put a collection of models into play. That is called ensemble. The algorithm assumes that there is a linear relationship between independent variables and the target variable. It also assumes that there is no relationship between the independent variables. That all algorithms do. There's nothing particular about this algorithm. Assumption of normality of error distribution. This algorithm assumes that the model that you build, the best fit line would be such that the variance around the best fit line will have normal distribution. What do you mean by this? If this is my best fit line and the data points are scattered around this, and when you look at it from this angle, it will have a normal distribution. This is not guaranteed. Sometimes you end up with a best fit line, and the best fit line you might see a distribution like this, more errors on the positive than on the negative. This happens when you have outliers in your data sets. This algorithm, all algorithms will go down on their knees when it comes to outliers, but this particular algorithm is prone to outliers. If you have an outlier somewhere in your data set, the best fit line will get pulled towards that. It will get pulled towards, it will gravitate towards the outliers. Okay? So when that happens, the best fit line that you get, the MNC that you get, that MNC may not be the right M and C for your production. So model may perform poorly there. Okay? So when you build up models, linear models, any model, the first thing we have to do is handle the outliers first. Okay? There are various ways of testing this out, whether this is happening or not. One of the ways of testing this is you do a scatter plot between the actual values of y and predicted values of y. Okay? Between actual values of y and predicted values of y, since the data is spread around the best fit line, there should be no correlation. The distribution to be scattered like this. Predicted value of y, actual value of y, there should be no correlation between them. When there is no correlation between actual and predicted, that means your data is evenly distributed across this best fit line. Sometimes you might notice there is a trend in these errors. There is a trend, some kind of a trend. In the difference between actuals and predicted, there are trends, which means there is a trend in the residuals. As the value of x increases, the residuals increase in magnitude. When you see such trends in the residuals, that means there's something not correct with your data sets. maybe you're having outliers, maybe you're building models on non-linear data sets. Those are kind of things which will come out. I don't know whether you heard this word, homoscedasticity of errors. Homoscedasticity, heteroscedasticity, there are two things that will come across in statistics. What it means is, as you build the model, the errors should not spread out like a cone. The spread of errors across this model, for all the range that you have, the spread should be more or less uniform. Sometimes you will see that as the value of x increases for the best fit line, the magnitude of the error increases. The spread is still normal, but the magnitude of errors, residuals for higher value of x is different from the magnitude of errors for lower value of x, the independent variables x. Such things indicate heteroscedasticity, homoscedasticity. The expectation is it will be homoscedastic. Homo means homogeneous. Okay, so the residuals, irrespective of what the range of x is, will be similar across all the range. Assumption of independence of errors. I mean, error done in one record is no way influenced by the error done in another record. Error done on one dimension is no way influenced by the error done on other dimension. The dimensions are independent of each other. That assumption is what is usually violated. But still, we go ahead and build our models. I found a very good what you call site which discusses these errors. I've given you the URL here. By any chance you've done this Durbin-Watson test statistics? You've done statistics, right? The inferential and this thing, descriptive statistics. Inferential statistics, you would have done z-score, z-test. You've done all the t-tests and all these things you've done, right? Okay. If you've done those things and if you remember those things, maybe you would like to visit this site. A lot of information. Please expand your horizons. Go beyond what we teach you in the class. It's just not possible to teach everything in the class for the time limit. So go beyond the whatever we teach, expand your horizons. Yeah, that is what will give you a very firm, sound footing into data science, and you'll be able to face situations confidently. So wherever I come across any URLs, any articles, I'll share those things with you on the slide. Advantages, we are still not out of the woods. There's still much more to come. We're not yet learned the full stuff, but we'll do a hands-on and then we'll see the other stuff. Advantages is very simple to implement and it's easier to interpret, provided the number of dimensions is less. So when I have equation like y equal to m1 x1 plus m2 x2 plus c, I can give a physical meaning to this. I can say for every 1 unit increase in x1, how much y changes, that is given by m1. So I can physically interpret this. I can give physical meaning to this equation. You can't do this in all the cases. You may not be able to do this. Suppose you are using neural networks. You can't interpret those models. You don't know what they are. They're all black box.
Sir, what do we mean by physical definition?
I can convert this, whatever this formula is telling me, I can map it to English, right? I can tell you in day-to-day language what it is telling you. I won't be able to do that if I use, say, random forest. You're going to do ensemble where you'll do random forest. Random forest is a black box model. We don't know what it's actually doing inside. Support vector machine is a black forest. We don't know what black forest. Black forest is a pastry. Black box. We don't know what it's doing inside, right? This model is a white box. Outliers can bring it onto its knees. This particular model is prone to outliers. All linear models are prone to outliers. Decision tree is not prone to outliers. And this is a very important point. Since the linear model goes through the point where x bar and y bar meet, the best fit lines, the lines evaluated for you go through where the x bar and y bar meet. If your x bar and y bar are not reliable, then your model itself will not be reliable. So if I built a model on a dimension y and x, where this is a very large spread, the x bar is not reliable. When x bar is not reliable, how will the model which is going through the x bar, making use of this x bar, how will the model be reliable? Right? So the more time you spend in selecting your attributes to build the models, the higher the quality of the attributes that you use to build the models, the better your models will be. And the last, boundaries are linear. This is a problem not in regression, this is a problem in classification. Okay, so if we can use linear model for classification also. So if you're having a distribution of classes like this, okay, and then this, and you're trying to build linear classifiers, you'll get probably a line like this as a best fit line. So above is this triangle, below this is circles, and one triangle is. Whereas on the other hand, if you have made use of non-linear stuff, non-linear models, then probably you would have got a better result. Maybe you would have gotten something like this. Okay, so if you use non-linear models, it might do a better classification than linear models. So this limitation is not in regression, it is in classification. Let's do one hands-on. Okay, the hands-on is not AutoMPG dataset as it is given here, it's the other one, which is simplistic. So we'll start with simpler ones. The other one which I've given to you is CAR. Okay, CARPA is linear regression. I've taken the dataset directly from the UCI site. It's called imports_imports-85.data. This is the name of the data file. Okay, so instead of downloading it, I'm directly reading from there. So let me begin. Matplotlib is an instruction to the Jupyter notebook to make all the plots in the notebook itself, sorry, Jupyter server. I'm importing pandas, numpy, and from scikit-learn linear model libraries, I'm importing the linear regression. You can have linear classifiers also. Then I'm reading the CSV file which is available in this URL. It's a comma separated file, and I've taken all these column names from the UCI dataset. So that gives me the data frame which I call car_df. This is my data frame. All of you okay? So this is like loading a data into a table. So let's look at two records. Transpose is not a must, but since the number of columns is huge, I put a transpose. I'm seeing first two records, record 0 and record 1. There is obviously missing data in some of the columns. And there is string data types in other columns. Fuel type, gas, it's a string data type. Number of doors, 2, it's a string data type. All right, no problem, go down. Our objective is to predict the last column. Given all these independent variables, can we predict the price of the car? Is there a relationship between price and all these variables? That is what we want to find out. What is that relationship? But before you do that, look at the data types. Many of the data types are object. Object means string. Machine learning algorithms cannot handle string data types. They have to be converted to numbers. So what I'm doing here is, I'm going to convert into numbers, but before I convert numbers, I'm dropping some of these columns. The reason I'm dropping these columns is, if you go and take a frequency count on these columns, fuel type for example, or engine location for example, most of the records have only one value for this. This is called low variance filter. Look at all the data provided to you. In the data you have columns, where in the columns there is not variance at all. There is a gender column. Gender column, all the data is about males. Then that column is useless. It's not going to give you any information. Such columns are called low variance columns. Though they are supposed to have multiple values, they have only single values, a few values. We remove them from the analysis. So when I did this,
So you usually do this check and get to this conclusion?
Yes. You do frequency count Very complex application.
What I did is I've manually browsed the data file. This is an Excel sheet, CSV file. You can actually see, let's do it now, why are we talking? Let's do this. What you do is, go to this site and let's download this data set. Control C, okay. Now, HTTPS, double quotes. Thank you. Now we'll save this down. We'll save it as. Let's save it as text document, and then we'll load it up. I'll just call it. Okay, where am I saving it? I'll save it on desktop. Okay. Done. Let's open it. Okay. Let's start Excel. Excel is running into problems with C. Oh God. Oh, okay. Okay. It's going to clash with their recorder. So I'm not going to open this. Let's get on to this code, but do this analysis. You'll find that these columns are having low variance filters. They're fit to be kicked out. Right? So then what I do is I saw the car data types, the column data types. Most of the data types are object string types. I dropped my useless columns. Number of doors, most of them have 4 doors. Then fuel type, most of them are giving the fuel type as gas. Engine location, most of them is front, 1 or 2 is in the rear, so on and so forth. So once I drop them, I'm still left with some object data type. Number of cylinders is object. And any other object data type? No, only that is object data types. Single value there, we're dropping it. Okay. Which means the current price of the car is not a function of that, it's a function of other variables. Okay, look at this. Hey guys, do you understand why we drop low variance filter? The reason why we drop low variance filter is the price is not influenced by this particular column which is low variance. If the price was impacted by this column which is low variance, then all the prices should be fixed. Right? Which means the variance in the prices is because of the other columns, not this column. So that's why we drop it. Now the number of cylinders, what I'm doing here is I'm converting all this into numbers. So wherever I come across a string called 1, I replace it with numerical 1, 2, I replace it 2, and so on and so forth. You should do this with care. Okay. You should do this with care. Suppose you had a column called gender and the gender was male and female. Then I cannot do this blindly like this. Because if I replace a gender, say a male with 0 and a female with 1, then I'm introducing an order in that column. That's called ordinal columns. 0 is less than 1. But there's no such relationship in the real world. So if you have a gender column, then I will use a technique called one-hot coding. One-hot encoding. I will use that technique to replace my strings into numbers. That example I have given you in AutoMPG dataset. Okay, you look at that later. Okay. On the other hand, if I have a column called income group, where they have income groups like low, middle, high. Now there I can go and replace low income group with 0, medium income 1, high income with 2. Because the same order which exists between 0, 1, 2 exists in that column also. Okay. So if your column is an ordinal data type, you can go and introduce order in your numerical values. If the column is not ordinal, gender column, then you cannot blindly convert them into 1 and 2. You have to resort to one-hot coding. In scikit-learn, there's a facility function called label encoder. Label encoder introduces order in your data. So be careful when you're using that. Instead of using label encoder, use one-hot coders.
All right. Everything has a but. Yeah.
Before dropping this variable, we have to convert it to level encoder or one encoder.
Which variable?
We dropped all the variables.
Not necessarily. Since we're going to drop, why do you need to convert?
Then how we will check the variance of this?
I manually check.
Frequency problem. I just did like car underscore def not really so it showed some of the values which have the integers, which are only integer or float.
Yeah.
I didn't check the character. That we have to convert to.
That if you want to do it here, then
So basically you did the background job and then it's fine.
Shall we move on? Okay.
So be careful when you're converting your object data type into numbers. Don't end up introducing any order which doesn't exist. So when you use one-hot coding, have you all seen one-hot coding anytime? You're not seen one-hot coding? Okay, I'll tell you what one-hot coding is, then we'll move on. Sorry, you have a column gender, and the gender column has male and female, okay? This I cannot use as it is in my modeling. So what I do is I convert this into numerical data types. All data types should be numerical. So when I convert into numerical, I use one-hot coding. What will happen is, it will replace this gender column with two columns, gender underscore M, gender underscore F. Okay. Wherever the record is M, you will have 1 here, 0 here. Wherever the record is female, you will have 1 here, 0 here. So this column will be dropped. In your data set, you will be left with this column. 1 and 0 will be stored on the hard disk or in wherever you're storing it as numbers.
Numerical values.
Okay. In last class we had used this category of category.
Can you just name this?
Yeah.
We used what?
Category or something.
Level encoder we used. We just manually converted. We didn't use the scale category. Last time we just converted to category and then we changed it to 0 and 1.
0.
But we didn't use level encoder and 1 or encoder.
Be careful when you're doing this, sir.
Giving for the same problem.
You see, level encoder is something like it will do a sequencing 1, 2, 3, 4, 1, 2, 3, ask for the number. But what happens if you see like cities, let's see, we count 2, 3 cities, it doesn't have 1, 2, 3. If you have like 10 themselves,
Bore and Stokes is right now object. So I'm dropping these data types. Okay. And here car data types, let's say again, Bore and Stokes is still object data types. Okay. Here I'm converting my cylinders into numerical data types, and here I'm converting my data types into this thing, float. Okay, guys, all of you with me on the cylinders till cylinder point. Okay. After cylinder point, what I've done here is based on the experience I had in the other data set, where there were missing values. In AutoMPG dataset, you'll see missing values. Okay, so what we do is, if we come across any missing values, replace it with NaN. NaN means not a number, null values. Okay, so what I'm doing here is car underscore df dot replace wherever you come across with some question mark, replace with NaN. But I didn't find any question marks in this dataset. The question marks were there in AutoMPG dataset. Okay, so we can actually delete this line. We don't need it. Then at this point, what I'm doing is, there are question marks there. Oh yeah, sorry, there are question marks there. Correct. We saw it here, right? We saw it here. Question marks here. Sorry, mistake. There are question marks here. These question marks now would be replaced with not a number, null values. Okay. When you replace question marks with null values, you can do numerical Python operations on it and convert into appropriate values. Okay, that's why we did this. Move on. My data types right now are, after changing the data types here, after dropping the columns here, some of the data types are still object. Object means string data types. So what I do here is I first convert my cylinder into numericals. Then I change my data types here. Look at this. car underscore df bore, I replace that with as type float. I replace stroke column as type float. So I'm changing all the data types to float. Because many of these columns, let's say which column had that question mark, normalized losses. Normalized losses. It's already a numerical column, I think. Yes, it is already a numerical column. So I don't need to change it. There you go. It's already a numerical column, so I don't need to change it. Rest of the columns which are object data types, I'm changing into float types. Till this point, is it okay? Once I've changed the data types to numbers, numerical, I know there are many missing values. So the strategy I'm using here for missing values is replace the missing values of price column with the median of the price column. I want to explain this step to you. So I have a data frame, and in this data frame I have one column. This column is called price. In this column there are many NAs. NA. Wherever there are question marks, we replaced all of them with NAs. The question mark has been left behind by the data entry operator because when he was entering the data, he did not have values for those columns, those records. Okay. So we replaced question marks with NAs, all this became NA. Because now these have become NA, I can use the function fill NA. What this function does is, if you see that syntax, what I've done is find out the median of this column. Whatever values are available, using those values, find out the median. Replace the NAs with the median of this column. It is always safer to replace missing values with missing values with median, because means they are easily impacted by outliers. Mode is used in categorical variables. We are running with float variables. So we always replace mean or median, but we are not yet checked the outliers. All columns will have outliers. Mean get easily impacted by outliers. So if you replace these values with mean and go and remove the outliers, then these values will be completely incorrect. So replace with median. Median is not impacted by outliers, right? And the beauty of this is, in scikit-learn, I can find median of even an object column. The column is supposed to be numeric, but because it has question marks, the data frame is converted into an object data type. But you can still go ahead and find the median of that column. Why? Because median is physical central value. Mean is mathematical average. It's a calculated central value. You cannot find mean of an object data type. You can find median of an object data type. Right? All of you getting the difference? That is where the difference between Python and R comes. In R, I will have to first convert into numerical value even to find median.
Sorry, anything? So as a thumb rule, can we say that always there is median?
No. Now, how do you address missing values? Okay, how do you address missing values depends on your analysis of the data and why the values are missing. The values can be missing because of some random reasons. We call it randomly missing values. Values which are randomly, you don't see any patterns in them. They're missing values in all records, in all columns, randomly distributed. Then we say that data is missing at random. There's no particular reason for it. Okay. Whereas there can be situations where the values are missing because of some reason. They are not because of randomness. For example, if you take income, usually you will find nobody wants to disclose their income. So you'll find missing values in that income column, many of them. So depending on what is the reason for that missingness, you will apply different strategies. If it is income column where the values are missing because of the nature of the column, then I might have to build a submodel, a model inside a model, where I predict the values of the income based on the other attributes available. So my domain knowledge will come into play, which will help me understand What are the other attributes that this income column is going to rely on, depend on? How can I guess it? So whenever I create such imputed values, as we call them, I'll create a new column, income imputed. So I will not touch the original column. I'll create a new column called income imputed, where all the data available is copied as it is, including the missing values, and the missing values are imputed from the other columns. That is one strategy. If your data is missing at random, then replacing the column with a median is the default strategy we use. Look at the spread of the data on that column. If you see long, thin tails, mean is not reliable. So we replace with median. Right? There is a package available called mice. It's available both in R and Python. In Python, it is available in another package called stats model. Stats model. Mice stands for multiple imputations through chained equations. Multiple imputations through chained equations. Yes. When you run this package on your data set, it will automatically try to replace the missing values in all the columns with predicted values where predictions will be based on the other columns. It will establish the relationship, it will see which one is strong relationship, it will go and impute. So one column's missing value might be imputed multiple times from multiple columns. Please go and read about this. It's a very powerful package. When something comes with power, you have to be very careful in using it. So read about this mice. I'm not going to cover it here, but it's a very beautiful package. You should read about this. And just to add to the confusion, apparently the mice implementation in Python is slightly different from mice implementation in R. Though they both call it mice.
Suggest a lot of things also. Low variance in automatic drop. Nice.
So these are the tools that you should be aware of, you should have in your portfolio when you start doing data science projects. All right, all of you on this? Shall we move on? Once I've done this, then I go and do my basic statistics, diff, describe with descriptive statistics, and you know how to interpret this? All of you are aware of this? Take any column, say height of the car. First thing you should look at is difference between mean and median. The mean is 53.72, median is 54, not a very big difference. 53.72 and 54.10, not a very huge difference to worry about. Look at the distance between the length of the left-hand tail and the right-hand tail. Left-hand tail is minimum minus first quartile. 47.8, let's take it as 48, 48 and 52, that's around 4 units. 4 units. Difference between this and this is again 4 units. So it's going to be a very symmetrical bell curve. The distribution is likely to be a symmetric bell curve for height. All right, I don't see any skew to worry about. Look at the car weight. Same story repeats here. 2555, 2014. If there is any column where the mean and median are very different, then you might be having a skewed data set. Look at this one, price. Now price is the target, forget the price. Let's see if our analysis stands. Let's see whether it stands, okay. So this is a numerical way, a statistical way of analyzing your data, but instead you can do a pair plot. In pair plot, I always prefer to have the diagonals in form of density graphs. How do you get that? When you call the pair panel, you give diagonal kind is KDE, kernel density estimates. When you do this, you get the plot like this. Now let us spend some time on this. Always keep in mind the output of the pair plot is a square matrix. It has as many rows as many columns it has. Okay. So this is rows versus rows comparison. So we have normalized losses, then we have wheelbase, we have length, so on and so forth. What I've done is from car df, I have taken using index locator all rows column 1 to 16. Yeah, column 0 is my column 1 to 16. How many are there here? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I have not taken the price column here. So what we do here is, instead of doing this, you do this. You do this. Just comment this out. Okay. sns.pairplot car underscore df KDE. You do this. We'll do this pair plot. Now we run this. So let's let it plot. Fortunately, it's coming out fast. Yes, sir. Got it. Now I want to make sure my price column is reflected here. We're going to predict the price, right? So price column is, I think, second last or something. Cylinder MPG it's last but one. Why is it not showing to me? I'm not getting it. One second. I probably didn't. Car underscore df diagonal. Are you able to get the price column? No, it's there in the data set. It's there in this price. There you go. Car underscore df describe, it's there in this data set. But you guys are getting it? All right, okay. Let's look at that. Okay. The first thing that you need to do is, when you do pair plot, is first thing that you need to understand is first row and first column is same, second row and second column is same, third row and third column is same, so on and so forth. Okay. And when I do a comparison of a column with itself, if I do a comparison of, say, MPG versus MPG, what kind of a plot will I get? Scatter plot? It will be a straight line. There will be no information here. There's no spread, nothing. So trying to do a scatter plot for a column with itself is useless. It's not going to give you any information. So whenever it comes to that point where you are going to look at a column versus itself, what they have done is, instead of giving you a scatter plot, they have given you a density curve. By default, they give you histograms. We have changed it to density curve. The advantage of doing that is, in R, if you do this pair plot, it will leave out the diagonals as blank. It will leave out the diagonals as blank. It will not show you anything there. Whereas what happens in scikit-learn is, they give you a distribution. Why leave it blank? Use it to show the distribution on that particular column. Okay. So that is why diagonals, you will see the distributions, how data is distributed on that particular column. Okay. So let's look at the diagonals. In the diagonals, in my case, first column is symboling. Honestly, I don't know what symboling is. Maybe I should have done that homework. Next column is wheelbase. Wheelbase is basically how spread the front wheel and the back wheel, the distance between them. Okay. We see a normal distribution, except for higher values. Higher values, there seems to be some kind of a tail, doesn't look worrisome. Look at the length of the car, again almost a normal distribution. But we see some kind of overlap here between you see multiple Gaussians here, one behind the other. may not be of a concern right now because they're all kind of overlapping. Remember which was the column where we saw a perfect match? The central values? What is the column? Bore. Height. Height was the column. This is the distribution of height. So in distribution of height, now look at this. The distance between mean and median was almost very nil. And the tails were also equally spread. We were expecting a normal distribution, but unfortunately it's not normal. What it is showing here is two Gaussians, two normal curves are overlapping each other. Okay? This is what we call the mix of Gaussians. Go to the other columns, look at this one. This one has a long tail on the right side, a long tail. It also seems to have, but these Gaussians are ignorable, they're very small compared to the other one, okay? So look at the distributions, and on the distribution part, on each one of the columns, some concern but not too much to worry about. You should never expect a theoretical symmetrical normal curve in the distributions. All algorithms assume that the data on the independent dimensions are distributed normally. Okay, that's all they assume. Apparently not so, but still it's close to normal, so I'm happy with it.
Can you explain the compression ratio, that one?
This one?
No,
this one? Okay.
Compression ratio you see here, this is compression ratio. And compression ratio, what I'm seeing here is, there are two different clusters in it. Two buckets in the data on that particular dimension. Okay. This is a clear indication of mix-up of Gaussians. When you build models, especially linear models, you should not mix Gaussians. Every Gaussian has a particular characteristic. What do you mean by Gaussians? Gaussians means distributions. Okay. So if on a particular dimension, you have two different distributions, you are talking about two different processes which have generated this data. Remember, in statistics, you would have done a t-test or a z-normal test. When do we say the two data sets belong to the same process? When they're significantly overlapping each other, the central values are not very far away from each other. If the central values are very far away from each other, likely that the two data sets have not come from the same source. If the two data sets have not come from the same source, how can we include them in one single model? What is a model? Model is predicting the behavior of the source, the process which generated the data. Right? What happens when you use mix-up of Gaussians like this is, you're going to find x bar. X bar is going to lie somewhere in between these two, which neither represents this nor represents this. But your linear model is going to go through the x bar. So your linear model will neither be good for this prediction nor will be good for this prediction. He has done some typo. Hence, a lot of typos sitting on the extreme end. This happens when you measure these terms in some fractions and he's either added one extra zero or something of that sort he's done, because of which you're seeing outliers cluttered together in one group. So I have to go and find out what are these records which is causing this long tail in this cluster. My hunch and experience tells me this is most likely a typo rather than data coming from two different sources.
Or else the graph will be good.
Yeah, yes. This will be significantly good.
How do you identify proportion?
Go and put 1.96 standard deviation limit. Yeah, this is outliers. Outliers. So I can detect anything which is lying beyond 1.96 standard deviation on this dimension.
So I can identify this.
But standard deviation will be given for the complete observation, right? But that includes data of this part.
Doesn't matter. As long as they are beyond 1.96, they are suspect.
So when you replace those outliers with values, proper values, then your standard deviation will collapse.
I think cylinder is the best example for what you are explaining.
I'll look at this. Guys, since this point has come up, I'll discuss this. In your original raw data set, suppose it's distributed beautifully, you have outliers here. You do something about the outliers. You identify the records and replace all these values with the median. Suppose you do that. Okay. When you do that, you remove the outliers, replace all the values with median. Your curve will become sharper. When the curve becomes sharper, standard deviation decreases. When standard deviation decreases, the data points which are earlier not outliers, now they become outliers because your standard deviation is decreased. So 1.96 standard deviation for both sides has decreased. So new data points will come out as outliers which earlier were not identified as outliers. And this will continue to go on infinitely. So just handle the first level of outliers. Forget the second level of outliers. They're not really outliers.
All right. Yes.
So generally, at -2 standard deviation plus 2, right? You mentioned 1.9.
1.96 because 1.96 covers 95% of the confidence level. Some people use 2 standard deviation. Some people even use 3 standard deviation. That depends on your, where it's a matter of life and death, and I want my model to be perfect as close as possible. That means I want my deviations to be very tight. Where I can tolerate some errors, my deviations can be low. Okay? So it depends on your requirement.
Yeah, correct.
Because I'm 2 different clusters which I'm seeing here. But since the size is very small, my hunch is it's outliers. And the outliers have been introduced through some manual problems.
All right.
So in this case, it is good to retrieve the outlier, or we can just remove we can remove the record. That's also one strategy.
Removing record is always the last option because you're going to lose so many other column informations when you remove those records. Row only, he's talking row. He's dropping the rows. So if you start dropping the rows for all columns where you have outliers, your data set might shrink.
Exactly. We have one in the last exercise. So what happened here, they were having a 30 attributes, breast cancer one, right? So now every column except one, every column has an outlier. Now when we are removing the outlier for every column, 569 records coming down to 237.
So that's not good.
That's not good. So dropping records is always the last option when you have plenty of data. When data size itself is restricted, dropping records is not a good option. Shall we move on? All of you? Okay, let's move. So now always start by analyzing the diagonals first, how the data is distributed on each column. This is my univariate analysis. This is what the output of DF describe is. How your data is distributed on that particular column. It's a basic statistic, it's a descriptive statistics. Next we do is bivariate analysis. In bivariate analysis, how these columns interact with each other. For example, if you look at this one, this is telling you interaction between the symboling and this one, wheelbase. By the way, in this square matrix, above the diagonal and below the diagonal, it's mirror image. Either you focus below the diagonal or above the diagonal. Okay, so let's take below the diagonal. So I know this first column is symboling versus wheelbase. What it means is, as the value for symboling increases, you see that the wheelbase trend is going down. Wheelbase is shrinking as symboling increases. Okay, but I'm also seeing a lot of noise. For a given value of symboling, there are multiple values of wheelbase. So between symboling and wheelbase, there is a negative relationship. There is a negative relationship. Okay. Look at this. This is between symboling and length of the car. Since length of the car and wheelbase are almost kind of related, you'll see a negative relationship here also, but not as well as in this case. Look at the relationship between symboling and width. It's almost circular distribution. No significant correlation between the two. Right? We can continue to do this analysis. Let me just look at this one. This is compression ratio, yeah, and symboling. For increasing value of symboling, compression ratio that you find is in this range for one group of cars, whereas for other group of cars, the symboling range of symboling is very small. For this cluster, if the cluster is a real cluster, the range of possible symboling values is much less than this cluster. That's what is coming out of this analysis. Okay. Now let us look at the other columns. Let's look at this one. Look at this. This is relationship between wheelbase and length. Obviously, as your wheelbase, this is wheelbase, as the wheelbase increases, the length of the car increases. And you're seeing a positive relationship here. The R value will be very close to 7 or 8. So this is the case where you have two dimensions and both the dimensions are interacting with each other. They are not linearly independent. But the algorithm assumes that all dimensions are linearly independent of one another. Okay. So we have ways of handling this. One way of handling this is find out using your domain expertise whether calculating the length of the car is more prone to errors or whether calculating the wheel base is more prone to errors, measurement errors. If calculating the length of the car is more prone to measurement errors, drop the length of the car. Keep the other one. However, if you're not able to take that call, you might want to run a principal component analysis, a mathematical technique, or singular value decomposition, another technique. Okay, using those techniques, we can create synthetic dimension out of this. That synthetic dimension will be a composite of these two, so I'll drop both of them and keep the synthetic dimension. I'll talk about this when we come to PCA, principal component. Right now, I'll ignore this. Okay. So in the data set, what I'm saying is there are distributions amongst columns which have linear relationship. There are distributions amongst columns which are indicating no relationship. This one, these are all no relationship. But this is negative relationship, so on and so forth. It's a mix. Some columns are related, some columns are not related.
Can you just give us the cylinder one?
Cylinder one? Where is cylinder?
Last.
Oh, sorry. Where is the last? Yes. Which one do you want in cylinder?
Just
Cylinder versus cylinder.
Cylinder versus cylinder?
Yeah. Right.
This one?
Yeah.
Okay. What is the problem here?
If you look at the cars with number of cylinders, okay, in your data set, most of the cars have 4 cylinders, 5 cylinders, 6 cylinder, and 8 cylinder. Okay, most of the cars, look at this, have 4 cylinders. By the way, these data points might be sitting on top of one another. So that doesn't mean your data set has only 1, 2, 3, 4, 5, 6 records for 4 cylinders. Don't do that mistake. Your data set might have hundreds of records for 4 cylinders, but they're all sitting on top of each other. So that's why you're seeing only 6 dots. Most of the data have 4 cylinders. Some of them have 5 cylinders, some of them are 6, some of them have 8. Only few records have 12 cylinders, very few records have 2 cylinders. Now when you go to the extreme end, where cylinder versus cylinder, that's why you see a peak in 4, some peak in 5, then you'll 6 and the small peak here. None of the other have any peaks. Now cylinder is a numerical column, integer column. You can have 1 cylinder, 2 cylinder. Then what do you mean by the spread? What is a spread? How can you have a spread on integer columns? This diagram which I plotted here is called KDE, kernel density estimates. So there are 3 words in this. First word is it's an estimate. It's an estimation of the possible distribution, density distribution, density estimate in the population. In the population, how the cars are distributed around this value in cylinder. It is a density estimate based on a mathematical function. That mathematical function is called kernel. So using a mathematical function on the available data, I'm estimating how the density distribution of this column is likely to be in population. That is why you're getting the spread. The spread is not in your data. The spread is the estimate of the distribution density in the population based on the observations in your data set. So for integral columns also, you can have spread like this, because what the kernel is telling you is in the population it's likely to be like this.
If you're building the model on this data set, it's like involving is something that as to not understood what does it mean.
I actually went and studied what symboling is, but unfortunately I forgot. I should have known.
I mean, if I come to know that this is not of a very significant use, shall I not drop this?
You can drop it. Data. See, you can't do model building without domain knowledge. You have to have domain knowledge. We have to go and find out what the symboling stands for.
But in your drop statement, like we are not dropping symboling, so we should, I think.
Why do you think we should?
Because, I mean, it's also categorical value.
So what? Doesn't matter.
If a car coming from Japan versus car coming from US, the miles per gallon is going to be different. So it's a categorical variable. Origin of the car is categorical variable. It has an impact on mileage.
If you see the domain point of view,
so symbolism drop the root on road variance what you take as a limit for that. There are columns with values. So there are columns which have a couple of values and there are some with 3 values, and you decide to drop all of those. So how will you determine which one is picking?
Look at the ratio of the distribution. In a column, there are 8 values, but majority of the records is with value 1, very few percentage of value 2, then that becomes a low variance filter. That's a candidate for low variance filter. But the skewness in the distribution, suppose I have gender column, male, female. 95% or 90% of the data is males, 5% is females. So I might take a call that this column is going to be useless for my analysis and drop it. So it's a call that you have to take. It may not be 100-0, it might be some distribution, but is that distribution good enough for you to use it? You have to take a call. And that call you will be able to take both based on domain knowledge. If I know the drivers in the people who use the car is 50-50 amongst these gender in the market, I know that. But for some reason the data which I have does not reflect that.
So I might drop the call.
Should we be doing this scatter plot matrix analysis before we drop that? Wouldn't it help that way then do that first and then?
This analysis is done on the original data set. It's not on the dropped data set. You should always, this analysis on car DF, you should always do this pair plot analysis on the original data set, always, okay? Once, because this analysis is what is going to tell you which dimensions are likely to be important, which are not likely to be important. You should always do this on the original data set. Hey, you got your coffee?
Yes.
But I think here we've already dropped it and we're doing this analysis. This is not on the original.
Hey, no. I changed it here, no? I changed it here. I asked you to.
We've removed fuel type, engine indication, all of that we've already removed and then we're doing this analysis.
No, I commented out this line. I just now did that.
But you've already dropped the columns, that's my point. You drop first and then you bring this analysis.
Car underscore D?
Yeah.
Oh, you don't have this one?
No, about this. You go further up, yeah. So
Oh, you're talking about these, yeah. Okay, yeah. You should be doing this before you do this. Before you do this. Always do your analysis on the raw data set. Okay. All right, shall we move on?
Just one question.
Yes, please.
We did analysis on compression ratio and the second one is cylinder.
Yeah.
What we found is compression ratio have 2 Gaussians, so we need to treat the outliers and what are the things.
Yes.
But in this case, we know as per the domain knowledge, we cannot treat the cylinder thing. Right?
Yeah.
Like we cannot change the cylinder 12 to cylinder 4 just because it's kind of an outlier or something like that.
No. What you can do is go back to your data, find out what is a car model, go and refer to the manufacturing because you have all this information, whether this car model can have 12 cylinders. That analysis will do. That is what you have to do. See, missing value replacement, outlier replacement, all these things you cannot do without your any domain knowledge. You have to have domain knowledge. When I went and studied this data set, I found out that for a given car, say Toyota, some particular, within Toyota, one particular subvariant, the data given for mileage was unreliable because the factory manufacturing label itself says the miles per gallon is going to be in this range, whereas this guy is claiming to be so high. So the data itself became a question mark. So you have to do that analysis. Okay. So when you do a real life project, when you get into capstone project, you have to reflect all these things. How did you analyze your columns? How did you handle your outliers? How did you handle your missing values? And you have to justify your strategy, why you did that. You can't blindly replace something with a median. That may not be the optimal strategy.
Right? Shall we move on? Okay.
For symbolic, symbolic means cars are initially assigned a risk factor symbol.
Risk, yeah, correct. They are assigned a risk factor. Yeah, that risk factor is what they connect with symbolic. Can you just read out more louder?
The cars are initially assigned a risk factor symbol associated with this price. Then if it is more risky, the symbol is adjusted by moving it up the scale.
Okay, all right. So this is a risk factor associated with the car. And this reminds me, the risk factor associated with the car depends on the color of the car. I don't think we have color here. It depends on how the car has been driven, how the car is driven. These days, a lot of people, they take pride in telling that my car has so many chips. If you buy this high-end foreign brands, they all come with embedded chips. Those embedded chips, in real time, they capture the data about your driving style and pass it on to a central server, where they sit down and analyze. And the risk factor is adjusted, recalculated, recalibrated, based on how the car is being driven. The symboling reflects that. Right? Okay, let's move. Now, are you able to understand how to interpret this pair plot? It'll come through experience, but this is where you have to do it. Okay? Move on. So what I'm doing here is, from the car_df, I am dropping the price because that's my target. And whatever columns I am left with, I'm capturing that into X. So I'm creating a new data frame called X, which will now have only those columns which are independent variables. The target column price will not be part of X. Then once again, I'm dropping number of cylinders here because this is the same problem. It's a low variance filter again. But if you wish, you can keep it. Then what I'm doing here is, from car_df, I'm dropping the price. And sorry, I'm not dropping the price. I'm selecting the price column and storing it in Y variable. So X variable is all columns except price. Y variable is only the price column. So if you have 1000 record 10 columns, this will become 1000 record 9 columns. This will become 1000 records 1 column. Are you all okay with this? So I have segregated the independent and the dependent variable. If this was R, I don't need to do this because R takes in as input only one single data frame, and along with that a formula. Whereas in scikit-learn, I have to separate this data into independent and dependent variables. Then I'm making use of the random function which generates the training set and test set. We call it train test split. When I make use of this train test split on X and Y, I'm asking it to split the data in a ratio of 75-25, 25 for test, 75 for training. The output of this will be four data sets. So let me explain this to you, because some people get confused here. So if this was my data frame df, this was my target variable IV, independent variables, target. First thing which I did is, I captured the independent variables and stored them in X. I took the target variable and stored it in y. Then on this x and y, I did a train test split. When I do this, what happens is it breaks this x and y both into x underscore train, x underscore test, y underscore train, y underscore test. This training label y underscore train is for this x underscore train. This is my test data, x underscore test corresponding y underscore test. Now when I build the model, what I will do is I'll call the fit function, fit, and with the fit function I'll supply these two. This one, x underscore train, and y underscore train. I'll supply these two. This is at this point, the gradient descent will come into play. It'll identify for you the best fit model. The best fit model will reflect the relationship between y, this one, and x. This x comes from this training set. So it will be of the form y is equal to m1 x1 plus m2 x2, so on and so forth. How many columns are there? 1 6. So m1 6 x16 plus c. This will be the model. Once the model is built, we want to evaluate it. We want to see how it performs. To this model, I'll supply the x underscore test values, which means these values. And it will give me the predicted values, y pred. Are you getting it? So I supply the test data, the x underscore test, only the test data to this model. The respective columns get multiplied by their coefficients for every record. For every record, I get y underscore pred. What is the predicted price for this car? In the data set, I know my actual y underscore test is this. Predicted y is this. What is the difference between these two? That will be my accuracy. Accuracy will be the difference between the y underscore test, which is actual test labels, versus y underscore pred, which is your predicted test labels. Right? So let's see this, but before we go there, yeah, I think we can do it comfortably. So let's look at this. Train test split. I'm calling the linear regression here. This is where I'm instantiating the linear regression model. This is where this class becomes an object. And in that object, there is a function called fit. I'm calling that fit function and supplying the training set. When you run this, this is the point where the best fit line using gradient descent is found for you. Now look at this. I'm printing out the coefficients of all those, the best fit line, the best fit plane, hyperplane rather. So when I print the coefficients, these are the coefficients. Now we need to understand what this is. You said there are 16 columns. So the 16 columns have 16 different coefficients, m1, m2, m16. This is that m1, m2, m16. m1 is 88.57, m2 is 71.82, m3 is minus 93.38. All these are those m1s. So let's understand what it means. What it means is, for every one increase in symboling, 1 unit increase in symboling, the price of the car goes up by 88.57 units. dy by dx. For every 1 unit increase in the wheelbase, the price of the car goes up by 71.82 units. Whatever the units may be, dollars, yen, rupees, whatever it might be. For every 1 unit increase in the length of the car, the price drops by minus 93.3 units. Now look at this. This is where you need to be careful. We know that wheelbase and length are positively related, we saw that. Then how come one has a positive relation, other has a negative relation? But both of them should be positive, no? Wheelbase and length are positively related. But one of them is having a positive impact on the target, the other one is having a negative impact on the target. How can that be? Such things indicate to you something is not right in your data set. And one thing which is not right in your data set here, we all know that, is multicollinearity. Engine size, when engine size increases by 1 unit, the miles per gallon, price goes up by 251.74 units. Okay, that is the way you have to interpret this. But what is happening is, some of these ratios are kind of not gelling in, they're not fitting in properly. For example, we already found the length and the wheelbase, they are going in opposite directions. Okay, that is one problem. Then we have horsepower. When horsepower increases by 1 unit, your car price goes down, whereas actually when horsepower increases by units, car's price should go up. Horsepower increase means large cars you pay more price. Bit more considered, but this is not only negligible, it's also the wrong direction, right? Good point, right? So there are problems in these coefficients which are not falling in line with our domain knowledge.
So this coefficient is what we are talking about, right? So is it saying about the weightage kind of thing? Yeah. One thing I'm not able to understand is when you say 88, okay, it increased by 88 when unit change, keeping other constant. But some values is talking about 6,000 line, 6,000 scale, one is talking about 88. Yeah. If we compare among each other, it's a huge difference. So how we are going to interpret this in after?
The reason why the 6,000 is happening is probably you have an outlier on that dimension which is pulling it, right? So we have not addressed the outliers here. One reason could be that. The other reason is if you're not able to, if these numbers are not falling in place, then we can convert them into z-scores. The entire data set can be converted into z-scores, and then we can look at this. But the magnitude of the difference, you'll still see that the magnitude is still there. Okay, the difference is still huge. And the root cause of this problem that we are seeing, the root cause for this is, 1, we have not handled outliers. 2, we have some kind of a, correlation between the independent variables, which you noticed. We have not done anything about that. Multicollinearity, right? So those are the core reasons which you will come across in all data set, which lead to overall model level problems. Okay? Now I'm going to take you through further down into slightly more deeper stuff. Let me see if I can cover it today. If not, we'll start with fresh minds tomorrow, because I need, that particular thing needs a lot of brain energy.
Brain power.
So right now, all columns has specific units. They are not normalized. So this coefficient is on the not normalized data.
Correct.
So it's always better to have to normalize the things and then calculate the coefficient. Is it like that? Because otherwise you are not able to relate the coefficient.
The coefficients will not change when you normalize. It doesn't matter. By normalizing, you're just centering the data to 0. The relationship between y and x will remain same, whether it's a normalized data or a non-normalized data. Coefficients will not change. Linear regressions are not impacted by normalizations. The accuracy score, the coefficient, everything remains same. Okay? Shall we move on?
Yes.
So Linear regression only gives the coefficient m, but not the power of that x square, those things. We cannot.
No, this is simple linear model. If you build quadratic model, then it will. Right? So let's move on and let's see the intercept. This is the intercept. I'm printing the intercept. What you need to do is model.intercept. This is the model name. Model name dot intercept. This function will give you the intercept. Whereas if you want the coefficients, you have to use model dot coefficients. Look at this. For coefficients, it is model dot coef underscore. Coef underscore will print the coefficients. Model dot intercept will print the intercept. Now the intercept that we are getting is minus 1, 2, 3, 2, 3. There's an array. In that array we are passing the index. So the first one is intercept. In the other array we have the coefficients.
I just tried
coefficient also we are passing 0.
Yeah, that is a different array. So I'm saying starting from 0 and all the coefficients.
Yeah, in my code I just tried regression model dot coefficient. So just that much. Yeah. Regression, I mean the dataset dot coefficient.
Dataset.
This regression. I just typed that code. It was showing some other results. It's not showing the whole set.
Now, are you sure you're getting 0 in IDX? No, you have to do this. See, this is a different array. In that array, I'm accessing all the elements of the array using this, which is why it's printing out all these things. You have already done that. After fitting it, the output of this is best fit line. The best fit line has coefficients. All the coefficients are internally stored in an array which is accessible through this function. This function is accessing that array and printing out the results. Similarly, there's another array for your intercept. It's accessing that array using intercept. We don't know what that name of the array is. We can only access that array through this function. This point in the graph, all these coefficients in the graph are the lowest point in your error. This is error. There are multiple 16 dimensions over here. This is the lowest point. This combination of coefficients gives the lowest point in the error graph, the best fit. Right? So let us look at the performance of the model on test data. And as you can see, performance on the model on test data is 83.6%. Not bad, not good either.
So what does it mean for 83.6?
The comparison between this and this. Okay, so the 83.6%, what do you think it is? No. This is your coefficient of determination. 83.6% of the total variance in your data, test data, has been captured by your model. R square. This is not adjusted R square, this is R square.
That means I have 80% we still don't know why.
Yes. Sum of square errors.
X minus mean.
X minus x bar is for 2 by n. That residual error is 17%. 17% of the variance in your test data has not been explained. Alright?
So where does the intercept lie on that graph?
Intercept is one of these dimensions. Error is a function of slopes and c. Error is a function of m and c, right? So c is one of the dimensions. What I showed you earlier was only one m and c. Here you have 16 m's and 1 c. We can't visualize it, so I'm not able to show it.
That's the problem.
This 83.6% prediction is accurate.
It's the coefficient of determinant. How much of the variance in test data has been captured by your model, explained by your model? Shall we move on? Okay. Now we need to improve the performance of the model. Your first cut model will never give you the results that you're expecting, very rare. So you'll always end up in another cycle where your objective will be how do you improve the performance of this model? How do you notch it up? So there are various things you can do, but before you do that, I would like to introduce you to a library called stats model. Stats model, the formula API, SMF, stats model functions. Okay. What happens is, when you build these linear models in R gives you a lot of statistical information about your attributes and your models. Scikit-learn, linear regression, does not give you those information. But there was a lot of demand for that kind of R kind of analysis in Python. So those people who support Python, scikit-learn, they came out with this library called stats model. Stats model tries to replicate the behavior of R, okay, and gives you a similar kind of statistical analysis as you would have received or obtained in R. So let's see what it does and why is it required. So I'm importing statsmodel.formula.api, I'm importing something called SMF. SMF is a bunch of statistical model functions. And this, I'm going to build a linear model using this. But before I build a linear model using this, I have to combine my X train, Y trains into one data frame, because R takes as input one single data frame. It does not take independent variables, dependent variables separately. So I'm recombining the two into one using concat function. I'm creating a new data frame called cars, which now has both the Y and the independent variables put together for training. Okay. Now look at this. When you do cars head, you get the price column on the first column, and the rest of the columns. Now I make use of the smf.ols. OLS stands for ordinary least squares. Linear regression, ordinary least square. And as input to this function, I give price a formula where I say price is a function of the various columns. The plus which you see here, this plus is a field separator. It's not a mathematical plus. And at the end of it, you will see the data file name. Sorry, the data file name is cars. There you go, data is cars. So the output of this is once again the same model. But this model has been built in R, R-based, similar to R libraries. So the model is price is equal to, I'll take the intercept later, symboling is 88.57. 88.57 symboling plus 71.82 wheelbase minus, I'll just take one more, 93.38 car length, CL, and so on and so forth. The last thing being minus 123.06 or something, intercept. This is your model. This is the representation of your best fit line. Now you can write a code in Java where you have a function where function takes as input 16 variables, multiply those variables with the respective coefficients, subtract this intercept from that, and give the output as your predicted price. Convert that Java code into a runnable jar file, productionize it, your model is in production. All right? So that is the model. Same model we got in scikit-learn, same model we're getting here, but here we're getting some extra results, which we did not get in scikit-learn. Do some of these things look familiar to you? R square, adjusted R square, look at the difference between R square and adjusted R square. Adjusted R square will always go down when you add useless columns. R square will always go up. So adjusted R square will usually be less than R square. F statistics, analysis of variance. Remember these words, Fisher statistics, analysis of variance. Then you'll also have AIC, BIC. What is AIC? Hey Guru, we would have covered in stats. AIC is Akaike information content, BIC is Bayesian information content. Alright, forget it, no problem. Not required. Let's go straight down. Most important of these is your adjusted R square. Adjusted R square is lower than R square. 80%, is it okay with you? You have to decide. But before I go there, I'll come down to this. Okay, I'm going to stop at this point. What is this table telling you? I'll just take one example and you have to use that example on others. Okay. Then I'll tell you why this is not there in Python. Now you take any one of these dimensions, say length. The coefficient for length is minus 93.3. We already seen that. And then it gives you standard error, t values, probability of t values. Remember your hypothesis testing? When do you reject null hypothesis? When do you accept null hypothesis? You remember those concepts? Remember we use a p-value there? Right? P-values, that is what is this, okay? Now the thing is, let's take one of these example, length. I told you to find the best fit line, the algorithm will try out various lines, okay? And it will find out the errors for each line for you using gradient descent. And I also told you that the best fit line that it finds out will always go through the x bar, y bar. Agreed? So it would have tried out various lines for you before finding the best fit line. For each line on this particular dimension length, you can take any dimension. For each line on this particular dimension called length, you would have had different slopes. Each line would have had a different slope, different coefficient. So those coefficients would have a distribution of their own. Those different coefficients which it tried out on the length dimension before it found the best fit line, those coefficients would have had different distributions. Of that distribution, the one given to you for best fit line, minus 93.38, maybe this one, minus 93.38, how far away it is from the central value is given by your t-score. This is minus 1.2, whatever it is, t-scores. What is t-score? T-score is a z-score. All of you remember z-scores? Xi minus x bar by standard deviation. How many standard deviations away a data point is from the central value? We use z-score for that. When you use student's t-distribution, we call it t-scores. Formula is same. Remember student's t-distribution? Okay, the formula is same. So the selected value for coefficient for length, how many standard deviations away it is from the central value for the distribution of coefficients on length, that is given by this. The standard deviation of this distribution, the standard deviation of this, which we call standard error in t distribution, that is given by this. This is the standard deviation. This is how many z-scores away it is, your selected value is from the central value is this. You multiply these two. Multiply these two, please. Multiply these two. And tell me what is the value you get. Into minus 1.24. 73. You will get back the same value. You will get back this value. Okay? Look at this. If I am doing z-score, okay, z-score centralizes your data, converts the x bar and y bar into zeros. I take any value xi minus x bar by standard deviation is my z-score. Agreed? X bar is 0. because it centers the data. So that means z-score is nothing but xi by standard deviation. So xi is nothing but z-score into standard deviation. Here we call it t, and we call this standard error. So when I multiply t with standard error, it gives me back the value that you had over here, xi. It gives me back the xi, okay? So that is the way to interpret this. Of all the various coefficients tried out on this length dimension, just select this one, how far away it is from the central value. If it is too far, maybe it's not reliable. I'll do that analysis using this. The most important analysis which I want to take you to is the p-value. What does this p-value tell you? What the p-value is telling you is, I'm going to talk only for length, but the same thing applies for all. What this p-value is telling you is, probability is 0.2. What is the cutoff probability for your confidence level? 95%? 0.05, 5%. 0.2 is much higher than 0.05. What this is telling you is, even if in the population there is no relationship between the length and the price of the car, no relationship between length and price of the car, null hypothesis, and you're taken data from that population, you're likely to find this kind of a relationship between length and price in your data, which means this is a fluke relation. I repeat, what this p-value is telling me is, probability of finding this kind of a relationship between length and price in your data, even if there is no relationship in the population. In population, the slope is 0 between these two. And from there you have taken a sample, random sample. The probability of finding this kind of relationship is very high, which means this relationship is fluke. It's a statistical fluke, it's not reliable. Look at this one, p-value. Look at this one, stroke. P-value is almost 0. What it means is, if in the real world there is no relationship in Bohr and the price, and then from that population you have taken this sample, finding this kind of a relationship between Bohr and price, the probability is very low. Probability is very low. I'm talking stroke, sorry. Probability is very low, which means this relationship is not fluke. It is likely to be there in the real world. Okay, so let me put this pictorially and explain this to you. Then we'll wind up. Let's take one of these columns, stroke and price. Same thing applies to all. If suppose between stroke and price, if suppose there is no relationship between these two, then how will the scatter of the data points look? Agreed? All of you? R value will be very close to 0. The scatter of the data points will be circular. Okay. Now, what you will observe is most of the data points are near x bar, y bar. As you move away, the density falls. That is why you get a plot like this on this and a plot like this on this. Are you all okay? When I convert this into 3 dimension, where in the 3rd dimension, this is my x bar, y bar. If I plot the density on the y-axis, question to you is, how will the distribution look? Parabola? Cylinder? Keep in mind, very close, it's very high. As you move away, the density falls. So this will be your normal curve, a 3-dimensional normal curve. A 3-dimensional normal curve is the shape of the density of distribution between 2 dimensions which don't correlate. This is the shape of null hypothesis. Null hypothesis says in your universe the data is distributed like this. Agreed? We don't know what the universe looks like, but null hypothesis says it looks like this. If so, and from there I have taken a sample, and in the sample I am finding the distribution between this core, whatever it is, say core, and price, I am finding the distribution like this, where this is x bar, y bar. I'm finding a squashed bell curve. I'm not finding a symmetric bell curve, I'm finding a squashed bell curve. This relationship is what is expressed as this coefficient. Now the question is, what is the probability of finding this kind of a distribution in your data if the real data is like this? That probability is expressed as p-value. If the p-value is very low, less than 0.05, that means your universe is not like this. We reject the null hypothesis. Whereas if p-value is greater than 0.5, we say that there is not sufficient evidence to reject the null hypothesis. So I'm unable to reject the null hypothesis. May not be, I don't know, but I don't have sufficient evidence to claim that there is a correlation.
Shouldn't the null hypothesis be, I mean, by default, we are trying to prove the other way, right? So
no, we are trying to establish whether null hypothesis is likely to be true or not. We can't do the other way. We can't prove alternate hypothesis is true or not. We can't do that.
So shouldn't the null hypothesis be, is a relationship already and...
No, null hypothesis is no relationship. They are independent. It always negates your alternate. Alternate says there is a relationship. Null hypothesis, nothing doing, there's no relationship. No relationship means this is the way. Now the question is, from this you're drawn the sample, in the sample you're saying this, what is the probability of seeing this kind of a distribution if it's coming from this? If the p-value is less than 0.05, we reject the null hypothesis. If p-value is 0.05 or greater than or equal to, we say we don't have sufficient evidence to reject the null hypothesis. So we accept the null hypothesis likely to be true, we reject this. This analysis R provides, Python doesn't. And if you look at this, this is the p-values. So this tells you the importance of the attributes. Those attributes whose p-values is greater than 0.05, useless. Statistical fluke. Those attributes where p-values is less than 0.05, good attributes. Let me be a killjoy, okay? In the statistics community in the real world, there is a vertical split between the statisticians. One school of thought says p-values is not reliable. The other school of thought, which comes from the conventional statistics point of view, they say p-value is reliable. The reason why they say p-value is not reliable is, you can go and check it yourselves. Suppose I drop one of these dimensions with high p-value, symboling, and redo this analysis. All the other p-values will change. Now the question is, between your price and your length, if there is a relationship given by the coefficient, why should that coefficient change when I include another dimension, width? Why should it change? It should not change, right? The relationship should remain relationship. Why should the intensity of the relationship change when I add another dimension to it? But when you actually go and analyze this, drop the dimensions, you see that all coefficients change. Correspondingly, all the p-values will also change. The reason why they change is collinearity. They are not truly independent. Since there is collinearity and they impact each other, the coefficients are not reliable, hence the p-values are not reliable. It is because of this reason, this split between the statistics community on whether they should rely on this or not, scikit-learn guys said, forget it, we don't need this. We have other ways of establishing the reliability of the dimensions and the models. Let's use that. That is why scikit-learn does not give you this facility. But then subsequently under pressure, they came out with stats model libraries, which gives you this. Okay. Now, just to end up the show, what is telling you is p-value, and what it is telling you the 95% confidence within which these values lie. Okay. So if you guys remember 95% confidence level, area of rejection, area of, you'll see all, you'll be able to connect to those using this. I'm going to jump this, I'm going to move forward. Last one, overall probability value of the model itself. Can such a relationship between the price and the other good attributes, does such a relationship exist? P-value is very low, which means null hypothesis overall is rejected. Model level p-value is very low. So after removing all the unwanted dimensions, hopefully you will have a reliable model.
All right.
So do we need to reject or not based on p-value?
The p-value is very less here, so we should.
Lot of columns.
If you're working for people who believe in statistics and all, I mean, not that I don't believe in statistics, those people expect p-values from you, then you have to use stats model. If they don't care about p-values, don't come here. There are other ways of deciding whether a dimension is reliable or not. Ensemble techniques and all these techniques are available with us. So we use that technique.
Most influencing factor for the pricing. Then
Use decision tree regressor.
That will list out for you the dimension, as you will see now after lunch. It will list out for you dimensions in terms of importance. Which dimensions are more important?
But don't they again use the p-values?
They use Bayesian statistics. They don't use p-values. You remember naive, you won't have done naive. You remember Bayesian this thing, distributions? They use that for this. Some statisticians say that Bayesian distributions are more reliable than this.
In this particular video, we have talked about what are the statistical terms you need to know to start your career with data science. And also, please do let us know what are the new things you want to learn from us. Before complete the video, let me tell you, Great Learning has came up with the free initiative of Great Learning Academy, where you will get almost 80 plus free courses, and after complete your course you can claim your certificate as well, and you can use these certificates in your resume and also in your LinkedIn profile to show that you actually skilled up yourself. I hope you like the video. Do not forget to subscribe Great Learning and also do hit like this video. Thank you so much.